Hi, hi, hi. Hey! Now we're back. Can you guys hear me now? Are we all good? Are we live? Let's just get some confirmation. Are we live now? Hey, yes, we're live. Great. Wait, so this is why we're live. We are really happy to be here. Welcome to day 2 of the PX4 Developer Summit. Thanks to everyone for joining in. We had a great day yesterday. There was a lot of community-driven talks. Thank you everyone that joined Slack, that joined the chat room, joined social media and followed us. You guys are doing great. This is an awesome time to be here together with you. I want to thank the volunteers and staff. We did an awesome job yesterday. Please let know the community volunteers on chat that you're here. Let us know where you're from, where you're watching from. Send us your pictures on the hashtag that's here above, the PX4 Dev Summit hashtag. If you're here to watch the PX4 Developer Summit, you're in the right channel. I'm Ramon Roche. I'm the program manager for Dronecode. We have a great event today coming up. I want to say a few things, announcements for the day. We had awesome stats on day 1. We had around 400 average viewers yesterday on YouTube, Facebook, Twitter. We also had around 400 on Bilibili, which is the Chinese mirror. In total, around 800. That's awesome. Social media is blowing up. The hashtag, thank you again. We had a couple hiccups on audio yesterday, same as today. We'll make sure we got those solved. Thank you for your response. Thank you for the feedback. Let us know. We're here, we're listening. There's going to be a few additions today. Today, we're going to have polls on Slack during the live stream. When we're switching from speaker to speaker, we're gonna throw a few polls on Slack, so make sure you're joined Slack. There's going to be a few community volunteers sharing the links on stream. There's going to be also ratings, so go to SCAD, the event management platform. You can also rate the sessions from yesterday. You can also do that from the sessions today. Please do so. It's gonna help the speakers, it's gonna help us organize a better event in the future. Let's see what we got next. The live recordings, thank you for asking for those. There's going to be available 2-3 days after this ends. Our video processing team is really busy right now putting together everything you're seeing on screen today. So give us a few days before we upload the end products for those. If you're on Slack, please let us know. Share your LinkedIn profiles, share your social media, share pictures. If you're looking for a job, jump on Slack. Say hi. If you're a company trying to recruit PX4 developers, jump on our Slack, post your LinkedIn posts, post your careers pages. Let's try to make this the best event possible we can. And lastly, there's going to be not so secret after party. That's going to happen 3 to 5 p.m. Pacific. But here's the catch. That's only going to be on Slack. There's going to be a link shared in there. Please make sure you go to Slack and get an invite to that. It's not going to be shared on YouTube. It's not going to be streamed to Facebook or Twitter, only on Slack. So make sure you go back to Slack, reach out to the community volunteers and get an invite. Having said that, I think it's time we introduce our speakers for today. The first speakers. Let's see what we got next. So looks like we got Pixhawk community-driven open standards for drones. And we got 5 speakers. We got Peter from Netherlands, Alex calling from Salt Lake City, US, Michael from Zurich, Switzerland, Lorenz also calling from Zurich, Nuno from Portugal, and we're starting the day off with a great panel. I look forward for this session. Guys, thank you again for being here. Don't go anywhere. I'll be back after this session ends, and thank you again for being here. Stand by while I connect you. Hi, welcome back. This is the PX4 Developer Summit. Your host, Ramon Rocha here. Really happy to have the Pixhawk panel with me. Pixhawk, community-driven open standards for drones. The Pixhawk Open Standards provides readily available hardware specification and guidelines for drone systems. The Pixhawk Special Interest Group is a network of companies that are innovators and maintainers of the Pixhawk reference standard. There's a regular meeting happening on Tuesdays that's hosted by Dronecode. That's one of the main benefits of Dronecode right now. I'm really happy to have the work group with me. Today we have Nuno Marquez, the founder and lead software engineer for Drone Solutions, Michael Schall, from product manager from Altharion, Alex Klima, founder and lead electrical engineer for ARC Electronics. We have Peter van der Berg, an embedded software engineer from NXP, and they're here to talk about the progress, the status update of Pixhawk, and give us a sneak peek of what's coming next, how they operate, and what's coming. All right, guys, let's go back to them now. Hey guys, you're live on stream now.
Hi.
Hi.
Hey.
Did we lose Lorenz?
I don't think so. We did? Okay.
No audio. So give me a moment while I connect you to your speakers, and I'll be right back. Hey guys, so we got a small technical issue. You guys can hear me now. Let me figure that out. I was saying that we have pre-recorded sessions from yesterday, premiered yesterday live. One of my favorite is Mark West, getting started as a contributor from PX4. If you're new to this community, make sure to watch that. There's a lot of good sessions that didn't go live yesterday that are directly uploaded to YouTube. There's also going to be a lot of those today. Please make sure to check those out. They have premiere dates on SCED, the virtual event platform. So make sure you check those out. I look like the speakers are ready. Give me a moment while I check back with them. Thank you again for bearing with us while the technical issues were live. Remember, this is here for you. The community here is awesome. Thanks for the feedback. Thanks for all the feedback on chat. Let me connect you to the speakers now, all right? 1 second. All right, so let's try this again. Welcome back to the PX4 Developer Summit. My name is Ramon Rocha. I'm the host for today. I present you the Pixhawk panel, Pixhawk Community-Driven Open Standards for Drones. The Pixhawk Open Standards provides related standard available hardware specification and guidelines for drone system development. The Pixhawk Special Interest Group is a network of companies that are innovators and maintainers of the Pixhawk reference standard. I'm joined today with the lead for that special interest group. This group meets every Tuesday. We've been meeting for the last couple of months, tremendous work for Pixhawk. I am really excited for this talk, and without further ado, I introduce you to the panel.
Hi, everybody. So finally, we're on. Thank you for the introduction, Ramon. I will be quickly introducing the background of each panelist, because our goal here is to have a really hands-on live discussion. This is not pre-recorded. We did not prepare any specific points to present. So we have here Nuno Marques. Nuno has worked in the last month specifically on the high-level CAN and onboard messaging, and I have a lot of questions for him, why that's important, how that's useful. We have Peter van der Perk from NXP. He is deeply familiar with the transport layer on CAN. NXP is the leading hardware company in the automotive space, and they have lots of experience with, for example, CAN there and safety. We have Alex, who joins us. Alex is running his own electronics company, and with that has looked very deeply into smart batteries and what it takes to really take this ecosystem to the next level. And finally, we have Michael. Michael has been the product manager of Skynode, which is a very integrated avionics solution, and is also very deeply involved in the standardization efforts around the Pixhawk standard evolution. So the first topic that we'd like to dive into on this panel is onboard avionics and how we build networks on board. A lot of you who are familiar with drones will know that there's this inheritance from hobby parts, and so the interfaces so far have been extremely minimal, for example, with PWM. And so the first question to you, Nuno, would be like, I can connect motor controllers and servos and everything right now. Like, why do I need something else? Why do I need a standard?
Yeah, so we inherited most of the best of its applications with the usage of PWM, I2C, SPI protocols, for the peripheral connection in PX4. We mostly use PWM for ESCs, for server control, I2C and SPI for sensor data collection. But although these are functional, these protocols have known problems regarding reliability, right? So there are some specifics to the technology that make them probably not suited for safety critical systems that require a much more robust layering. And that layering is not just applied to communication between central control and monitoring units, which basically connects to the different peripherals or avionic components, but also for us a redundant distributed avionics system, as you talked about. So besides that, there's the need for that master on those buses removes the ability of having a distributed avionics system which is capable of working with a central unit, or it's capable of working, but without that central unit that defines addresses, that defines data rates, etc. And that's why the usage of CAN on avionics systems became, I would say, much more relevant, as CAN brings this peer-to-peer network capability with no need for a master, right?
Okay, but that's great, but there are already CAN parts, a lot of them. Even DJI is using CAN. So why are you working on a message standard for that?
Yeah, so if we consider that each vendor actually defines their own CAN protocol, even if they use the same physical protocol as CAN 2.0b or CAN-FD, if they use their or they build up their own protocol stack and specification, that will basically mean that for an interoperable component that we're trying to achieve, right? Hardware vendors and industry stakeholders basically consuming that same hardware will have problems in actually having their components or their hardware actually compatible with the different systems. So having this standard actually assures that we can guarantee that interoperability, and at the same time, the vendors and the hardware manufacturers are also making sure they are compliant with a specific set of rules and requirements, and they know also that their product is also plug and play.
Okay, so essentially the key takeaway is with that message standard, I can just connect, I don't know, a servo or motor controller to my commercial drone, and it will just work, no software changes.
Yes, exactly.
Okay, very cool. So one of the things that I find personally a bit confusing, and I'm sure a lot of people in the audience will have similar questions, is like, you know, what we already have UAVCAN V0. Now we're moving to UAVCAN V1 as part of that proposal. So how is that related? Isn't UAVCAN already defining what we're doing? So I'm confused there. Peter, maybe you can help me there.
Yeah, so there were multiple reasons why Pavel, the designer, and the UAVCAN team decided to go for V1. But it's mainly because they wanted to move forward to one good generic system, but also support for CAN-FD as well. My apologies, I'm hearing a lot of noise. Yes, we're back again. With the lessons learned from Z0, the designers from UAVCAN decided to come with a clean slate and designed a new protocol that's simpler and also it's useful for safety critical applications. So they want to support redundancy, so that's inside this protocol. And yeah, keep it as simple as possible, I think.
Okay, so essentially what you're saying is that on the protocol level, this is a really solid base to build on, but it's not specifying everything up to the sort of full implementation messages, and that's essentially how the DS15 standard comes in.
Yes, so when you look at the transport layers, we have our CAN bus, which just has basic frames, and UAVCAN to send big frames on CAN bus, and you don't have to worry about the framing of those messages. But here is kind of where UAVCAN stops. So the interoperability between let's say a motor and an FMU is not there. And the main goal is that if someone implements such a motor controller, they can follow the DS15 rules and have a easy plug and play system. Furthermore, as a flight management unit, we know what we expect from those components, and we have an interface where we can leverage that to, for instance, include a bootloader or have a mechanism to easily set up those components.
Okay, so it's pretty much like having USB, of course not literally, but equivalent. Like I can just connect the device and it'll work.
Yeah, that's the main goal of it. The main goal is having a plug and play experience and well, still be able to go deeper if you really want to. But also for the implementer, there has to be clear rules on what your device has to support. So from both sides, you can integrate to a nice, tightly good product.
Yeah, that makes a lot of sense. So if I'm interested to contribute there, and if I'm interested to make my device compatible, or if I just generally care about this, like how do I engage Nuno? Nuno, you're muted.
Sorry. Okay. Can you hear me? So we have the UAVCAN and CAN standardization coordination call that happens on bi-weekly on Tuesdays at 4 p.m. UTC. You can check the Dronecode calendar and add that event to your calendar as well. So basically, that standardization or coordination call is mostly used to foster the coordination and collaboration among the adopters and also the stakeholders of the unmanned avionics industry. And those might include, but they're not limited to, of course, the hardware manufacturers and vendors, and also unmanned aviation leading companies that use specific avionics components that leverage CAN or UAVCAN. And mostly what happens on those calls as a specific goal, we try to discuss and organize the efforts around writing and improving the SO15 CAN drone standard. And it involves some open discussions over the specific matters of the standard. Also reviewing what was the work done on the past couple of weeks and the added and updated components, verify if they make sense or not. And of course, also define the goals for the course of work on the next couple of weeks. So we can see it like a Scrum, a daily Scrum call, but like happen bi-weekly, adding also the blocker removing, if we can say so. Can you want to hear me?
Yes.
Yep.
Okay.
Yeah, cool. So Ramon, maybe you can share the links with the audience in the chat while we're talking, so people can engage. Otherwise, I can follow up in the chat later after this as well.
Just so you know, links are in chat already.
Oh, perfect. So now that brings us to the next topic. So I already mentioned that Alex has particular experience with batteries. So, I mean, I've been using LiPo batteries for the past 10 years on sort of development systems, R&D systems. Like, why do we need to change that? Why do we need to change to a different approach of using batteries?
Yeah, I think for the Pixhawk hardware ecosystem to really evolve, we need smart batteries are kind of that last key thing to bring the safety and reliability up to the next level. Hyon from UAVCAN gave a good talk yesterday on the technical background on how smart batteries operate, but ultimately it's you can get the full capacity out of the pack safely without having to worry about completely running out too early, and so you can fly your drones longer and safer with smart batteries. So it's kind of the goal of the smart battery standard.
Okay, so how is the standard, in what state is it? How is it being developed? What are the next concrete steps for smart batteries?
Yeah, so far we've got we've defined the connector. We've got the connector, the pinout defined. We've got the the messaging set defined, the communication interface that's going to be on the CAN bus with UAVCAN V1. And as part of that UAVCAN standard, they were just discussing, we've defined the battery message set that all smart batteries that meet the Pixhawk standard will abide by. So being on the CAN bus and using UAVCAN will allow multiple batteries in parallel to be used much easier than just using SM bus. That was one main driver there. The next steps are, defining that mechanical interface and latching. That's probably the next big hurdle. Otherwise, most of the electrical and protocol is it's in place at the moment.
That's super cool. When do you expect from the adopting companies to see the first products on the market?
Yeah, so I'm partnered with Holybro at the moment to bring the first Pixhawk smart battery to the market. So that should be sometime this year. You should see that on the market, and that'll be a 99.9 watt hour 6S pack, something you can carry on a plane. And yeah, so it's pretty exciting.
I think it is. I've met people who were essentially saying like, oh, this open source flight control work is really great and we're really happy with it. But as long as our end users have to use batteries that have leads and that have to be actually, dialed in on a charger, we can't sell that to our end users. It needs to be something that just gets stuck into a charger and that never gets deep discharged. And so I think that's as important as the radio link. Very, very cool. So the natural evolution, we've talked about the network, we've talked about UAVCAN as a transport, V1. We've talked about the message set for that as part of the DS15 standard. That naturally takes us to a part that is already in pretty good shape already, which is the flight controller itself, Pixhawk. And the fact that we've open sourced the hardware design 2013, 14, so already 6 years ago, led to a lot of compatible designs because people were mostly happy with it and didn't change too much, and so it just worked. But over the time, there was more discretion, and so today we have, I don't know, 10, 15 different types of flight controller designs. They're all Pixhawk derived, but they're a little bit different, and sometimes the hardware vendors are relatively small companies and they struggle to maintain software. So that is obviously the segue, Michael, to the question to you, which is why 7 years after the first Pixhawk, do we need to standardize this? Why do we need standards for flight controllers and flight controller interfaces?
So as you already mentioned, there have been like a variety of flight controller designs over the years. And some of them, I would say, were more successful to work together with the software. And there have been issues from a sensor perspective, from a power supply perspective, or just the support from an overall community effort on these hardware designs. Now, standardizing an interface and the interface between software and hardware in that case really means that there is a clearly defined standard on how I can build a flight controller that is fully supported by the software side. Both entities know what they will encounter, and it's like it is a seamless transition in that case. This just gives confidence for an end user that he can buy a product that is, he also knows that PX4 will run nicely on that platform.
Okay, that sounds fairly important. What does that mean for future upgrades? So we know there are always new processors. There are new processors coming from NXP with automotive safety features. How does this one standard help us in that regard?
Yes, so currently integrating a flight controller in a specific vehicle typically means also integrating against an interface that is defined by the manufacturer or vendor. for a commercial or industrial vehicle, this often requires to design a carrier PCB that then interfaces to the flight controller. Introducing a standard like the Pixhawk Autopilot bus is a way to completely standardize that and open it up to the market to develop a flight controller, and that is then also future compatible to an aircraft that follows the same interface. The standard has a pinout, it defines the connector on it, it has a mechanical layout, both in size and how it's mounted and where the connectors are placed. So if a drone OEM decides to integrate against that standard, it's not just compatible with the current flight controller design that is on the market, but it also is compatible with future designs that are coming later on with better compute, different designs, or other innovations that we will see in the industry just happening naturally by like other companies growing into the market by doing so.
Okay, that sounds pretty important for this industry to scale. Good. So how, if I want to use that flight controller because I want to create my own baseboard, or I want to maybe create my own flight controller, how do I engage?
So there is like Pixhawk.org as a central point of reference where we publish also the documentation for all these standards, and you can find the latest releases that are already finished or complete. Then there is a bi-weekly call every second Tuesday where you can engage with the community where we discuss those topics. On those calls, part is the flight control designs like FMV, FX, and all these other generations that belong to it. We discuss the Pixhawk Autopilot that's there. But then there are also other standards like the Pixhawk payload bus or the Pixhawk smart battery that were also part of those discussions. So please join there and provide your feedback so you can have an influence on what we actually standardize and how the interface will look like in the end.
Very good. So, okay. I think we've covered a lot of ground. So those were, I think, my main questions. Now, I would really love to turn to the audience and see what questions are coming up. So I believe that there's one, or rather two topics that I quickly would like to cover that we haven't touched. So one is, we haven't really specifically talked about it, but part of the Pixhawk standard series is also a payload bus, and that is defining the interface to a gimbal or camera, or both. And it's using MAVLink for communication, it has Ethernet, it has USB, and it's something that you should also check out if you're interested in the standards. We're not discussing it to full depth today because we have different people on the panel. But it's something that is also well specified and where you will find drafts and where there is a bi-weekly discussion in the working group. Now, the other topic that was already asked in the audience, and please write more questions into the chat, was unmanned traffic management, UTM integration. And what are we doing there? So two things. Number one, there are a number of standardization efforts and bodies already in the space. There is also a inter-unmanned system traffic management open source project, inter-USS, part of the Linux Foundation. You can check that out. And we're implementing that, of course, as a community that's focused around the flight controller kernel. We are not necessarily driving our own airspace standards. So we're working with the existing bodies. We're really close there. We did an integration with AirMap, with PX4 and Q ground control about 2 or 3 years ago. You can, I'm sure, find the announcement online. This is something that you can also explore, and of course we're more than happy to welcome other UTM providers with an integration with Q ground control in our community. So very active there. We're not driving it ourselves though, because there are already great efforts underway. So let's see what came in terms of questions. So one question is, how does Pixhawk roadmap to compare to Skynode? So It's really important to tell this apart. Skynode is a product of a company. So from a PX4 perspective, it's just one of the products that is using the standard. In terms of standardization, we're looking at all the different stakeholders, all the different companies that participate. So there's Modal AI, there are companies like Holybro, CUAV. There are other vendors who might not have engaged yet in the standardization effort, but who are super welcome to. There are end users like FreeFly, for example, that are using these standards, or Quantum Systems or others. And the goal of the autopilot standard is to create a common base in terms of mechanical and electrical interfaces for these different parts and companies to work together. And then individual products use it and are compliant. And so you know that when a product uses the standard, that you get certain levels of interoperability, the same way as you know that if a product supports Wi-Fi or Bluetooth or USB, that certain things will work. And that's exactly the goal here. Let me see if there are more questions. Payload bus for RGB cameras only? No, the payload bus is super general purpose. You can connect a LiDAR, you can connect thermal cameras, anything. By default, we have a pretty well worked out set of camera standards, including for IR cameras, but that's being continuously expanded, so it's not limited to it. Let's see, more questions. 200 people there, no questions on standards. Any thoughts on working with parachute recovery system companies? Yes, absolutely. I mean, by all means, we're looking very heavily now in architecting software, hardware for safety, and that's part of the standardization effort. So parachutes are, of course, an important part of that solution. And so we're more than happy to collaborate on that.
Hey, Lorenz, Remote here. I have a question from the audience.
Yes.
Why reinvent the wheel with standards when the industry got plenty of standards already? Avionics, automotive, IoT, UGV, etc. Why not just pick one?
That's a good question, because everybody is trying, the old story is you have 13 standards, then you try to do one standard to unite them all, and then after that you have 14 standards. We're very well aware, but what you need to know is that we've done this Pixhawk standardization in the beginning since 2008, but really where the whole drone industry adopted it around 2013 with Pixhawk 1. And so that is a well-established thing. Google Pixhawk, see how many different models are out there. They're all using the same system architecture. They're all more or less software compatible. And that has already set a standard in this industry that a lot of people are implicitly relying on. The same way as the IBM PC set standards like the ISA or PCI bus for the PC industry. And so we're already there. We've already done it. And we've done it because all the aviation standards that are out there, they are targeting pretty high, I wouldn't say high end, I would say large, very regulated systems. And it starts with things like that every of these standard document copies is like $500. So if you're a smaller drone company and you want to implement, I don't know, an aviation system, you end up easily spending $20,000 on PDFs. And so that's a non-starter already. So our standards are not just standards, they're also open, they're free. You can just download them. That's one big topic. And then the other topic is they're compact, they're easy to implement, they're small. And again, we're not starting out of nowhere. We're taking all the legacy, all the history of Pixhawk, and we're just formalizing what everybody is using already.
Great, thank you, Lawrence. So I'm going to give you one last question, and then I need to let you go because we have another speaker queued up. Last question is there going to be a specific organization to take care of the standards?
So they're all, the standards are all part of the Pixhawk working group. That is a project of the Dronecode Foundation. So part of what we're presenting here, part of this Dev Summit. And so we do already have a nonprofit organization that is already very familiar with standardization efforts, is backed by the Linux Foundation. So we have also the professional structure around it. And yeah, that's how we're driving it.
Excellent. Thank you, guys. Thank you for your time. Hey, folks. Welcome back to the PX4 Developer Summit. Glad all your issues are gone. This was just the panel. Thank you, panelists. This was really awesome. I want to thank them for their time and their awesome contributions they're making to the open source community. Pixhawk standards, check out their website. We just linked it on the chat room on Slack and also on YouTube and Facebook, Twitter. Next up, we got an SOC independent and open platform that aims to help standardize high-performance AI-enabled drones by Dr. Jiang Zhang. He's calling from Cambridge, UK. He's the director of 96 boards, recently added Dronecode Gold member, chief scientist in AI, and board member of AutoWare Foundation. That's really exciting. Give me a moment while I connect you to Dr. Zhang. Yes. Hey everyone, we're back. Thank you for being here with the PX4 Developer Summit Day 2. We got Dr. Yang Sang from 96 Wards presenting an SOC independent and open platform aims to help to standardize high performance AI enabled drones. Dr. Yang is calling from Cambridge, UK. He is the director of 96 Sports, chief scientist in AI, and board member at the Ottaware Foundation. 96 Sports is well respected within the industry for providing innovative and flexible solutions. It provides a range of hardware specifications created by Leonardo to make the latest ARM-based processors available to developers at a reasonable cost. 96 Sports just joined Dronecode as a gold member and will collaborate with Dronecode on open standards adoption. 96 Sports plans to incorporate different components of the Pixhawk hardware standards in form of mezzanine products and new specifications. Let's hear for Dr. Yang. Let's see what 96 Sports has in tow for the community. Dr. Yang, thank you for being here.
Thank you for having me, and hi everyone. And I'm glad to be here. Have the opportunity to explain what we do, why we joined Dronecode, and what we're planning to contribute to this amazing dynamic community. So my name is Yang. I will be presenting my screen shortly as we now. Okay, so I will this briefly will be two parts of the presentation. First part, I will give a brief introduction, as brief as I can be, about who we are, what we do. Then the second part, we would like to spend a bit more time in talking about what we have been doing so far, trying to adopt the Pixhawk standard as well as to enable the high performance drone platform, as we see there is a growing need for that in the market. Not only, yeah, give me 1 second. I'm just gonna, oops, sorry. Give me that. Can you see that now? Okay, great. Okay, so 96 Sports is the only SOC independent open platform specification. What we have is we develop a range of open platform specification with all 96 board members and open up for the entire developer community worldwide to choose to use. Today, we have probably over 100 different type of 96 boards, all built with the latest and greatest SOC from multiple, all the major SOC vendors, including some of startup silicon vendors all around the world. So what we have is a bunch of companies who join together, very similar to Dronecode, as 96 board members. We also have a large, partnership companies all around the world, over 100 of them, who doing different things, building mezzanine products, developing software service, OS vendors, etc. We have been leading some of the technology frontier in the open source community, as many, as we'll probably soon see. We cover a range of the segment market from consumer mobility, enterprise computing, IoT device, smart TV, smart and networking, automotive, and AI. So what we will show a little bit later in terms of what are the main cross points, if you like, for what we're trying to do with drone community and with Dronecode in particular. So what is 96 Sports, right? A series of open platform certification which we have developed, you can find from our website. And it is designed, all of them are designed with a cross SOC in mind, which means it can support multiple different SOCs, has been tailored for different segment markets from the specification point of view, I should add. It is well supported by the wider Leonardo members and also the ecosystem. And it is today the chosen reference platform by many open source projects, which I will give some of the examples for you, and you can take a look and you take that away and take a look at many of the platforms, which I hope today many of the platforms you have been using today are actually one of the 96 boards out there. So what's 96 board is for? So we're for universal OS support. We're for the SOC independent platform to support the rapid prototyping, a single development community, and build for production. That is one key thing which we have is we believe people who would most benefit from 96 boards. It's not only building a hobby project for yourself, but actually have an idea, have actually a product concept in mind where you want to build for scale. So this is some of the projects I just mentioned, which have been using many, not only one, but multiple 96 boards. As you can see, Pixhawk here. And in fact, we have had some very successful mezzanine product from existing 96 board partner before we actually join force with Dronecode. So this list continue. I won't spend time to work on this, but the slide is I have uploaded that, and if you want to take a look and let me know if there's any particular interest you have. You will also continue to see that covers many angles from the blockchain to security to the 3D gaming to real-time kernel, and of course an OS distribution as well. The other thing is that we do work with multiple different cloud vendors as well, addressing the cloud connectivity side. Actually, it's not difficult to find. If you found many of the cloud launch events on the device end, most of them actually have a 96 board there, right? So this is just to give you a glimpse of what we do. I said the core of the 96 boards is set of the open platform specification, right? Which is one of the core area which we will be working together with Dronecode. So today we have mainly consumer, enterprise, and IoT edition, which these three are most widely being adopted already, because actually those were the first three sets which we developed. They support a wide range of SoCs, which we will probably see the names very soon. And of course, we have been developing 96 board automotive platform for the large scale, for AGVs and vehicles, etc. And I've got some background audio here. That's normal. Last year, we have launched the 296 board song, which is system on module specification as well, which has been quickly adopted by many silicon vendors. Today, this is actually one of the most popular specification, which or product built to the specification has been requested by the professional enterprise developers. Now this is this slide actually needs a bit of updating. So as I said, 96 boards consist of a large list of steering committee members, which including many silicon members. I do apologize because some of the icons need to be changing, but this give you an idea who actually are the steering committee members who join us developing those standards. Of course, we would actually in the update, which we have Dronecode there as well, because Dronecode has officially joined 96 board as well. Manufacturer partner, this is only a selection of those which we have pretty much in every continent. I'm not sure about every country, but we have in many places who working on in their specific sector of their choice. So what are the real products built to the specification? I think this would give you a good idea what they look like. So as I said, the first of three 96 board specification covers consumer, enterprise, and IoT, and this would be what it look like. What is interesting is today we have over 100 of 96 boards that features way different, a long range of silicon, and most of those are latest greatest silicon. Okay, they're not 10 years old silicons, and they are actually one thing which we see today is many companies choose to launch their product on 96 board, and silicon product. So each of those, many of those boards actually looks very similar, as you can probably see, because they follow the same specifications, which is 96 board specification. However, what is interesting is that even though they look very similar, but none of them actually exactly the same. So that is one of the key, philosophy, if you want. What we hold is that, well, we draw the line between what doesn't make sense for everybody to reinvent the wheel, but where we want to see differentiation, where we want to see people building things differently, from the IP in the silicon itself to actually the end product. So that's what two keywords I hope that people will take away from this presentation. Is 96 board is about standardization and differentiation. Right? We standardize the part where it does not make sense for anybody to reinvent the wheel, to do it twice, but join together, do it once, do it well, a plug and play. Yet we do encourage people to highlight, to focus their investment and time in building those bits, either from the silicon wise, from the hardware, from the software pieces, where they can actually gain differentiation value, which render to the hopefully the what they will gain by using these standards. So form factor wise, we have 96 port standard, extension, enterprise standard, extension, and IoT standard and extension. This is a closer look like. If you look at all these names, you can easily find on the web, Google or 96 port website. They features different silicons from Xilinx, Qualcomm, HiSilicon, MTK, Action Semi, Rockchip, NXP, Bitman, which is actually a silicon startup on the Bitcoin side, Intel and Qualcomm. This is not a complete list, as I said, but this give you a taste of what it looks like when we say SoC independent. Mezzanines. So this is very important part, because we believe mezzanine is actually the extra mile from your development platform to give you a specific angle to penetrate a certain market. So we do have a very active 96 port mezzanine committee, which is completely self-organized by the participant, the developer himself. Actually, we do have a guideline for that. We have many very interesting community design and mezzanine. In fact, we will talk about shortly about what we designed, a universal drone mezzanine to bridge between the high performance SoC powered 96 board to support the drone. So those are the mezzanine product. Majority of them are developed by the ecosystem partners. They covers from the very small sensor, Bosch sensor kit, to very sophisticated. For example, have the 5G LTE on board, 4G 5G LTE modem silicon on board, and also the view control unit. At this slide, I want to say that we are in support of the PX4 Developer Summit. We are giving away 50 of the 96 board mezzanine, most of the popular mezzanines, and this will be anybody who filling, I believe, one of the post-event survey will be able to get your lucky draw. Once you have, you will be shipped with the one free 96 board mezzanines. Okay, so hope you win. So yeah, just this, it covers all the from LoRa to robotics, audio, NB-IoT, security, LT. I'm sure there will be some of them which will fit your development needs. Operating system, this is rapidly changing on a weekly basis. Well, some of them not strictly operating system, depending on how you look at it, but it is very widely supported by a different type of mainstream, and actually some of them, probably more niched SoC operating system support. In fact, if you go on to SUSE, OpenSUSE, or Fedora, this OS websites, you will probably find a dedicated section for a range of 96 board. Middleware, SDK, and tool libraries. So we have spent quite a bit of effort actually to support and cross community, and which is, we believe, is very important for 96 board developers. In fact, what we highlight, remember, 96 board is built for production. So we're not really just stopped at actually offering platforms where you can build your idea prototype. Actually, we point a clear path from the hardware, software stack and the tooling point of view for taking you to the journey of making the mass production. So 96.4 AI initiative was first launched at March 2018, as you probably see, with 13 companies globally. Today, we have probably the most popular, AI development boards, which in 96 portfolio, including very, very popular High-Key 960, 970, Rock 960, Ultra 96, Ultra 96, and AIML from IMX 8-based NXP, different skill of IMX 8-based. So, and of course, the latest announcement we have had 17th of June, and Qualcomm's 865C-based robotic kit. So that is a very, very popular. In fact, the first ARM development box. Some of the, if you pay attention to that field, it is actually a 96 board inside. It's called a sequencer 96 board. Okay, it's a 24-core A53, very power efficient ARM machine for developers. So this is not news, but I would like to highlight again. I steal this image from Dronecode website, because I think that I couldn't make a better one. So we joined Dronecode as a gold member. And the reason why we do that is we do believe we can support in the era we just mentioned, high performance drone in the coming. And it actually does, as I said, the spirit of 96 board, we actually have considered this for long, that decided it does not make sense for us to reinvent the wheel to develop another drone specification from ground up. In fact, we decided the working with Dronecode, adopting and supporting some of the existing, such as the Pixhawk hardware standard, would be the best for the community. But in order to enable the if I may say 1.0 drone platform to the 2.0 drone platform, which was much higher demand in terms of the computing, much higher level in terms of the intelligence or mobility, and much diverse in terms of the sensor and the configuration of which we believe that, so that's what 96 board can help. So that can bring me to the second part of the presentation, is that 96 board drone. So we're focused on heterogeneous computing platform, where we enable the multiple performance silicon platform choice, and provide a flexible architecture for the developers who have probably different experience or different paths when coming to this field. And we do support and Pixar as open standard. And the picture here is, well, give you an idea of what we're thinking, right? So we're designing a pixel mezzanine board. Well, we used to connect the 96 board ecosystem from the bottom to support the Dronecode community, Pixar hardware standard on the top, right? So while we consider to not only actually 96 board main board, but the necessary, the useful, important, the 96 board mezzanine. For example, I'll give you an example here, a mezzanine which give you LTE connectivity when you have that license, necessary license in the as a modem on the mezzanine away from the main board. So 96 board CE consider that can have a range of different SoCs through the standard interface, which is high speed and low speed interface, 40 pin and 60 pin respectively, with relevant 96 board mezzanine supporting connected to the mezzanine board, Pixel mezzanine board, give you the performance SoC, where you can offload the performance computing where it does not make sense to put on the FUM module itself, and also we wanted to, it becomes a generic interface where can support some of the payload that being defined through the PPB interface. If you're familiar with the latest spec has been going on in the Dronecode community. So that is what the physical can look like. And going down another level is we call it universal 96 board drone mezzanine, right? And well, you can see the main part of the complexity will be between on that mezzanine, we will need to handle all the different interface and the relationship of that. So this today, I should say, is a draft, right? This today stays as a draft. We want to take this opportunity of the development summit to if you have any input at all, we're happy to discuss that. And we're happy to discuss that. We're happy to bring the draft to the Dronecode technical steering committee to gain more input where we can actually build this. So those are some of the proposed interface and the capabilities. I won't go through it in very detail today, but as I said, a slide is available, and we definitely welcome any input you might have. For example, you tell me, okay, this part we would probably looking at integrating more, some LiDAR sensors. In which case, we probably want to have a higher bandwidth in terms of Ethernet, gigabit Ethernet on board, and we probably need more than one of them, and to have a physical separation between different network. So we will definitely welcome that feedback, and this is a draft of our starting points, if you like. And we do put a lot of emphasis in terms of the power design, because this is one of the very practical issue which we have come across, which we believe it matters a lot in this supporting for the drone mezzanine as well. So please do take a look through the input and output we were thinking about in terms of the power distribution and the power capability. We do envisage is a separate power supply, and but yes, I won't read through them point by point because it doesn't seem to make much sense for me to do that in live stream. But if you have any question after the presentation, happy to answer them. So that's my short presentation. I hope that give you some of the idea in terms of what we want to do here, and it's not only what 19 Sport want to do here, what we want to do actually with Dronecode, with this community, and supporting your development. So thank you.
Thank you, Dr. Yang. That was great. There's a few questions from the community. I just posted those on chat with you directly.
Yeah. Sure.
Please read them out loud before answering.
Okay.
Thank you.
Okay. So first question is any effort for positioning indoor drones with 96 board? Okay, this is a very so this is good question, and I must admit today we have not actually go down to that level in terms of the breaking down to different specific use case, indoor, outdoor drones. What we have had some experience with is that in the robotics and the AGV market, obviously the indoor and outdoor, we will probably be looking at a different sensor configuration, and we will have a different capability of receiving the signals for certain input of the data, for example, GMS. And we probably will using different, will adopt a different technology to achieve positioning or navigation capability. So today I couldn't give you very specific detailed answer for drones because we haven't got that point yet, but I'm sure we will. If there's any points which you guys can give, which we will be happy to discuss that. I know that doesn't answer the question completely, but I hope that tell you what we are, as a reality. So second question is, what feature supporting AI, GPU or Tensor Core of some sort? Okay, that is a very good question. So so today, I think that majority when we talk about AI support, we are talking about many from two different angles, right? If people who from the silicon background, they will tell you will care more about how the tensor-based or DNN, deep neural network-based computing being offloaded to different IP fabric. So that IP fabric could be CPU actually, could be GPU, could be ASIC even, could be NPU designed specifically for taking offloads of those particularly neural network intensive calculation. It could be FPGA, it could be DSP, it could be all sorts of different IP fabric. It depends on how you implement them from the silicon point of view. So that's one part of it. Second camp, mainly looking at this from the framework point of view. Well, we are probably more concerned about which framework you support, natively. Do you support, at what level you will be able to support them? Are you able to charge the computing to the best fit for purpose, the silicon computing resource made available? So, so what I can say is from we probably fall in more in the first camp, is where we can, from different 96-bit AI platform, we have FPGA-based AI platform, we have DSP, we have, in fact, in one of the latest, we have actually 8 different type of cores in one silicons, and supporting, scalar-based, vector-based, and the matrix-based. Sorry, matrix is the wrong term. So scalar-based, vector-based, and tensor-based computation. But how they actually carry out that computing, changes from quite, I think drastically from silicon to silicon. Having said that, there are some actually very popular, or actually becomes quite established middleware, and which we also supporting. In fact, if I may say, they actually were also developed using 96 boards, different 96 boards, such as the TVM and NVM. And so I hope that somewhat answer the question in terms of what features support AI. The third question is the board are like Arduino boards, right? Answer is yes and no. I think the first of all is, I think we mainly not only looking at the small silicon in ARM boards and Cortex-M based silicon, we're actually looking at some of the really capable, not only mobile, but actually enterprise grade silicons. And so we're looking at actually across the spectrum. And for us, it's really, and that's one thing. Second thing is that instead of focus one or two particular type of silicons, we actually cross silicon platform. And this is why you will see startups actually building silicon startups actually using 96 board to launch the silicon, and which you probably don't see it on Arduino board. Having said that, Arduino is a very important developer community in its own right, same as Raspberry Pi, which we have actually many mechanisms to be able to enable the connection with both community. And we see them as a very successful social engineering project, but 96 board has a different target and focus in mind. And again, this is, we mainly also are today using the latest silicons as well. The fourth question, do they come with a library and API to program? Yes, every board does. And in fact, every specification, if you look at through every specification, it not only has requirement in terms of the interface, the hardware, or the IP capability of the silicon, but also have the requirement in terms of the bootloader, the firmware, the security aspect of it, the kernel requirement, the upstream status of the driver, and the binary blobs feature requirement, even to the point where some of the protocol requirement version are also included. How is the processing of an AI system in your board compared to the usual ones that are well known? Okay, that is interesting. And I think apart from one, which is NVIDIA's NI platform, and I hope that the other well-known usual ones are actually pretty much 96 boards. So next question, do all of your SBC fit on all of your mezzanine boards? Right, so that is so let me put it this way. Ideally, that is what we would like in a very in a perfect world. However, it doesn't happen that way. But what I can say is that most of our mezzanines and all of the 96 board officially compliant products, they are electrically compatible. And however, because there are some optional features, there are some mandatory features, whether they are supported the IOs, in the same way through those connectors, I can't vouch for. I can't say 100%. But yes, the cross compatibility between the mezzanines and the SBCs, the main boards, are certainly one of the key area of for us in terms of cross compatibility among the products is very important. It's a goal we want to achieve. Which board do you recommend for PX4 flight system? So we can't play favoritism. All 96 boards are important, and so this is hope the last question I'm answering is actually we believe there are many 96 boards could be quite beneficial for different use cases supporting the high performance PX4 flight system. What we have done here is if I can find a board here on my desk. So this is AeroCore 2, which you can find. So this was the first 96 board we have done that will enable. So this is a Dragon Ball 410C, one of the very first 96 board, and this is AeroCore 2. 96 board has PX4 stack on it. What we've done is actually that has been put on a real drone commercial product. So so this is 4 years old product. So exactly same mechanism can plug into the one which we announced last week in the exactly same manner, right? Different silicon from different company. So what I would say is pick your favorite in terms of the price tag, the capability, with if everything goes to plan, the universal pixel mezzanine product we are developing with Dronecode would help to standardize the high performance parts, enable the high performance drones. So thank you, Raymond, thank you everyone.
Thank you, Dr. Yang. Hey guys, your host here, Ramon speaking. Please join me in thanking Dr. Sang from 96 Sports. Doctor, thank you for your endorsement and support. We look forward for that's coming out of our partnership. And
Great.
Talk to you soon.
Yeah, talk to you soon. Thank you. Bye for now.
Wow, thank you. So we're still live. If you are an organization working with the open source projects in our community, the second best way to give back to the community, to the open source world, is to join Dronecode. Dronecode is supporting the open source projects within our community. The first best way to contribute is obviously pull requests, issues, comments, jump on our docs, fix our typos. I want to thank everyone that's been doing amazing work so far. Next up, we got 2 sessions. But before we go there, I want to mention that there's going to be a post-event survey sent out to all the registrants. It's going to be a special surprise there, because if you can participate for a chance to win special prizes by sponsors. Sneak peek, we might have some 96 boards for you for all those members that are participating in the post-event survey. So please let us know if you're interested. Stay tuned. And next up, we got 2 sessions. So first up, we got Andros Goffey on his presentation, Smart Wings, Active Turbulence Suppression for Aircraft. You can find that on the PX4 YouTube channel. It's premiering right now. So make sure you go there, check that out. We also have live here on this channel, Julian Lecourt. He's going to be joining from Lausanne, Switzerland. He's going to present a very innovative and creative use of PX4. I know many of you are looking forward for this one. It's called, is it a drone? Is it a plane? No, it's Jetman. All right, give me a minute while I connect you to Julian. All right, everyone, we're back. Your host Remote here. I'm happy to be here. Day 2 of the PX4 Developer Summit. Next up, we have an interesting session. We have, is it a drone? Is it a plane? No, it's Jetman by Julian Lecourt. He's calling in from Lausanne, Switzerland. He holds a doctorate in robotics from EPFL and currently working as an R&D engineer at Flybotics. He's the science and engineering consultant for Jetman Rossi. Helped the Jetman develop a hover flight stabilization system for jet-powered wing and intuitive pilot wing interfaces on body movements. In this session, he will show how the PX4 ecosystem enabled the world's first VTOL flight with wearable wing capable of a maximum speed of 350 kilometers per hour and a maximum altitude of 5,000 meters. The presentation will focus on both technical and safety aspects of the project and will contain the behind-the-scenes images from test flights. I'm really excited. Please welcome Dr. Julian. Julian, this.
Oh yeah, hello.
You're live.
Everybody. I'm live. Okay. Hello, everybody.
Welcome. Thank you. Go ahead.
That's great pleasure to be here today to present you this project. It was an amazing project. So let me share my screen. All right. So is it a drone? Is it a plane? No, it's Jetman. So this is a project where we have achieved the world first vertical takeoff and landing with a manned aircraft, jet-powered, that is capable of flying almost 400 kilometers an hour and 5,000 meters high. Of course, working on the manned aircraft was very intense, but that was, I think, the best project I've had the opportunity to work on. And on the top of that, Yves Rossi, who has developed the wing, is a wonderful person, and I'm very glad that I've met him. So if you don't know him, here is a short video that describes what he has achieved with his wing.
This next story you have to see to believe. The latest chapter in the amazing adventures of Jetman. This time he's really outdone himself, soaring to new heights even Superman might be envious of. Jetman will soar across Wisconsin later today.
Rossi invited us to come along as he flew beside the C-17 vintage bomber. This is the kind of formation flying you don't usually see.
It looks like he's starting to make his climb. He's out over the channel. There is no turning back now. He is over the English Channel and underway. Ladies and gentlemen, Yves Rossi has landed in England. Yves Rossi.
And why jets? Why not propeller-driven aircraft?
Because I don't want to become a salami.
So if you look up in the sky around the U.S. and think it's a bird, it's a plane, no, it's Jetman, everybody.
All right, so pretty impressive, right? When you've done all this, what do you want to do next? I mean, flying formation flight with aircraft, going in the Grand Canyon, crossing the English Channel. Well, UAVCAN has been dedicated on a journey to feel the flight like a bird would do. Well, we're talking about very specific kind of birds that have jet engines, but yeah, that's the idea. And one missing part is VTOL, vertical takeoff and landing. Right now, a flight looks like this. You go up using a helicopter, and then once you reach a safe altitude, around 1,000 meters above the ground, then the pilot jumps out of the helicopter, then gains speed, and then it can fly and do loops, whatever it wants. At the end of the flight, it has to open a parachute to go down safely. What would be awesome would be to remove the helicopter from the equation. That would reduce the cost tremendously and also make it way cooler. And even better would be to also remove the parachute. So you don't need anymore to be an experienced paraglider to operate the wing. But that's pretty challenging. So what do we do? How do we get there? First thing we need is safety. So you'll see throughout this presentation, safety was always first, and it should be. And up until before this project, UAVCAN was always flying at high altitude because that's where you have the safety of the parachute. If you are higher than 800 meters above the ground, you have the time to open a parachute in case something goes wrong. You even have the time to eject the wing, which will then land with its own parachute and open a second safety parachute. When you go down close to the ground, that's where it's getting really dangerous. So I will say it once, maybe repeat it during the presentation. Do not try this at home unless you really do what you're doing. It's very dangerous to fly close to the ground. And you will see that we have taken all the measures we could to ensure the safety. And PX4 was never the last remaining safety measure. We always had a backup. Right. Second thing we need is power. Obviously, if we want to take off vertically, you need to sustain your weight and even more. For this, we are covered because the wing is now equipped with 4 JetCat engines that each deliver 55 newtons of 55 kilos of thrust. Considering that the weight of the wing plus the pilot plus the fuel is 180 kilos, that means that you have a thrust to weight ratio larger than 1. You can go up vertically at 180 kilometers an hour, which is the speed that you fall down when you do free fall. All right, and last thing you need is control. Here, I'll take a step back and mention something that I haven't yet. There are no flaps on the wing. UAVCAN wants to feel the flight like a bird, and he uses body movement to control the flight. There are no joysticks, no flaps on the wing. In order to roll, he twists the shoulders to go left or right. If he moves the torso forward, it will pitch down, torso back, pitch up, and move the head to do a bit of yaw. And that's it. And actually, there were tests done in the wind tunnel that showed that the wing design should not be stable. However, this particular design was used to cross the English Channel. So that's to tell that having a human on board actually controlling the platform is really something different from what we are used to do with drones that are entirely rigid and robotic platforms. So knowing that, the first trial was made without any stabilization system. And here you can see, all right, now that you've heard the noise, I will mute all the videos. What you can see on this video is that the thrust is controllable manually. There is only a potentiometer in the hand that controls the thrust. And that's enough to control the altitude. However, all of the other axes are not stable enough. On roll and pitch, it drifts very quickly. And on yaw, you have no control at all. So the solution to that is, oops. Yeah. The solution to that is to use a thrust vector system. So thrust vectoring nozzles here in red on the drawing were added in order to deviate the airflow left and right and front and back on 2 of the engines in order to make the flight controllable. Then, as I said before, the idea with this wing is to be as intuitive as possible, to let you control the flight as if you were flying. You should not feel the wing behind your back. And the way we achieved this during hoverflight is the following. The wing here pictured with an airfoil is stabilized in order to stay level, like it is on this picture. And then when the pilot will move its torso forward, it will offset the center of mass forward, which will be considered as a disturbance from the point of view of the controller. Wind gust, body movements are all considered disturbances for the controller. Then, as a reaction, the controller will align the thrust vector with the center of mass so that the platform does not tilt and the wing remains level. But now we have a new stable equilibrium point where we have a forward component of thrust, which means the platform is moving forward. So that makes it very intuitive to fly. You move forward, the platform moves forward. You move backward, the same thing happens. The tilt vector will move and it will move backward. Right, so let's put that in practice. We need a test pilot, and I'll introduce you Chuck. Chuck was the brave first test pilot of the platform. And although he's made of plastic, he is nonetheless a very proud and talented pilot. The test with Chuck allowed to tune roughly a PID controller that was then used on real flight with Yves Rossi on board. So here you can notice a safety harness that limits the movements of the pilot so that it can never touch the walls, both on the top and on the bottom. So we have taken measures so that nothing wrong can happen. Here you can see the wing flying with the stock PID of Pixhawk, PX4. No big change in the code, just some tuning. So one might say that the tuning is not correct. And here I will pause. Whoa, yeah. Just a reminder that things can go wrong very quickly. So it was very important to take the safety measures for that. Yeah. So that's the closest we've been to an incident. It was nothing bad, but we are happy that we have taken safety measures precisely for that type of event. Well, I was saying that some might say that the tuning was not great on this flight, and they're probably right. But the thing is, you have to consider that each flight is only a few minutes, and we can do only 2, 3, or sometimes 4 flights per day because it takes some time to prepare. And it requires up to 5 people to operate, like to have all the safety measures we wanted. So it was very time consuming to tune the controller. So instead, the approach that I've taken was to do some system identification. Here, we are looking at roll and pitch jerk. that were measured from the flight I just showed. So in blue, you have the measured jerk. And in orange, you have the predicted jerk predicted from the actuator movements. You can see that we can have pretty good modeling of the platform. And this was used in model-based control that replaced the PID controller existing in PX4. And here I wanted to show this short video because this was the first test of this new controller. And it was a very nice moment because you can see in his eyes that, well, that's the moment we both knew it would be working, right? He's testing the strength of the controller, and then here, yeah, he knows that it's really strong and that it will work. So that was very exciting. Okay, now that we have something that is able to stabilize the flight, we need to prepare for outdoor flight. So a bit of architecture. In the wing, we have a Pixhawk that has a few custom applications running. The first one is called the JetGuy command. It's basically an application that replaces the commander. We wanted to have as much control as possible on the behavior of the system. And we could not afford the system to switch mode, I don't know, like go to land or disarm without us knowing. So what JetGuy command does is when all the safety checks are passed and the button is pressed, it then forces the system to off-board mode. So it's an off-board mode that is triggered by onboard applications. It's a bit backward, but it's the best way we found to have a good control on the behavior of the system and be sure that it follows our state machine. So speaking about that, I'm very excited about the ongoing work on state machines because it will make PX4 much easier to comprehend and easier to assess what the behavior of the system is. Right now, that was the best solution for us. There is also a JetGuy control, which implements the controller and button that handles the button state. On the left, we can see that we have added a second Pixhawk in the helmet. And this Pixhawk also runs custom apps. One use is to provide information to the pilot through an LED about the state of the system. And the second use is to give commands to the controller, yaw commands and a bit of trimming on the roll and pitch. And on the right side, we have non-critical parts of the system, which is a Raspberry Pi running a web server, exposing the state of the system, and then a smartphone on the ground that is very useful when we set up the system to know that everything is fine, all the estimators are healthy, and all the batteries are charged. Okay, and with all this, here is an example of the kind of flights that we achieved. This was, I think, about a year ago today. So let me fast forward a bit where it takes off. Oh, if I can. No, I can't apparently. No. Well, the point is, it's very, very stable. And according to the pilot, it's very easy to fly. You don't have to do a lot of crazy motion to stabilize the system. You just lean backward and it moves backward. Then you turn the head and it just follows. Move forward and it moves forward. That's apparently very, very easy to fly. All right. Then we prepared for the outdoor experiment. Removing the safety barriers one by one, always being precautious. So the first test was going outdoor with a light breeze and with the upward anchor removed and but the downward wire was kept for safety. Then we did first hops on the boat. So thanks to Sagra for lending us the boat. It was very great. It was a short flight, but it was the first that was completely unfettered. It was very, very exciting. And the whole team was super happy after that. And finally, here is the flight that we've done on the shore, the first vertical takeoff, completely autonomous, no remote, no joystick, only body motion to drive the flight. Okay, great. So what next? At the beginning of the presentation, I promised you that we could remove the helicopter from the equation, take off from the ground, have fun in the air, and then land. We are not quite there. Actually, here I highlight all the zones where we have flown. So very low on the ground, less than 2 meters above the ground. We have flown a bit higher above water, because in case of failure, that's a safe splashdown. We have flown higher than 800 meters, because that's where you have the safety of the parachute. And there we tried forward flight, vertical flight, transitions, both ways, all works great. Eve has also developed a ballistic parachute that allows to open a parachute down to 200 meters altitude. But there, the vertical flight was not tested yet. And what's missing is the blank area you can see between 10 meters and 200 meters. There, we don't have a system to ensure safety yet. And that's somewhere we will not go until we have the safety measures to go there. So if you are a manufacturer of a system that provides safety down to 10 meters, then please contact us. Otherwise, we will not do that for now. And if you see anyone doing it or claiming that it's okay, it's, according to me and to Eve, it's just irresponsible. It's just taking too much risks. Right. To finish the presentation, I would like to show you this short video because I find it wonderful. It was after trials of transition at high altitude. Eve spotted a nice cloud and decided that the test session was over, and he started to climb 4,000 meters altitude and started to play into the clouds, which is very wonderful. Yeah, on that video, I will look at your, I'm sure, many questions, and I thank you for your attention.
Hi, Julian. Can you hear me?
Yeah, I can.
Thank you. Awesome. That was awesome. Let me share some questions from the community with you real quick. Can you do me a favor? Can you share your screen for now?
Yeah, I can.
Yeah.
Yeah.
While we wait for those questions, community, please go to the PX4 Slack channel for the PX4 Dev Summit. I want to invite Julian here in live on stream. He's on the hook now. So, Julian, can you go to the Slack channel and share some of those videos with the community? That would be really cool.
Yep, I'll do.
Awesome.
I'll do. Yeah.
All right, so questions. Thrusters, are they electronic, fuel-based? If so, which fuels?
So the thrusters are fuel-based. These are gas turbines that run on jet fuel. So if the question was about the environmental aspects, yes, it pollutes a lot. It consumes 30 liters in 8-minute flight. So it is gas-based, but the power to weight ratio of these gas turbines is just unbeatable. You have a gas turbine of 5 kilos that produces 55 kilograms of thrust, and it's all contained in a small package. You cannot afford to have large propellers on this platform. So for now, that's the only solution.
Great, thank you. Another question is, what is the reason behind the decision to not have control surfaces?
So that's by design. The goal, according to Yves, was to get out of the cockpit. When you are in a cockpit, you are driven by the aircraft. You move the joystick, and then some mechanics happen. The aircraft moves, and then you follow the aircraft. On this wing, that's the opposite. You are moving, and then the wing follows you. So it's completely different feeling, and that's the goal of the project.
Great, thank you. Okay, so I'm going to leave some of those questions for you to answer on Slack. There's a lot of good, interesting questions, but I think they're better answered by you on Slack asynchronously. Thank you again for being here today.
All right, thank you
for the presentation.
And I look forward for the following presentations. Thank you.
Awesome.
Bye-bye.
Thank you. All right. Hi, your host here, Ramon speaking. Please join me in taking Julian Decor. I'm concerned by Chuck's safety now. We got to check on that safety pilot. And just a quick note before we continue, please, like Julian said, don't try this at home. This is done by professionals. Don't try this at home. That's not why PX4 exists. There's a reason, there's safety embedded into the application. Please be safe at all times. Next, we have two announcements. Okay, let's see. We got a special secret after party. Please, link is going to be shared on Slack. And you can find the speaker slides and videos and everything on Sched. You can also go to Slack, ask the speakers. Everyone's there. You can just go and tag them, ask them any questions you want. We have two sessions coming up. I think right now Andreas Golfi is premiering on YouTube. The next premiere is Paolo Kirienko. He's going to be talking about UAVCAN, uncomplicated application level vehicle communications and networking. I got that right the first time. Good. Pablo is going to be premiering on YouTube soon. Please go there, ask questions. His session, I already seen it. It's really good. You're gonna like that. And then next up on this channel, live with me, next up we got Jaime Martin Loza from Madrid, Spain, and then Nuno Marquez again, repeat speaker, joining us from Lisbon, Portugal. They're going to be talking about bringing MicroROS to the PX4 base flying systems. I can't wait to hear what's coming next for ROS and PX4. I'm excited. Please give me a moment while I connect you to the speakers, and I'll be right back. everyone. Welcome back. Ramon here, Program Manager for Dronecode. Really excited for this next presentation. We got bringing MicroROS to PX4 base flying systems. Let me do a quick intro. Jaime Martin Loza is the CEO of Eprosima. Experts on middleware specialize in implementing middleware standards such as DDS, RTPS, RPC over DDS, CDR. He's calling in today from Madrid, Spain. Jaime, awesome work on all the contributions to the community. Thank you. Nuno Marquez is a PX4 maintainer, directly responsible for the implementation and maintenance of the MicroRTPS bridge in PX4. He's calling in from Lisbon, Portugal. This talk is going to focus on presenting DDS, RTPS, XRCE, DDS, and MicroROS. And we go over on how both MicroROS and the MicroRTPS bridge work and trace an ideal roadmap to migrate from the MicroRTPS bridge to MicroROS in PX4. Welcome our speakers, community.
Yes.
So, hello.
Hi, guys.
Very happy to be here. So, I'm going to share my screen to start because we have very few time. Let me do this. And I'm going to be presenting this agenda with Nuno. We are going to present together. So I am going to present the concepts regarding DDS and MicroROS. And I'm going to be talking a little bit about our company. And right away, Nuno is going to talk about the bridge and how to migrate the current bridge to MicroROS. So let me tell you something about Eprosima. We are, as Ramon was saying, experts on middleware, and we are very focused on DDS and ROS2 because we are the default implementation of the middleware of ROS2. We are also contributing to the standards. We are OMG members, and we are members of the technical steering committee of ROS2 because we are a major ROS2 contributor. And also, we were in the past contributors to PX4 because we developed the initial version of the MicroRTPS bridge, that is a bridge between the MicroRT of PX4 to DDS and ROS2. So we have three main products. Probably you know those products. The first one is Fast DDS, that is the in middleware of ROS2. Also, we have MicroXRC DDS, that is an extension of DDS for microcontrollers, and is the base of MicroROS, ROS2 for microcontrollers. And we also coordinate the MicroROS project. And we have this third product that is important today, the integration service, that allows you to connect DDS with other protocols, such as ROS1, ROS2, or WebSockets, or Orion Context Broker, and user-defined protocols. And it's going to be the base of the ROS integration service, a common project between the Open Robotics Foundation and Eprosima. So let's talk about DDS slightly for those of you that don't know about DDS. So when you are working on DDS, you have to imagine a global data space, and in this global data space, you define topics, and then the different participants or nodes join the global data space and just declare their interest on publishing on or subscribe to those topics. There is no central broker. It's just a pure publish subscribe model. So in this kind of architecture, the latency is very low and the throughput is very high because you have no intermediate steps related to brokers or demos or whatever. As soon as you have the data available in your publishers, the middleware sends the data directly to the subscribers. Also, the discovery is automatic, so it's very easy to use in the typical cases. And this is the same model for ROS2. They have been studying different middleware options, and finally they choose DDS because DDS comes with a lot of success in defense and aerospace and other critical applications, so it's perfect for robotics. So in the case of ROS2, you have the typical layers you have in ROS1, the C++ and Python and Java APIs, and a C API, and then you have the different middleware interfaces that are basically DDS implementations, and the default implementation is fast DDS. So why it is interesting to bring DDS to PX4? Basically because you can connect a lot of different modules of ROS2 or DDS applications into the companion board using this bridge, this current bridge you have called MicroRTPS. Basically, you have all the power of ROS2 and DDS applications within your drone. And then we have these extensions, this extension of DDS that is called XACI DDS as the standard of the ONG, and it stands for Extreme Resource Constrained Environment DDS. And then you have the same model you have in DDS, but you need a special node that is the XACI DDS agent, and the clients that are going to run in the microcontrollers connect to this agent. The client is a very tiny C application, and you have all the power of DDS within your microcontroller. This is not just a bridge, but a proxy. And that means that through remote procedure calls, the client is going to create entities, publishers, subscribers, and topics using the agent that is going to be the proxy. And this is very useful for these use cases, and also for the IoT cases in which you have a low power device that is not connected to the global data space constantly, but you just connect from time to time. So why using this this protocol? As I said, you have the full power of DDS. It's compliant with a standard. We have the first implementation of the standard, but it is natural that in the future it's going to be more. We are going to have more implementations out there. Our default supported platform is NATEX, the same operating system you are using for PX4. This is not a casual event, but we choose NATEX on purpose. And also, we support FreeRTOS and Zephyr, and it is easy to port to other different platforms. So you have also additional features such as fragmentation, services, IPv6 and multiple transports, and others. And last but not least, I'm going to talk a little bit about the integration service. It's basically a common project between Proxima and the Open Robotics, and it's basically a bridge designed for DDS and ROS2. And you have different protocol adapters like a WebSocket, ROS1, ROS2, or in Context Broker, and you can create your own protocol adapter that we call system handler. And let's talk a little bit about MicroROS. MicroROS is something very similar to ROS2, but for microcontrollers. As you can see, there is a one-to-one mapping between the concepts you have in ROS2 for microcontrollers. But we don't use the full DDS, but this XACI DDS extension for microcontrollers. So it's the same idea, and the platforms we support for MicroROS are the same platforms we are supporting for XACI DDS, that is Zephyr, Natex, and FreeRTOS. And well, now Nuno is going to explain how to use this within PX4.
Hi everyone. So I'm going to start sharing my screen. Okay, perfect. So as everyone knows, we already have I would call it PX4 FastRTPS bridge implemented in PX4. It exists since 2017 and was already presented also in the past summit. Just an overall overview of what it does. So you have two components. We have the client and the agents. And the client is associated with the autopilot side, and while the agent is associated with the off-board computer. And following the flow of data, you can, so the idea is that you have a one-to-one conversion or one-to-one mapping between the data that is being published and subscribed in UORB and the data that is being published and subscribed on by DDS participants on a specific DDS domain, which can be, of course, ROS2. And you start by, for example, if you have a new UORB process or a PX4 module process that is publishing new UORB data, the client will basically subscribe to that data, will serialize it, write it to a UART or a UDP link. Well, and in the agent side, that data is going to be read, going to be deserialized, and then FastRTPS or FastDDS will have the work of publishing into a specific DDS domain. The other way around also works. So if you subscribe from data coming from a DDS domain, you serialize it and publish it and write it to a UART or UDP link, and the MicroRTPS client side will read that data, deserialize it, and then publish it as a new UORB topic. Next one is basically, I'm going to quickly give you an overview of how exactly is the bridge working, or how the bridge can actually be generated. So this is basically, if you are aware of the build system of PX4, this is a make target. You use PX4 underscore, the target can be FMUV5 or can even be CIDL, and then underscore RTPS. And in this process, the first part of the process that it verifies all the new UORB, if all the new UORB messages actually have an RTPS identifier. Then it verifies what are the messages or the new UORB topics that are supposed to be sent or published or subscribed from the UART or the serial link or the UDP link. After that, we use specific IDL templates for basically generating all the required code for the publishers and subscribers on the agent side, and we use that with the help of the FastRTPS gen application from Prozima. And at the same time, we are basically generating all the RTPS specific linking code to all the messages that we are going to exchange. Finally, the client code, it's automatically building this build process, but the agent code is stored in a specific build folder that you can manually build by manually triggering it. And it basically builds the agent application, which basically publishes and subscribes from ROS2 and DDS. Optionally, you can, if you don't want to use ROS2, you can directly generate using FastRTPS gen. You can generate a subscriber or a listener application, so you can evaluate the data that is coming from PX4. Then, of course, you have the PX4 ROS2 bridge, and in comparison with what you had on the raw FastRTPS bridge, this one directly connects with ROS2 topics, because we added support in FastRTPS gen to actually directly connect the types being generated on the PX4 side with the types that ROS2 supports. And this basically we are able to do that because we have two different packages. So we have PX4 ROS.com, which basically it's the materialization of the PX4 RTPS bridge for ROS2, and it has the agent code that actually interfaces with the ROS2 side. But it's actually also dependent on a second package, which is called PX4 messages, where we basically have the ROS2 message definitions that correspond to new ORP counterparts. And those are Pascal case naming because it's the ROS convention for message types. And what we do with that, the PX4 message on the PX4 message build is that we generate we do generate the IBL files that are required to generate the code for the agent side using FastRTPS Gen. And at the same time, we're generating the type support and interface code that we do require to use on ROS2 nodes, so we can actually be compliant or have that one-to-one conversion from new ORP topics that are converted to ROS2 message in ROS2 nodes. Since past year, there were several new, there were main features and bug fixes that I want to basically have a look at and show it to you. So the first one is that we had support for ROS2 dashing, Eloquent, and Foxy, and the way we did it was basically by adding that type support conversion on the FastRTPS Gen, and we are able to actually have that one-to-one conversion with ROS2 topics present in dashing, Eloquent, and Foxy. Foxy is actually, or the Foxy support was actually something that happened in the past two weeks. Time synchronization is really important because we have the agent and the client with different timestamps. So we have the timestamp on PX4, we have the timestamping also on the agent side, so on the companion computer, and they usually have different monotonic times, and we want them to be synchronized. And if we exchange data between the agent and the client, we want to be sure that the message timestamping is actually synchronized. At the same time, also the participant and the topic filtering is really, really important because things like publishing data and then subscribe to the same data that we published, it's not ideal. It's not that what we want. So we are also topic filtering on both the agent and the client side. And currently, and this was added like 2 weeks ago, we added support for Proxima FastDDS, but keeping also back support to all the versions since FastRTPS 1.6. And then we arrive, of course, to the new bridge that we are aiming to bring to PX4. And right now we are calling it a MicroDDS bridge. Being it a bridge or not, that's conceptually something that can be discussed because, of course, MicroXRC DDS will serve as a proxy more than just a bridge. But in this case, what we are replacing is what we had with MicroRTPS in the PX4 side, and also on the companion computer side. We now have the MicroXRC DDS client and agent on that side, and we are basically helping or extending the DDS domain into PX4. And although we have this straightforward many-to-many data exchange before also in PX4, right now we are currently able to take the full advantage of what MicroXRC DDS can provide. So this is a protocol from the MG consortium, and this is a specific implementation from Proxima. And what we are bringing is the full capabilities of DDS into the microcontroller. At the same time, the client library is dynamic and it's static memory free, and that means that instead of just the wire protocol, instead of just so if we evaluate the stack, the only memory footprint that is going to be present by adding the client side is because of the stack growth of the different topics that we are using. At the same time, we have this profiles concept where we can actually add or remove functionalities to the library, changing where basically what changes is the binary size. So you change the binary size, also you will be also have more flexibility to different targets that you're actually aiming for. And at the same time, we also have these so-called MicroXRC DDS Gen, which allows you to generate all these serialized and deserialized code which basically use helpers from micro CDR. But before, we were using basically some custom templates. We don't need these custom templates anymore because we just need to generate the respective IDL types or the IDL files, and then this generated code or this generated tool will generate the code that we need. So we come up with the PX4 ROS 2 bridge. And the main difference with respect to the other slide is that now we have a second component here, which is ROS 2. And how are we exactly connecting with ROS 2? We're using something, or we are leveraging something that Jaime talked about, which is the integration service. And what it does allow you, for example, is that you have, for example, a DDS domain running on a companion computer, and you have a separate DDS domain, which is related with ROS 2, for example, running on your laptop. And you can leverage the introspection and tooling from ROS 2 on your laptop while isolating the mic or the drone DDS domain from the other domain. So this allows you to basically have the a low stack or a low footprint DDS implementation running on the drone, because you're not bringing ROS 2 to it. Otherwise, you could do it as well. But at the same time, you are separating the waters here. So you have DDS for the drone, and you have DDS for ROS 2, and the integration service allows you to do that. And it allows you to do another thing. So while before we will be using the ROS 1 bridge to do the bridge between ROS 2 and ROS 1, and of course, in consequence, you'll be bridging ROS 1 with PX4. We don't need this in this case because we can leverage the integration services from Proxima. In specific, we have a system handler for ROS 1 that we can use, and you can directly communicate with PX4 using ROS 1 by the means of the integration service. This also, as Jaime told you, this is not just about the integration service for ROS, but also for other middlewares that can be brought into communication with PX4, like context and message brokers, and even TCP tunneling through one. And now we're up to the last part, which is basically the bring up of MicroROS into PX4. So as MicroROS leverages MicroXRC DDS, what we do in this case is that we bring MicroROS client and agent, as I said, leveraging MicroXRC DDS below it. But at the same time, we're capable of using the ROS 2 client libraries and the functionalities and the API that it's brought from ROS 2, but on the microcontroller, which means that you can, for example, use the ROS 2 API on a PX4 module and, for example, subscribe to data on a new work topic and publish it as ROS 2 topic directly on the microcontroller. About the bridge migration. So we split this into two different phases. The first phase is basically bringing MicroXRC DDS into PX4. So it's basically migrating from MicroRTPS to the MicroDDS proxy or bridge. And the idea is that you need first, of course, to remove the current client templates because they're customized. We don't need those because we can basically use IDL files to generate the code that we need using MicroXRC DDS Gen. We do some code adjustments, of course, that support the integration of MicroXRC DDS, and that include, of course, bringing leveraging the new ORB to IDL type conversions, and at the same time, leveraging what we brought in the last year, which is the time synchronization and filtering. At the same time, on the agent side, we're going to leverage the integration service. So on the PX4 ROS.com package, because we want to have direct integration with ROS 2 by the means of the usage of the integration service. Of course, in the end, this all needs some sort of validation and code and documentation update, and that can be done through the unit test and integration tests, and of course, some example applications where we validate on something that is real. So it can be something as a system monitoring vehicle control, etc. The second phase is bringing MicroROS to PX4. So with MicroXRC DDS in place, we integrate the ROS client libraries, which are brought with the MicroRTPS client. And since there are already support for some ST targets, but not STM32F7, which targets like platforms like the Pixhawk 4, it's important that we make this integration for F7 first, and then not only in the Pixhawk 4, but we can have support for this in a platform like this Altarian Skynode. Of course, other platforms need to be integrated further because we are not just supporting ST targets on PX4. We have other targets that we want to integrate and validate. And as we did the code validation, code modifications for the MicroXRC DDS, we also need to do the same thing for MicroROS and basically leverage the ROS2 API or the client libraries on the PX4 side by using the ROS API inside PX4. And again, some validation needs to be done by means of unit and integration tests and also by example applications. And that's all from our side. We're now free to receive your questions.
Great, thank you guys. Ramon here, can you still hear me?
Yes, I can.
Awesome. So I'm going to share some questions from the community with you. Please read out loud the questions before answering them.
Jaime, do you want to answer the first?
What is the first question? Oh,
so the first question is, why does one need DDS when MAVLink already does a message passing between PX4 and off-port systems? And we're talking about MAVROS in this case, of course, I would assume.
Well, in the case of DDS, you have a protocol that is a multi-purpose protocol that is widely used in a lot of different applications. So in terms of interoperability, for example, in the case of ROS 2 that uses already DDS as the middleware, you're going to have a lot more. And also DDS has a lot of heritage in different data links. So has been used in UAVs, in tactical data links, and well, you can make use of all that history to incorporate that use cases to your own system.
Okay, so there's another question which asks if would we recommend shifting to ROS2 for UAVCAN or UAV applications, or if it is stable yet. So I would say that most of the components of what we're currently supporting in PX4, it's already working. It was validated and it's being validated in different applications, and there are some people already using it. I would say that this jump into MicroXRC DDS will even make the bridge itself and what we're trying to achieve with this PX4 ROS2 bridging, well, it will make it for sure much more stable, and with the security and the performance that we're trying to achieve with the inclusion of DDS. So the other question is, how do you see the future of ROS2 in the UAV industry and its PX4 environment? Do you want to answer to this, Jaime?
Well, you have the different markets for, let's say, professional UAVs in the defense and aerospace markets, and consumer drones. But every day, the line between those markets is disappearing. And I think at least you are going to see a lot of UAV let's say, professional UAVs using DDS in the consumer market and vice versa. So ROS2 is becoming more and more DDS because they are exposing a lot of the DDS capabilities, and the wrapper they have is very, very thin. So what I see is that finally both markets are going to be the same market, probably. And well, ROS2 is going to become a standard de facto also for the PX4 community.
Okay, another question is that is CAN DDS realized in PX4 code base? No, it's not. I don't think it's going to be. And the last question that I have is if there is any plans for MAVROS 2 for PX4 ROS 2. Well, I can answer this. So there's plans for MAVROS 2. There's no plans for MAVROS 2 probably in PX4 because we are leveraging the direct integration with ROS 2 by the means of first, of course, MicroXRC DDS and then ROS 2 because it allows you to do the direct translation from PX4 to ROS 2 without the need of the usage of Mavlink.
Hi guys, thank you.
That's all the questions.
Ramon here. Nuno, thank
Yes,
you
Ramon?
for your time. Thank you, Hyman.
Thank you.
This was really great. I'm Ramon here, your host, speaking. Please join me in thanking Jaime and Nuno. Thank you for your presentation and all the grandiose open source contributions. Tremendous work from both of you to help us where we are here. Thank you, and I'll see you guys on Slack. Bye.
Thank you. Bye.
All right. So, hey, so amazing day so far, right? Thanks for sticking with us today, community. We have lots of recorded talks. We premiered around 7 of those yesterday. There's a few more premiering today, right now. I want to give you a quick reminder. Please join us on Slack. Our community volunteers are doing amazing work to post questions from both chats, Slack, and YouTube. I want to make a quick announcement. For those of you that are not familiar with the PX4 community, how we operate, there's community coordination calls happening weekly. The PX4 Dev call happens on Wednesdays, 8 a.m. Pacific. It goes for an hour and a half. We go through weekly status check-in with all the maintainers, and we also review issues, PRs live for the community. We have a community Q&A session. We try to keep on top of releases, issues, PRs, and everything that's important to our open source community. We also have a call on Tuesdays for hardware coordination. This is where the Pixhawk special interest group meets. That's on Tuesdays. That is at 9 a.m. Pacific. And those are all free calls. They're open. They're inclusive. Join them. There's links by our community volunteers on chat right now. I think they're posting links to all of the information for those calls. We have 2 more sessions coming up. You guys ready? So we have Victor Mayoral Vilches. Let me say that again. Victor Mayoral Vilches. His presentation is called The Cybersecurity Status of PX4. This is a very amazing presentation by Victor. I've already seen it. Please go to the YouTube channel to find him soon. He's going to be there answering questions live. You can find that on the PX4 YouTube channel. I'm sure our volunteers are going to post a link on the chat room soon as well. Don't miss it. It's going to be premiering next. And if you're sticking with me here, with us, with the community, next up we got Ram Grandi from the Netherlands and Deepak Singh from the Delhi on our journey to achieve event-enabled autonomy. And let's hear from them how they're tackling delivery with drones. Give me a minute while I connect you to them. Hey guys, I'm back. We're having minor technical issues with our speakers right now. Let me make sure audio works well, video works well, and I'll be right back with you, okay? Stay tuned. Stand by. All right, community. How are you all doing? Happy to be here. Thank you for sticking with us. Next up, we got Our Journey to Achieve Event-Enabled Autonomy by Breed Digital. They're an autonomous delivery startup based in the Netherlands. They are on a mission to create hassle-free last-mile delivery using drones. Our speaker, Ram Gandhi, is the co-founder and fellow developer at Breed Digital. He's calling in today from the Netherlands. Deepak Singh is a final year undergraduate student majoring in electronics and communication engineering from NSIT College Delhi, currently working as a technical research intern at Breed Digital. On this talk, they will share their learnings and the realization of a forward-looking autonomous drone delivery architecture. Community, please welcome Breed Digital. Oh, mic's all yours, guys.
Hey, welcome everyone. Hello, my name is Ram.
Hey, I'm Deepak.
Let me share my screen a moment. Okay. We hope that you're having a bright day like the slide is going to have. And thank you for your interest for attending this event. And it's really a great pleasure to be speaking at this event. And thank you very much, Dronecode Foundation as well. We have a lot of interesting slides coming up, and we hope to make you stick till the end. It's a great slides and great presentations all around last few days, and we're very impressed with it. And that's why we have something else very interesting as well. I trust we will keep you stay until the end of it. This is what we're going to talk today. How do you enable event-enabled autonomy for your drones? That's us, just in case. We are Breathe Digital. We are a very early stage autonomous delivery startup based in the Netherlands. Our mission is to create using drones. And as you see that we are spread across the globe, and who doesn't like open source? Come on. So we design, build, and also code our drones and the ecosystem around it. And we truly believe that the higher levels of automation across the chain is going to make the drone delivery very affordable. And to just make this happen at Breathe Digital, we have a codename project just for this thing to happen. We want to enable restaurants to deliver flying food. And as you can already imagine, there are so many moving parts involved in delivering stuff with drones. And you got to keep so many systems in hotline. And there is a great deal of autonomy that's needed at every stage in the architecture and your solution. Reality. So what we want at the end of it is really take your hands off and let the system do the magic. So autonomy in and out was very, very important for our dream to make it happen. Why event-enabled autonomy is so important for us, and what the role it's going to play to enable the forward-looking drone delivery architecture. So there are a couple of aspects that we felt in when we started up, and there are some of the things I'm going to list down here. The very first one was the over-the-air updates. So we want to make sure the source code that we change, the code that we do for the drone is really landing on the drone, irrespective of whether the drone is offline or online, because everything is cloud connected these days. And you also want to make sure that's very reliable, secure, blah, blah, blah. At the same time, there are so many moving parts involved in this solution, and we want to make sure the transmission is always reliable over unreliable connections that we all have. And what's also very important is this thing, which most of us are aware of, is it works on my machine syndrome. We want to really avoid that from the ground up. We want to make sure whatever piece of software that we build is truly reliable enough that it runs on the real hardware. And we want to get the testing confidence while we are building our solution from ground up. So what we have for that is simulation on steroids. So I'm going to take you through a slide on that, on how we perceive simulation in our software development lifecycle and how it's really helping us to up the game. And the last or the lead, what I truly believe is that developers are happy when they see their code in action. So it's really our responsibility to make sure the piece of code that's written and the moment it's deployed onto the drones, real or virtual, the end-to-end time should be really short, because the moment you have given that acceleration to these features to reach the target state, the more energy the developers would get. So hopefully they will consume less coffee, who knows? So we believe that the key to the designing such a forward-looking solution is lying in the embracement of your events that are happening across the in or out. Let's dive right in. What is event-enabled autonomy? That's the topic of the day. So what I did was I looked up on the internet to see if I could find a definition that I could use here, but there is nothing like an event-enabled autonomy that's termed or coined so far, and Google Trends across all the history shows me that. So maybe it's time for us to define it. Why not? So let's take a moment to define it so we are all on the same page. So event-enabled autonomy is as simple as achieving autonomy by sourcing events. So by what I mean is, in a plain English, events are nothing but an action or an occurrence that happens. For example, a low battery event, or a mission is in progress event, or a no-fly advisory event. And these kind of events keep happening all around us, either on board, off board, all over. And autonomy is really the capacity to take or make informed decision. And it could be obstacle avoidance, or it could be also emergency landing, and many things like that. So imagine if you could source all these events, off-board, on-board, cloud, whatnot, and the system of interest, and it can do the magic, necessary actions. That's exactly what we would like to term as event-enabled autonomy. So I have a very small example, so let's see it in action. So at a very, very simplistic level, again, as I said, it's a very simplistic level. This is how an event-enabled autonomy would look like. So you see that the events from the drone are coming all the way into the PubSub bridge, which is in the middle. At the same time, there are events that are originating from the cloud that's on the right side. And there are various types of events. It could be like from the drone, for example, you could have a pre-flight check event, successful or failure or whatever. Or it could be also mission progress event, or a health probe event, telemetry event. So what's interesting here is sourcing these events from all around and creating some sort of a hub wherein interested parties can actually tune into this particular to make sure that they react on time. And by doing this approach, what we have achieved is we created a decoupled architecture across all our modules. And by decoupled, what I mean is we got greater flexibility to kind of compose them and create complex workflows without having to worry about making changes to the core components every time that we want to make things different. So how do you create such a system? We have been spending some time on it, and enabling this event-driven approach has been very important for us. So we have made 3 design choices. When we sit back and think through, these are the 3 prominent ones that popped up in our head that we would like to share with you. And hopefully you can make your own impression of mind maps of how you see things in your perspective. The very first one is very interesting. It's a C++ and or Python in our context. So share his findings on this topic. Over to you, Deepak.
Oh, hello, everyone. Thanks a lot, Ram. Hello, everyone. So here we have a demo showing the obstacle detection algorithm in running. So on the left, we have the algorithm written in, like the code written in C++, and on the right, we have the code written in Python. So when it comes to C++ versus Python, C++ has a very clear edge in FPS or in the memory footprint. With C++, we were able to achieve 22 frames per second, whereas with Python, it was only 14 frames per second. And when it comes to memory, as can be seen from the graph, C++ had a lower memory footprint. So in this case, C++ is the clear winner. Let's have a look at the other aspect of things.
Okay, I think Deepak is having some troubles, probably. So when you look at it from a build perspective, what you do with C++ is you actually build the native machine code suitable for the underlying operating system and also the processor instruction set. However, for Python, you actually build the bytecode, which is consumed by the Python interpreter. So with that specific aspect has been a great importance for us, because you actually build once and you can deploy the code Python anywhere. And it is very important, and you will realize it in the next slide by saying it. So in this slide, I assume all of you agree that Python is a winner when it comes to build once and deploy anywhere. So it's a tie, basically. So we want to take you through the reasons why we chose Python over C++ for us. it was really very hard decision for us to kind of switch in the middle of our assignment or mission, that we move all the way from C++ to Python, because naturally we started with C++ for all the low level programming, and we chose Python for doing the high level stuff. It could be integration, orchestrations, and stuff like that. However, we realized that in order to write a reliable software, you need to have a parity between simulation and production situations, environments. And how can you bring the parity is by making sure that you build and you test the same piece of code and same binaries that is deployed on the drone at the end of the day. And in order to reduce or bring in the parity between these two environments, we realized that building native machine code on the real hardware was very challenging when we use C++, given that we cannot have we can have a ceiling when it comes to automation at scale. So there is some level of ceiling that we felt. And with Python, when we moved in, we write once, we push it to a drone without any exclusive compilation steps. And second one was Python being a high level language. It was very faster to develop, and we see the progress that we are making day in, day out. And also the ever-growing third-party libraries. So the MAVSDK Python is a very classic example of it. It's a prime example, and it really enabled us to tap into the PX4 ecosystem via the Python bindings. And it's a very big thanks to all the contributors of the MAVSDK Python, because for let us focus on our position without having to worry too much about the PX4 internals. And the last is really the developer well-being, which I keep coming back because it's very important for us to reduce the time to deploy our changes all the way across the ecosystem that we have. And Python really helped us in that line. Second one is, when would you use edge compute over cloud? And this is also a very classic question that we all get. Is it suitable for edge or it's suitable for cloud? So I tried to list down some of it from our experience in this slide. We see the need to use the power of the edge when it comes down to these three things or even more. The first one is physical connectivity. So if you see the need for sense and respond, sense avoid, or even local connected devices that you want to leverage, then there's absolutely no other choice other than doing this stuff on the edge. Number two is time sensitive. If you have latency sensitive activities like obstacle detection avoidance or even acts of emergency, that's exactly when you will also choose to do things on the edge completely. And the last is privacy sensitive. So you might want to, for a situation like in Europe, for example, we have a GDPR and all privacy regulations, making sure that the vision data and the location data of the things we see and we watch has to be handled very carefully. So probably that's also a reason why we could do things on the edge itself. There are many more other things, like if you want to save some power, you want to avoid a round trip to the internet, probably you want to do it offline. So there are so many aspects like that you could use edge over cloud. So Deepak has a very interesting example to show it over to you. Over to you, Deepak.
Hey,
are you
thanks,
back?
Ram. Yeah.
Yeah.
So hello everyone. Here's a short demo of our obstacle avoidance algorithm. So we use the PX4 SITL and the gazebo simulator for simulating the same. On the left, you can see the gazebo world, and on the right, we have the Q ground control, where, as can be seen, we've planned a mission using the GPS coordinates. Now, the drone is equipped with an RGBD sensor, simulating closely to the hardware that we have, and the drone has to reach that goal location while avoiding these obstacles. So let's see the drone in action. As you can see, it's taking off. Now, using the RGBD sensor, drone creates a local depth map, using which it computes trajectories and the control signals. As you can see, it took a turn around the tree, and now there's another obstacle coming in front, and it will plan a trajectory around this. For doing this, we use the offboard control mode in the PX4 firmware. Yeah. So what happens is, when it encounters an obstacle, it changes mode from mission to offboard. And when there's no obstacle in front, it changes back to mission mode so that it can execute the pre-planned mission safely. So it has reached this waypoint. So yeah, so this is the entire stack. As you can see, we have an RGBD sensor, which basically passes the point cloud to the companion computer, which is running the detect and avoid logic. So it initially checks for obstacles. If there are no obstacles, then it continues the mission. If there's an obstacle, then it changes to offboard mode. It gets the current drone state using the MAVSDK Python API, and it generates the velocity command, which is passed to the Pixhawk using, again, the MAVSDK Python API. Over to you, Ram.
Thank you, Deepak. It's very important to mention to everyone that the moment we chose to switch to Python, and it really helped us greatly, because then we could focus more to compensate the underperformance of Python in its raw form with using NumPy and other libraries. Along with that, we leveraged the asynchronous libraries of Python to make sure that we utilize the OS threading very effectively on the edge to make sure whatever you see on the slide happen at a very low cost and no footprint on the CPU. The next up is really when to cloud over edge. And that's really the last topic that I have today. So there's several advantages of choosing cloud over anything. And primarily it's because it's 24/7 available, it's scalable, and it's secure and so many things. Still, we do see there are very exclusive requirements when to use cloud over the edge. And those are, the first one is reliable transmission over unreliable connectivity. So we know that things are not always connected and there's always a blip in between. So we solve the problem using a very classic PubSub pattern in a store forward mechanism based on the type of the data between the drones and the cloud. And as you can see, the autonomy is in both sides. Even the cloud is autonomous in its own aspect, and the drones are also autonomous in their own cocoon. And we make these two autonomies talk to each other with the help of event streaming across both the sides. And there are, we got to make sure that we design the solution for failure, and which essentially means the command data, the result data, or the over-the-air updates that go in back and forth, all of that, we should not lose it at any given time. So this approach has been, even if the drone has been shut off for say 30 minutes or 1 hour, our over-the-air update has been always waiting for the drone. Whenever it comes back up online, the entire solution software has been overridden on the drone, so it's ready to fly off in the next mission. So the ability for us to push our code updates back to the drone in less than a few seconds is really what is enabling us to move fast. And this loosely coupled design from the ground up is also another important thing to observe, is the way that we can do hand-on and hand-off between these components is very interesting. If we kind of split them up using PubSub mechanism, it enabled us to create complex workflows without having to deal with the individual modules. And the last one I have is a simulation. So how do we do simulation in the complicated world that we have today? So this is a workflow I can show you. On the left side, these the world. So they do the thing. And when they create a feature, then it's basically going to be get drones that we have created on the cloud and also the real drones. So what it happens is that inside the cloud, we have provisioned very high GPU virtual machines, which exactly contains a drone stack, the mock sensors, mock actuators, and we have camera streams and the drone dynamics as well on the cloud. So this really let us make sure we create a synonymous environment very similar to the production situation, right on the cloud, right in the simulation situation. So the dev, just a matter of few seconds, should be able to connect over virtual GL over VNC to it, and they can actually see the encoded, decoded 3D graphics from Gazebo or RViz and stuff. So it really enabled the acceleration at which we can move forward. And it only takes a second to fire up virtual machine on the cloud. So with this approach, what you see, the tooling on the right side is what we use for simulation. We believe that it will enable the developers to push source codes very faster, and the features additions will take them much farther. And we get the testing confidence as well as we move forward. So with that, really completes our talk, and we hope you enjoyed it as much as we do. And last but not the least is, yes, we are hiring. So we are really looking for go-getters, and we promise there is never a day without coding. So come talk to us. Thank you for listening. Over to you, Ramon.
Thank you. Thank you, guys. Great presentation. So we regrettably ran out of time, but Breathe Digital is going to be on Slack. Please join them on Slack if you have any questions. Feel free to ping Deepak or Ram directly there. They're both of them there. Thank you guys again. All right, how are we doing on time here? So I think we've done very good today. Not as many issues as yesterday, which is really good, especially for me and my mental sanity. Thank you for sticking with us. We're still live. Welcome to the PX4 Developer Summit. I'm really happy to be here today. So let's see. We got a lot of pre-recorded talks already premiering. I've seen saying that after each session, but it's for a good reason. There's a lot of good topics going on right now. Please go join the speakers. They're answering live questions while the video is happening. So please join us there. We have 2 more sessions coming up. We got Toon Dang, graduate researcher from the University of Nevada, Reno. His presentation, Autonomous Path Exploration Planning in High-Risk Environments Using Aerial Robotics. You can find that on the PX4 YouTube channel. I'm sure my amazing community volunteers are going to help us on chat and Slack right now. Don't miss it. It's going to be premiering next. And then here in this channel, we got Jonas Walterin, for the MAVSDK maintainer. He's joining us from Lausanne, Switzerland. Jonas works for Autharian, and he's going to be talking to us about extending MAVSDK with new features. That's a great topic. Give me a couple minutes while I connect you to Jonas. Hey everyone, we're back at the PX4 Developer Summit. I'm your host, Ramon Roche. I'm really happy to be here. I have Jonas on the line. Jonas Walterin is calling in from Lausanne, Switzerland. He's the software engineer at Autharian and a MAVSDK maintainer. He's a computer scientist from EPFL and has been involved in creating mission control apps and developer tools since 2014. He's a repeat speaker at the Dev Summit. He spoke at the first one at the ETH Zurich last year. Jonas did a workshop on how to use MapSDK. This session today is going to explain how product definitions and auto generation can be leveraged to extend MapSDK. This is a huge topic, guys. This is one of the main benefits out of the MapSDK. I'm really excited to have you here, Jonas. Please take it away.
Hi, everybody. Thanks for being here and welcome to the Dev Summit. My name is Jonas Vautrin. I am working for Authorian. And in this session, I will be trying to give you a feel of what it takes to extend MAVSDK with new features. Because 20 minutes is so short, I will not be starting from zero and I will go pretty fast. So I'm assuming that you have some familiarity with Mavlink and MAVSDK. And what I will be doing is I selected a feature that I want to implement into MAVSDK, and I will be showing you how I do that. Before I start, I still wanted to go through a quick overview of what MAVSDK is. So at the lowest level, MAVSDK is a C++ library. It has very few dependencies and it's lightweight. And we made it such that we can run it on as many devices as we need, be it companion computers, Android or iOS devices, or whatever ground station we can imagine. Everything that one may need to talk Mavlink to a drone is inside MAVSDK C++. So what that means is that if you want to write a C++ program using MAVSDK, this is all you need, nothing more. Now, if you want to use another language, one of the language bindings we support, it's a bit different. So if we go one level higher, we have MAVSDK server on top of MAVSDK C++, and that guy is there to make the link to the language bindings we have. So MAVSDK server is an executable that uses MAVSDK C++ internally, and that exposes a gRPC interface to the language bindings. I will be focusing on adding a new feature to MAVSDK C++ and showing you how it propagates to MAVSDK Python, but it's the same thing for all of the other language bindings. Actually, most of this is auto-generated. All the language bindings, all of MAVSDK, the header files of MAVSDK C++. So when you want to add a new feature, what you have to do is define it into a proto file, generate the code, and then implement the Mavlink logic here. And that's it for the introduction. So let me directly go into a demo. As I said, I have chosen a feature that I want to implement, and that is not yet into MAVSDK. So that will be this one, do flight termination. What this does is it disarms the drone, and on PX4 it should open a parachute if you have it configured. Okay, so here I've got a terminal, and it's located into my MAVSDK repository. Just to show you, it's a Git, it's the Git repo, MAVSDK repo. So what you need to do if you want to generate code, first you need to be able to compile MAVSDK. So I already did it. So here I'm just running it again, and that's working on my setup. Then the second thing you need is to be able to run the proto file generator. And that's a script we have. So it's in tools and it's called generate from protos. So if I just run that, it's now failing, and that's on purpose because it has one dependency. This dependency is this proto cgen MAVSDK. And so I need to install that. But the good news is that it's available on PyPy. So you can just run pip install it. So let me do that. I like working with Python venv, but you don't have to. I will just be doing it here. And now I can pip install proto cgen MAVSDK. So this is necessary to generate all the plugins, all the code for all the language bindings and everything. Now that I have it, the generation script, it's going through all our proto files. You see the plugins here, action, calibration, camera, and it's generating the code for me. If I look at the git diff, nothing has changed here. I just have my new venv, but that's because I haven't changed the proto files. What I will do now is go into this proto submodule and edit the action proto file, because this feature that I want to add, do flight termination, I will call it terminate, and it's very similar to like arming, taking off, or actually even like kill, which disarms the drone. So I just decide that I will add it here. So the first thing I do is just write some documentation. So terminate will send command to terminate the drone. And then say I just want some definition. So this will run the terminate routine as configured on the drone. E.g., so disarm and open the parachute, something like that. So that's my documentation for this feature I want to add. And then as you see, it's defined in the proto interface definition language. So a function is an RPC here. So I just copy, my function is very similar to kill. I just send the kill command and that's it. So I will imitate a bit that. So I have RPC and I want to call my function terminate. And then all of the functions need a request and a response. So I just terminate request and I return terminate response. Okay, good. Then an easy thing to do is to just like follow another function that's similar. So I've got kill. This terminate request is not implemented yet. So I will follow the kill request and see that here I want to implement the terminate request. Message terminate request. And I do for now exactly the same as kill, and I will comment on it later. Action result, and that's it. Okay, so in the request, that's where I would put parameters if I have some. So here I don't, but for instance, if you look at go to location request, it has 4 parameters, and that will be translated to the different languages. So I'm fine here, I don't want any. And the result is just saying that it could have an error message. It could, like the function could be denied, or I could have a timeout or something. So that's it. I just defined now the API for my new feature. Let me quit. So if I check, I have like the proto submodule has changed, and I can run the auto generation again. It's going through all the plugins, but what's interesting is that it went through action.proto. That one changed. The other ones did not. Once it's done, I can check again, and I see that now like action-related files got generated, modified at least. So it's all good. All those files I will not have to touch. They are all auto-generated files. But the thing is, as I said, I still have to implement the mavlink logic somewhere, right? What I like to do is follow the compiler, right? So I just compile and I see where it crashes, because it has to crash somewhere. And here it says in action.cpp, which was auto-generated just before. It tries to call imp terminate async and imp terminate, and it doesn't find them, of course, because I did not implement them. So the file where they should be implemented is in the implementation of action. Let me go there. So plugin action, and I should have an action imp. Let me go to the header. Same as before, I just go to kill and I look a bit around and I see that, yeah, terminate is something that should be similar. It has a result, an action result. It's called terminate. It doesn't have any parameters, and that's it. And in C++, we have blocking functions and non-blocking functions. This one is the blocking one, but if I look for kill, the other one here is also the non-blocking function, the async one. So I need something similar here. So I just define it. And the compiler error before was actually complaining that it was looking for that. So it has a result as well under a form of a callback this time because it's async, and that's it. So now I solved those errors, but I only edited the header file, right? I need to write the implementation now. Same thing, I want to go close to the other similar feature here. And what I can see is that this is the blocking function And what the blocking function is it creates promise and a future. It runs the async function. It iterates for it. So I can just do exactly the same thing here. So let me just copy it and change the kill function for terminate. Terminate again, and that's it for that. So I just implemented the blocking function of terminate. That was easy. And now I want to go check the async one. And this one is actually the Mavlink logic, right? It's defining a command, it's setting some parameters, a target component ID. So that's the thing I need to implement. So same thing, it's just terminate, it's called terminate async, and it takes a callback. Okay. Now it's a command as well. So I just define my commands. And I need to set what command it is. And so for that, I go back to the documentation and I said, that's this one I want. So let me copy it here. Next step is the parameters of it. So command.params .param1. I know that there is one parameter here. Param is called terminate. And it's activated if bigger than 0, and it has to be 0 or 1. So I need to set it to 1. And there's no other parameter. Fine. So here I just set it to 1. And then the next thing that I need to set is the target component ID. That's necessary for a command. Target. All of this is really Mavlink logic. If you know how Mavlink works, that's just how you would define a message with any Mavlink library. This parent object I use is a helper given to you by MAVSDK. So in this case, it gives me the autopilot ID, which I use as the target component ID. And then if I look at the other one, the last thing is it does is just sending the command async. So I just copy that. That's the same thing. That's my command. Great. So now I implemented terminate and terminate async. And that should be it for compiling, right? Let me try that. Okay, so it's compiled and it installed it now. And if I look at my git diff, I see that this is what I just implemented now, and all the rest got auto-generated. Great. So I prepared a small C++ example. I put a label at the top. So you see it's an IDE. And this example will not be working. It's missing a few things. But what I want to show is the auto-completion there. So it's depending on the MAVSDK I just built and installed. So if I compile it now, I should be able in my action plugin to just do action.term and I get terminate. As you see, I get both the async one and the synchronous one. So that's it. We just implemented a feature that is now available in C++. From the auto generation, we got for free the implementation of MAVSDK server. So that should be it now for the MAVSDK server side. Now, one thing is we have this proto file that we edited. So let me go in the proto repository. And that's the diff we made. Now I will be wanting to propagate that to Python, right? So I need to somehow get it into the Python repo. And the Python repo also has this proto repository as a submodule. So what I need to do is push it. So I prepared already my branch, that's this one. And I will just add terminate for dev summit demo, something like this. And I just push the branch. Okay, so what happens here was not planned. If I look at the remote, I'm on the HTTPS remote. So let me just git remote. update the remote so that I can actually push. Okay, let me do that again. So you don't need to have any special rights. You could just have a fork of the repository, and that would work for you. You don't need to be a maintainer or have any rights there. Let me just go check there. So I just pushed my branch now, and I'm not logged in. Demo. Let me do it here. Demo effect, sorry. So that's what we changed now in the proto repository, just the new function. So what you would do now typically is just add us as reviewer. I can just add Julian and say that's the new function I added in the Dev Summit demo. And if Julian is watching the presentation, maybe he can review it now. But we don't need that, right? So now let me go to another IDE I prepared. This time is for MAVSDK Python. And I have PyCharm here with a small example that's that will create a system, connect to it, and then set the takeoff altitude to 20 meters, arm the drone takeoff, and then wait 10 seconds. And what's missing here is I would like to be able to do a wait drone.action.terminate. But as you see, it's not auto-completed. So if I try to do land, I get the auto-completion with the documentation that we had in the proto file, but I don't have it yet for terminate because I need to generate it. So let's go check this terminal I have. Now, what we have here again, we have the proto submodule. So let me go there. And if I fetch, I should get the, the dev summit terminate. So let me check out into this branch, dev summit terminate. And we have now the commit we just did before for C++. So I can go back, and this time I already installed Proto C Gen MAVSDK as I showed you before, so I can directly run the auto generation script. For Python, it's in other tools and it's called run Proto C. So it's the equivalent to what we have in C++, but now it's generating the Python code for all the plugins. And that's it. I should be able to install it locally. And I can go back to my example here. Theoretically, it should have updated, and now I should be on the latest, on the latest version of MAVSDK. So if I do drone.action.terminate, it now exists. So it was just completely auto-generated, and it appeared in the SDK. Good. I still have a few minutes. The goal was to really show you that it's working, and I hope it does. So let me save that and go to my my environment, my simulator environment. So down there on this shell, I'm inside MAVSDK that we just like built before, and we installed it. So we installed it into build default install, which means that it should be here. So in bin there, I've got MAVSDK server. So I need to run it, and I run it on port gRPC port 50,051 because that's what the Python example we have will be connecting to. So now it's waiting on one side on this port for the MAVSDK Python example to connect, and on the other side it's waiting for a Mavlink drone to connect. So let me start a drone here. It's just like normal gazebo with some model and some world. It should take a few seconds to start. And okay, I should be set up now. So we have a drone here. We have the Pixhawk shell, and we have MAVSDK server waiting for MAVSDK Python to connect. let me just quickly try it. So I come under takeoff to see if my simulator is working. And let me land again. So see that is working now, which means that I can go back to my MAVSDK Python example and run it. So let's just quickly look at it again. It will connect to MAVSDK server running on localhost port 50,051. It will connect to it. It will set the takeoff altitude to 20 meters because we want to see it, fall after the termination. It will arm takeoff, wait 10 seconds so that it has time to take off, and then it will terminate. Okay, let's run that now and go here. So it's taking off, and now it should be waiting for 10 seconds, and at the end it will terminate, and we'll see what happens. Awesome. It just terminated and opened the parachute. And now it's landing. Good. Let me stop this now and go back to my slides. Okay, so that's it for my demo. To conclude, I know that I probably went pretty fast, but I hope you got a feel for what it means to add a new feature into MAVSDK. The main point here is that all you have to do is add a C++ Mavlink implementation and the corresponding proto API, but the rest will be auto-generated for you. So you don't have to know any of the other language. You don't have to know Go to add a feature to MAVSDK, but it will still be propagated to Go. And maybe the last thing I'd like to say is if Julian is watching the presentation, maybe you have a new PR to review. Thank you.
Thank you, Jonas. That was excellent. Thanks a lot for your presentation. Why don't you head to Slack and help our community with a few questions? I think there's a bunch of them for you there. Thank you again.
Yeah.
All right, so following up with our agenda, very ambitious agenda today, guys. Well, let's see, we got, well, before I continue, I just want to make a brief mention. Jonas, I'm a big fan of your fearless attitude towards live demos. I would be freaking out trying to do a live demo on a conference. You are amazing. Thank you for their contributions. So it's me again, your host, Ramon. Really happy to be here. So thank you for sticking with us. We have a quick reminder. There's a 5-minute break after the next speaker. It's going to help me refresh and do some organization and logistics here together with the community volunteers. And then there's also a lot of polls going on Slack. Jump to Slack, let us know who you are, where you're here from, where you're watching from, and if you're looking to be hired or you're looking to hire from the community, please be sure to go to Slack, share your links to your career space, share your LinkedIn profiles, any like your GitHub profile. That's going to be also a great resource. Let us know if there's anything we can do to assist you. And lastly, follow us on social media. Please, please, please help us reach more followers. I think our PX4 YouTube, Facebook account had somewhere around 200 followers. How is that possible, guys? Help us reach more. Okay, so next up we got Julian Kent with an amazing presentation, and he's going to be speaking about automated testing as part of the PX4 development. This is a great and very important topic, so I'm looking very forward to that. Julian Kent is the PX4 avoidance maintainer, and he's a senior engineer at Alterian. He's going to be calling in from Switzerland. Why don't you give me a minute while I connect you to Julian? Hey guys, welcome back to the PX4 Developer Summit. I got your next speaker lined up, and the next presentation is called Automated Testing as Part of the PX4 Development. Our speaker is called Julian Kent. He's calling in from Zurich, Switzerland. He's a senior engineer at Ethereum, where he coordinates the robotics-focused activities, balancing core feature development with supporting Ethereum customer integration work. He also lends his expertise in electronics, software, and hardware design around the company as needed. Jack of all trades. This session motivates the use of automated testing in PX4 of all types and explains which types of testing should be used in what circumstances. Julian will show you how to implement unit and functional testing with G-Test and as a kickoff point for new contributions. Please welcome Julian Kent.
Thanks for the introduction, Ramon. Today we're going to be talking about automated testing as part of PX4 development. Now, I have a quick overview for you. We're going to start with what is automated testing, because of course, this isn't a topic that's familiar to absolutely everyone. Next step is my motivation for automated testing. And to me, this is the most important part. In PX4, we now have the technical parts to get the automated testing working. What we really need is the cultural stuff, and this needs to come from everybody. This is community members, this is core developers, this is OEMs, everybody. So for me, this is really the core part. It's the extra work, yes, but why automate? We're going to go through a few steps of how to do this in practice, and then I'm going to end off with a demo, and hopefully that'll work just like Jonas's one did in the presentation just before. So we'll start with what is automated testing. And while I'm sure most people are familiar with the process of manual testing, that is, you write some code and afterwards you go and you check whether it works. There's actually a lot of stuff here, a lot of different layers of automated testing that you can do to make sure that your code really works and that end users get the best code and that you have the best developer experience. Now, the first one is unit testing, and this is very low level, one function at a time, one class at a time. You check that that has exactly the behavior that you wanted it to have. And this is really for you, for the developer, to make sure that you implemented the thing that you wanted to implement and that your idea is actually captured in the code. The next step is functional testing, and this is a higher level. This is with multiple classes working together. This is maybe passing messages backwards and forwards or one library calling into another. This is to make sure that they work together, that the one library, when it calls into the other, gives it the right type of data or these kinds of things. In PX4, we have UARB messaging, and this is included in the PX4 functional testing libraries. The next is integration testing, and this is usually with a full system. In web development, this would be calling fake servers with your actual data, or putting your data onto a fake server and calling it and checking that it's working. In PX4, this is something like CIDL testing, where you run your whole system in a simulation. And basically, this covers everything except for the specifics of running on the actual hardware target. Then finally, we get to the manual testing, which I think everybody is familiar with. And that is the user, this is in the testing world known as user acceptance testing. And this is where a real human tests it, often on real hardware. And especially for us with drone development, if something goes wrong here, this can end up being quite expensive. If things, you can end up with broken frames. But even if something doesn't go horrifically wrong, this is also expensive because it's taking up users' time every single time something like this needs to be done. So now that you have a brief background of what these different types of testing are that I'll be referring to, let's go for my motivation about why it's so important. So the first step is that development with testing is maybe unintuitively a lot faster. And that is because you get feedback on whether your code works a lot sooner. If you, to go back to the previous example with if your code goes all the way to a user before you know if it works, that can take days to get a response, or months, or something like this. Whereas if an automated test runs, you can have your results in seconds. Now, if this can actually have a big improvement for developers as well from another perspective, in that you haven't forgotten what you're working on and all the very low level details when you get to the automated test, when you get to the results of whether your tests are working. So this means that you have a full, in your mind, every little detail, and when you get that feedback that there's a bug here, or maybe it's not a bug, but maybe it's not doing exactly what you expected it to do, you can have your full mental model is still there, and you get really quick feedback cycles. This makes less bugs get introduced as well during the bug fixing, and it's less development time in total. So the next one is, let's try to split human work and computer work and make computers do work that computers are good at and humans do work that humans are good at. So computers are good at running code, and they're good at comparing outputs. Humans are good at pattern matching, creative thinking, and problem solving. So if you're thinking about checking whether code runs correctly, this is very obviously a computer task. It's you run the code and then you compare the output with the previous time the code ran or with what the specifications were for the code. Whereas for humans, designing the tests is writing specifications and writing code, and this is something that computers are not good at. Next reason for automated testing is that tested code is reusable code. If you have code that is completely untested, or that tests are only done at a very high level, then you cannot reuse the lower components of that code because they'll probably not be architected in a way that allows them to be run in isolation without all of the pieces around them. So if you only have CIDL tests, then this means that you'll probably only be able to reuse your code across different vehicles. And this means taking the entire flight controller as a stack. Whereas if you have unit tests, if you have functional tests, you can take whatever those units or whatever those functions are and pull them into other areas. And this means that you can, and this is entirely due to the way, because the tests point to the code, so you have to have your code architected in a way that multiple things point to it via a well-defined API that your tests actually specify what the behavior is. So this means that the interface of the tests and the interface of the system is very similar, and so this works quite well. A next step is low-risk refactoring. If you have already quite a few tests in your system, then if you refactor and you broke something, probably a test will fail. And this is much quicker to find out than putting it on a vehicle and trying to fly it, and then the vehicle crashes. And then this is more to make the maintainers' lives easier. If you have untested code that is under active development, you end up with more bugs. If you have untested code that is not under active development, this code is hard to maintain because it's probably not specified or documented very well exactly how it should behave. Whereas if it was tested, it would be easy to maintain because the tests say exactly what the code is meant to do. And if you had tested code that's under active development, fewer new bugs. And then when we come to industry outcomes, on the right, I've got here a study from 1985, and I've actually left out a bunch of the different types of testing and design reviews that they've gone through. But they've said that roughly 25% of bugs are caught in unit testing, and they actually said it was between 20% and 50%, and more are caught in functional testing, more are caught in integration testing, and then in-field testing and code review both catch about 50%. However, the cumulative effect of having all of these different layers of testing and review add up to around 99% of bugs. So if you're only doing some of these, you're probably not going to catch as many bugs as you could be. And if then this ties in quite well with here in how many actionable feedback cycles do you get per hour. With a unit test, if something breaks, then you know almost down to the line what is broken. With a functional test, you probably know within 100 lines where the bug is. Integration tests, it could be pretty big. And in-field tests, it could be even hardware that's a problem. You don't know. So, and code review, oh, you can only do 1 or 2 of those an hour, right? So it's really there is a trade-off here between how many bugs you catch and how quickly you can get feedback and how specific that feedback is on exactly the type of bug. And just to give an example of the type of things that high-level or in-field testing might not catch, but a unit test would catch, is something like a controller that is clamping its inputs because the inputs are wrong. And you would never find that out if you didn't have a unit test, and the functional and in-field tests, or the in-field testing and integration tests would probably pass, but you'd have reduced performance. And this is something where the unit testing would give you that better performance, even if technically at the high level it was working, if not very well. So who benefits from unit tests? And I didn't put this on the overview because I wanted to surprise you with it. Everyone benefits from unit tests, and everyone benefits from functional tests. Everyone benefits from integration tests and in-field testing. More testing is better, right up into the point where we stop finding any bugs at all. And I think that's a very, very long ways away for basically all software that you've ever met. So community contributors, they are less likely to introduce new bugs into the software if their code is tested, and the maintainers like that as well, and because they are less likely to have bugs, so they're more likely to review it and merge it quicker. And also this means that your code is less likely to break in the future when changes happen. The core developers, more tests in the code means it's easier to maintain, and the bugs tend to surface before it gets to end users. And this really means that less bug reports, and the developers can deal with the problems themselves instead of having this giant loop around to end users. Manufacturers, you deal with less bug reports from your end users. If you have custom features that need to be developed, they can go quicker. And new airframe bring up, testing new things, putting things on real vehicles, chances are that the bugs already got caught on an earlier level, and so you're not going to have as many crashes, as many fried motors, fried hardware, broken whatever, lost customer trust. And end users, of course, they like less bugs, they like faster bug fixes, and they like more features, because remember, we can do more features in the same time when we have tests. So in practice, how do you make this really, really happen? I'd like to go over a few places here where automated testing 100% makes sense. If you have new code, write unit tests for it, write functional tests for it. Write your tests as specifications. Make sure that your tests explain what your code is meant to do, and then test against that, check that your code is doing the right thing. If you have untested code and you don't know what the quality is like, you don't know how it behaves, write tests for it. You can then find out exactly how it behaves. You can give it any type of input you want, and you can make sure that it does the things you want it to do. If you have code that needs to be debugged because you think there's a bug in this test, in the code, there's a perfect place to write a test. Because often bugs are triggered by edge cases because, well, you don't usually write bugs on things that are working well, or find bugs in things that are working well, so it's going to be in an edge case. And these edge cases are on real vehicles, very difficult to reproduce. Maybe you have to have it at a certain time of day. Maybe you need your GPS to fail at the same time as you're taking off. Maybe you need some other strange combination of things. However, if you have some theory about what's triggering your bug, write a test. Make in your test, trigger that exact use case. If the thing breaks, your theory is correct. You now have a reproducible situation on your computer where the tests are showing exactly where the bug is. Now you can fix your code, and when your tests pass, you know the bug is gone. There are some cases where testing sometimes doesn't work. If you don't know what your code is meant to do, maybe you're trying to explore some new image processing algorithm and you just want it to look cool, but you're not exactly sure how to write what does cool look like, then great, maybe you don't need tests for that. However, you should probably still try to set up a quick feedback loop so you can very quickly get feedback on whether your code is doing what you think it is. Glue code is where you have a bunch of systems and your code just sticks things together. And in this case, putting code together, it can be a lot of pain to set up a test for something like this. I would still recommend having something that you can check that it at least runs and it at least thinks it thinks it knows what it's doing, even if you're not 100% sure. Testing, of course, you're not going to catch every single bug, but you should at least try to catch the easy ones. And the last one is your test code or your build code. Does that need testing? Probably not, unless you have something big that you're trying to do in your testing code, like you're trying to generate a whole bunch of sample data to test your other stuff with. Maybe you want to make sure that you're actually generating the sample data that you think you are. Otherwise, when your other tests start failing, you might be very confused. So zombies, surprise. There were zombies here, and this is actually an acronym. This is to help you remember what kind of tests you need to write. So the first one is 0, no data, null. This is try to test the simplest use case just to make sure that your thing gives you back probably something similar to what you gave it. Don't just set your test up, don't do anything, make sure that there's no surprises. The next thing is 1, just put a little bit of data in, check that it still works. Now you can build your test up to do everything that you think it did, that you want to do. You can add more tests doing all the functionality you want. Boundaries, catch your off by 1 errors. Make sure that you loop through every single element in your array. Make sure that if you specify that something should stop at a certain point, that it stops at exactly that point. Check right before and right after to make sure that it stops at the right time. Interfaces, make sure that your API does the things that it promises, and make sure that you are actually testing what your API promises and not some other functionality that your API isn't actually promising and that is maybe more specific to the implementation than the API. Exceptions, try throwing garbage at your code and see what happens. Make sure it doesn't crash, best case. Like, especially when you're working on high reliability systems like drones, we don't want our code to seg fault, hard fault, whatever it is, and because that can lead to really, really bad outcomes. And then simple at the end. I think they needed an S here, so they added a simple. Just put up something simple and make sure that this works. Often this is the first kind of test that I do after the zeros. So when you're doing your testing, it can often fit into a framework we call behavior-driven development, where you use your test as specification for your code. We set it up with a given, when, then. So given the initial conditions of your code, we do when we do the thing we want to test, then you should get your outputs. And here's a real example, but I'm going to do a demo for you now with an actual real example. So in PX4, there's this function here, and my colleague Roman recently wanted to call it, and I said, oh, that looks like it's got nice inputs and outputs. It can very easily be used for a unit test. So this is going to be what my demo is. This is a waypoint from heading and distance, and this has existed in PX4 at least for 4 years. It hasn't been modified. So let's add a test for it and see how we go. You give it your latitude and longitude start, your bearing in radians, a distance in meters, your latitude target, and your longitude target. So let's copy that. Let's make a new test here. Waypoint from heading and distance. And let's start with our zombie acronym. So let's do 0 as a starting point. So let's start with our behavior-driven development, a given, when, then. 0 distance and ring from a starting point. When we call this, then it should give the input. So let's make a few things. So we have doubles actually. Minus 33, 18, No, these are floats. Okay, so this is our inputs. Now we need to call the function with lat start, long start. Let's see here, we have lat start, long start, bearing, distance, then lat target, long target. So long start, distance, okay. Why is this complaining? Ah, yes, I need to point pointers to these. Okay, now my function is happy. For those of you who are wondering, I'm using kdevelop as an IDE. It works really well with PX4. Then we have expect float equal. Lat start, lat end. Okay, so this is now a test. We've written a test, we've added a test. So let's run the test. We can just do actually, so if you go into ECL, you can do make test. And there, our test passed. Let's just make sure that it's actually working. Let's add a, you know what, let's make the distance minus 1,000 and check that our test fails. Oh, yes, it looks like our test fails. So let's go and see what it said. It said minus 33, and but it should have, but what it actually gave us at lat end is minus 32.99. Now, I put minus 1,000, and the bearing is 0. You would think that if I gave minus 1,000, the latitude would go further negative, not go north. So that's a bit of a surprise there. If I do plus 1,000, do I get the same result? Yes, I get the same result. So now this is something that I would say is unexpected behavior from the test. And let's actually call this distance is negative. Now, this is actually something that I think we should fix. So if it's saying minus 1,000 and you're having a bearing of 0, that should mean it should go south, if not go north. So let's see what actually is happening inside of this function. There's the offender. It's taking the absolute value of the distance. That doesn't make much sense for this standard 2D projection type of function. So let's take that out. I'll check afterwards to make sure that it's not being used anywhere that's expecting that negative distance to be positive. But still, this is something that I think is unexpected behavior. And if it doesn't hurt somebody now, it might hurt somebody in the future. So now if we go back here and run the test again, now we get a more negative number when we did minus 1,000, which is exactly what we expected. So I will go back and figure out the exact transforms to get this into the correct values. But now you've seen how to make a test, how to write a test. And if you're doing it anywhere else in PX4, this is basically the same process. You will go in, you will write tests according to exactly the G-test, and there are also there's also in the user guide a fairly extensive way, and there are also examples that are there. Yeah, so questions? the questions. So the first question is, do I have experience on using TDD in these type of platforms? Yes. I prefer behavior-driven development instead of TDD, but it would test TDD as test-driven development. I feel like test-driven development sometimes deviates a little bit from where from what the actual value is for the code that you're providing, and instead focus a bit too much on providing value to the tests instead of the code, which is why I like behavior-driven development, because you're doing it. But yes, I think behavior-driven development on these types of systems is very valuable, because you end up with something that is well specified, that you know exactly what it's meant to do. Do we have a system tracing standard? There is some stuff. I know that you can output stack trace or stack pointers on there's a high-speed bus, and this is definitely available on V5X. I'm not sure about others yet, and this can be used for profiling. And yes, however, I think for a lot of the development, a lot of at least business logic, things that don't involve drivers and things that don't involve actual hardware-based performance tests, where you're more interested in relative performance rather than absolute performance, I think a lot of it can be done on your laptop, cross-compiled, and not have to go through a difficult debugging cycle and special IDEs that can connect over JTAG and things like this. Yes, and any more questions, you can find me on Slack. I will be there to answer anything else you want to know. And I hope to see more tests in the future.
Julian, thank you so much. Let's quickly change to my screen right here. Hey, thank you so much. Really like your quote, tested code is reusable code. That's a great quote. And what about zombies? Like, that is really fun. Thank you for sharing all of these workflows with the community and share your perspective from my co-maintainer. It's different, obviously, from trying to come in from an external dependency into PX4. And as a PX4 maintainer, we care for different things, and we want to enable the community. So thanks again for all of that. And I agree, everyone benefits from more testing. So looking forward for more collaboration from the community in this topic. Next up, we got a 5-minute break. There's going to be lots of polls and good stuff going on Slack, thanks to our community volunteers. Afterwards, we have 2 sessions. We have one pre-recorded, one of my favorites for today. I'd probably said this a lot already, but the Amador UAV high school team, amazing stuff going on in there. Please go and see their presentation. It's called PX4, an autonomous drone competition, an octocopter, and a bunch of high schoolers. What could go wrong? Turns out some things did go wrong, not all of them, but I'm not going to spoil it for you. Please go and check it out. Amador UAV team, thank you. Mary, Kay, Callian, Vincent, Justin, Sanjay, you're doing amazing work. Thank you. And then on this channel, we got control allocation. We're working the PX4 mixing system by Sylvain Führer, PX4 fixed wing and VTOL maintainer. He's going to be calling in from Zurich, Switzerland, and Julien Lecour again, calling in from Lausanne. This is going to be a deep dive, guys, the PX4 mixing system. So let's join Sylvain and Julien after the break, and let's see if they can give us a quick tour under the hood of PX4. Please don't go anywhere. I'll be right back. There's going to be a 5-minute break. Hello, welcome back to the PX4 Developer Summit, guys. Few audio issues here. We're live. Thank you for bearing with us. Thank you for sticking with us. Please let us know if there's anything that we can do to make this experience better. For now, let me introduce our next speakers. Control allocation, reworking the PX4 mixing system. We welcome back Julien Lecourt-Colony from Lausanne, Switzerland, the engineer behind Jetman. We just saw him live earlier today. And joining him, we have Sylvain Führer, flight control engineer at Autharian. Sylvain's focus is on fixed wing and Beetle vehicles. In the PX4 stack, the output of the controllers is converted into actuator commands by mixers. Although very powerful insiders, the current mixing system is not user-friendly and is limited to static configurations. In this session, you will learn about the ongoing work on control allocation, which aims at complementing or even replacing the current mixing system. The future control allocation module promises easier and more flexible airframe configuration while enabling new features such as the continuous control of tilt rotor transitions and the handling of actuator failures. Community, let's welcome Sylvain and Julien.
Okay, Julien.
Okay, hello everybody, welcome back. I'm glad to start this second presentation of the day for me. It will be about control allocation, which is a work in progress that aims at improving the mixing system in PX4 so that we can do very interesting stuff like enabling handling of motor failures, actual control of tilt rotors during transitions, and all sorts of things. So I am Julien Lecoeur. I'm an R&D engineer at Fibertix, and I will be co-presenting with Sylvain. Sylvain, can you say a few words about you?
Yeah, hi everybody. I'm Sylvain Führer. I work at Autharian as an engineer with focus on Beetle and fixed wing vehicles.
Right, great. So PX4 can be used on many sorts of platforms. You can use it to control multi-rotors with various shapes. Here are a few examples: hexacopters, tricopters, quadcopters with non-squared rotors, etc. You can also control fixed wing aircrafts, VTOL, could be tail-seaters or tilt rotors. During my PhD, I also worked on platforms with tilted propellers that are capable of producing thrust laterally. And this is when I got interested into the problem of control allocation. Then, if you were connected earlier today, you could see a presentation on the Jetman project that uses thrust vectoring. So that's also an interesting control allocation problem because you have a nonlinear mapping between your actuator output and in the actual effect on the system. And yeah, right now I'm working at the Flybotics, where we have an innovative actuation system that is sort of midway between a multicopter and a helicopter, and that there are also interesting aspects of control allocation. So how is it possible? Here we see a slide with a lot of things to pass, but basically this is an overview of the control, estimation, and actuation of a drone, sort of what is implemented in PX4. And what I would like to focus on is what comes into the actuators on the right, called U. And this then is provided by a block called control allocation. This is what will be the focus of this talk. You have this control allocation block, which abstracts away the specificities of the airframe, be it multi-rotor, fixed wing, or something else, from the controller, which means we can run basically the same controllers for many types of platform. So what is control allocation? If you have U, the actuator commands, these are the PVM set points that you send to your ESCs, or could be something else. Then we can define G as the actuator effectiveness, which is a function that for a given actuator command, then computes what are the torques, moments, and thrust generated by the system. And then the control allocation problem is about finding the correct correct actuator commands that match the moment and thrust set points that are computed by the controllers. How do we do today? Today, we are using static mixing tables. Here, I give an example for a quadcopter. We have B, which is a matrix composed of +1s and -1s that converts the desired torques on X, Y, Z and thrusts on Z into actuator commands. Actually, you could, for this particular example, fill the matrix by hand. You put +1s when an actuator has a positive impact on one axis and -1 when it has a negative impact. But in reality, that's not how you should do, because it's very easy to do it incorrectly and to introduce coupling between the axes. For instance, on an hexacopter, if you use that technique, then it wouldn't work at all. So in fact, when you configure an airframe on PX4, you will use an airframe script. Here, I give an example for the vehicle, which will load a specific mixer. And then this mixer corresponds to a few files, which are now listed on the screen. So you have first the mixer file. Click, please. Yeah, thank you. The mixer file, which is actually defined with a geometry file, which is used to compute the static mixing tables and generate a CPP file during the compile time. That is a lot of boilerplate, and we think that we could get rid of most of these files and have configuration of airframe based only on parameters. The mixer table generation goes as follows. You have a description of the geometry of the multicopter or the drone in general, and then using an actuator model, you build an effectiveness matrix that you can then invert in order to obtain the mixer matrix. This is now done by a Python script at compile time, but now we have an implementation of pseudo-inverse in the matrix library that is now merged and available. So we started to build a dynamic version of the mixer, which is the control allocation module. Yeah. So here we have the current pipeline, control pipeline, from the vehicle rate set point that goes into the multicopter rate control, and then generate actuator controls that are basically the thrust and torque set points I was mentioning before, except they don't have units, they are normalized. This goes into a multicopter mixer that uses the pre-computed tables I was mentioning before, and finally out to the actual devices. What we suggest is to have a second pipeline where we have an angular velocity controller that is more or less the same as the multicopter rate control, except that it has gains with physical units. It is aware of the mass and the inertia of the platform, and it can thus generate torque and thrust set points that have the correct units. Then we have the control allocator module, which implements the pseudo-inverse and is able to dynamically update the table if needed. We will see that later. And at the end, this is piped in the existing mixer system with a new direct mixer in order to be compatible with the current system. Okay, a bit more information on the control allocator. This is a class diagram of the control allocator. On top, you have the main class. And what's important to see is that it uses two service classes. One inherits the control allocation class interface, which is basically what method you use to allocate your output. And on the right side, you have the actuator effectiveness interface that provides the effectiveness matrix. So we have, for example, in the center, the actuator effectiveness multi-rotor implementation that lets you configure your multi-rotor geometry with parameters and provides the effectiveness. What's important to note here is that if you have a very specific platform that cannot be described with the implementations we provide, then you can easily add an implementation of actuator effectiveness. If you have, same way, if you have a very specific and fancy allocation method, then you can implement it yourself quite easily. Right. Now that we have seen the way this is implemented, I will hand it over to Sylvain, who will show a few real-world tests and demonstrate the advantages of this new control allocation module.
Yes, exactly. Thanks a lot, Julien. Cover, as you mentioned, of concrete use cases where actually this new allocation architecture to we have at the moment in PX4. First example, I will go with a hexacopter. Actually, I could go with multi-rotor for this example, but that has more than 4 actuators. But here with a hexacopter, and I assume that this is the first time I configure a hexacopter in PX4, so that we don't have any special mixer in place for it. And in that case, what we need to do is we need to measure the vehicle for weight and inertia and give it the type. And then we need to define or set some specific parameters for all the motors, which is basically the thrust coefficient, the drag coefficient, the distance of the motor to the CG, as well as the tilt of the motor. So these are all parameters that you either can measure or you can find out via modeling. But the good thing is also that if you don't know them precisely, it's also fine if you leave some values at default. Then you just need to put in a bit more work in tuning. Otherwise, tuning is usually pretty easy if the model is correct. So what then the algorithm does, it computes this effectiveness matrix, G, which then, as Julien explained in his talk, can be inverted with a pseudo-inverse. And then, of course, we can solve for the actuator set points. In this case, these 6 actuators. So this is a static mix that we already have now in PX4, but I will show you now an example of something that we can't do with the current system. And this is actually exploiting the case that the hexacopter is over-actuated, so it has more motors than it needs to control its attitude of the 3 moments as well as the thrust. And that means that, so if you here go into more detail into this matrix, you have these 6 columns indicating or reflecting the effect of these 6 actuators to the moment as well as to the thrust force. And you have, as I mentioned before, you need to control 4 set points, the 3 moments as well as the thrust in Z direction. And you have 6 available actuator settings. That means it's over-actuated. Now, actually, we can use this over-actuation to control the vehicle in case of a motor failure. So in this example, I assume that I know immediately that a motor, in this case number 2, has failed. And then, of course, the whole effect of this motor to the moment as well to the thrust is 0. So we know that, and we can recompute the effectiveness matrix and then end up with a 4-column matrix, which is still fine for the control of a multi-rotor. Enough talking. I think some video show you more how it performs. So here in this task, I have on the left side a motor failure with the new dynamic allocation, and on the right side, it's a test with the current static allocation. And I fly in position mode, and let's see what happens when the motor fails. So in the first case here, the failure happens at this time. And you see, if you look closely, that this motor here has stopped working. So it's at 0 RPMs. And the vehicle still keeps its position quite nice. And you didn't see too much of movement, actually, when the failure happened. Compared to that, with the current static allocation in place, you then have the failure, you see an immediate response of the vehicle. And it then manages to stabilize itself as the integrators fill up, but you also see that it's not as nice as before, and I had really hard times controlling it and preventing it from flying away, and also the dynamics of the whole system have changed because these integrators introduce a lot of error and different dynamics than before. So I'm just about to be able to land it. Whereas with the dynamic allocation, I almost feel no difference, so I can move the drone left, right, forward, and backward. So the effectiveness matrix is recalculated to account for this motor that switched off, and the remaining control loops control it almost the same as before. All right, now for another example, which is the tilt rotor VTOL. A tilt rotor VTOL is a fixed-wing vehicle that uses the motors pointed vertically to take off and land, but then in cruise flight, it tilts them forward to accelerate. So it's a system with a total of 7 actuators, and for the allocation, we need to model the moments and forces from the actuators to the system. And we do this in this example with a pretty rough model that still leads to this quite complicated formulations. And if you try to fit this into a matrix as before on the hexacopter example, you'll see that this doesn't end up well, because you have here this cosine and sine terms in it, and also some actuator settings in coupling terms in other parts of the matrix. So this isn't for sure not linear, and thus also not invertible. So what we do here to have the system still controllable is that we calculate first some trim conditions of the motors and the tilt motors to allocate the desired forces in vertical and horizontal direction. And with these actuator trim settings, then we can linearize the effectiveness matrix. And from there on, it's then the same story as before with the hexacopter. We can invert this and solve for the actuator settings. In real flight, it looks then like this. So here I tilt the propellers of the VTOL forwards to accelerate. And it keeps on recalculating the effectiveness matrix depending on this tilt. And this leads to a very nice and smooth flight in this like transition mode or hybrid mode, where the vehicle is actually still in rotor mode, but it also picks up airspeed and thus it's in between fixed wing and multi-copter flight. And here's an onboard view. The motor is tilted forward to accelerate, as well as to control the yaw of the vehicle. And all the time, the effectiveness matrix is recalculated. Okay, so the current state of the whole integration into PX4 is that there's a PR open since quite a while now that's has got quite a bit of testing now, especially in the last couple of weeks. So here on the right side, you see all the vehicles that I personally tested it with. So it's a quadcopter, hexacopter, a fixed-wing vehicle and 2 VTOLs, a tilt rotor, as well as a tail sitter. But the state is that it's different for some vehicles than for others. For example, for multi-rotors, it's quite advanced. So there it's really, the interface is there that you set all the vehicle settings, geometries in the parameters, and you can basically add any motor anywhere. For the other vehicles, it's up to now a quite manual process. You need to add your effectiveness matrix yourself, and then of course recompile. But once you have that, you also see clear benefits compared to the static mixer that we currently have in PX4. You can check out the PR for more information about the current state. And of course, we welcome any contribution, be it review or coding, or of course also test flying, to really improve this and bring it in soon. So conclusion for our talk about this new control allocation architecture. Let me first point out the new ease of configuring that we would offer with this allocation. So instead of having the static airframe configs and mixers that you need to actually change in code to have a new vehicle, you can now do this via parameters. And this extends also the possible ways or the possible airframes that we can support with PX4, as we have no limits anymore. We can add any kind of actuation that you can come up with. Then I've also showed in the couple of videos that I showed that it increases the performance as well as the robustness of the whole flight controls system. As for example, for hexacopter, it added robustness with providing fault-tolerant control. And for a tilt rotor, the example was that there you have smoother transitions, smoother forward flight while still being in multi-copter flight and exploiting all the actuators that you have in this state. Last but not least, as this is a dev summit, especially for all developers out there, with this new architecture, we add a way of simplifying the current control structure, especially for VTOL. You have at the moment separate modules for multi-copter and for fixed wing running, which then get fused together to make something flyable. But with this new allocation in place, we could have a singular attitude as well as array controller that then also gets allocated in one allocator to all the actuators you have, being it flaps or motors or whatever. Yes, that's it from my side. So curious for your questions.
Awesome, thank you guys. We're gonna load questions on Sylvan's screen right now. We're about to load the questions there. And if we can make it happen, I'm going to... All right, so it sounds like we're having some technical difficulties with questions. So let me do this. Why don't we get Sylvan and Julian on the PX4 Slack channel for the Dev Summit, and we can ask all of the questions we want their community. They're going to be there and be able to help us with those. Hey, I'm here. Hi. So let me just, I have some technical difficulties here. Bear with me. I'm live and I'm new to this live streaming world. It's complicated. It's way harder than we initially thought it would be. But thank you for sticking with us. We're having a great time here. Thank you, Julian, Sylvan. Thank you so much. The future of mixing system looks really promising. Thanks for all your amazing contributions you're doing to open source. I'll catch up with you next on Slack and community. If you want to follow this up on GitHub, make sure you go to Slack and find their profiles. There's links to their GitHub profiles there. Follow them on GitHub as well. And you can also catch them on the PX4 weekly dev calls happening every Wednesday at 8 a.m. They're a regular attendee to those calls. So in the agenda for today, right now it's 12:42. We have pre-recorded session premiering at 12:45 in 3 minutes by Amateur UAVs. Please check that out. It's going to be really cool. But next up on this channel, we got getting started using UAVCAN V1 with PX4 on NXP's UAVCAN board by Peter van der Werk. He's going to be calling in from Eindhoven, Netherlands. He was a speaker at the panel this morning, so I'm going to welcome back Peter. There was a pre-recorded session earlier today by Pavel Kurenko. He's the UAVCAN maintainer. This is a follow-up of that presentation, and he will be covering the actual hardware development kits for the implementation. So this is going to be really important. So let's hear from Peter on the latest developments from NXP. They're deeply involved with PX4 and the UAVCAN community, so I'm really excited for this. Community, please stand by while I connect you to our next speaker. community, we're back at the PX4 Developer Summit. Thanks for sticking with us. Next up, we got our next speaker. He's already lined up and ready for you. Peter van der Berg is going to be speaking about getting started with UAVCAN V1 with PX4 and NXP UAVCAN board. He's going to introduce us to the NXP RTD drone UAVCAN S32K146 reference board running PX4 and UAVCAN version 1. We'll talk about S30K MCU and its references. CAN Bus, CAN FD, NUTX, PX4, and of course UAVCAN V1. NXP doesn't make drones; they make reference designs with using their silicon. So let's hear it from NXP community. Let's welcome Peter.
For the introduction, welcome to the Getting Started guide with using UAVCAN V1 with the PX4 and the NXP UAVCAN board. So first, a small introduction to NXP. We make silicon for automotive industries, industrial, mobile, smart home, and infrastructure. So this presentation is about our automotive line, and inside this automotive line, we have the mobile robotics line for small rovers and for small drones. And in that team, we make reference designs for drone solutions. So let's start with the UAVCAN S30K146. So the S30K146 is an ARM Cortex M4 MCU having two CAN connectors supporting CAN and CAN FD. And we incorporated the Pixhawk connector standard into our board, so people can connect it to the FMU using the standard GST-GH connectors. And on the other side of our board, we have different peripherals. So we have UART, SPI, LEDs, and we even have a secure element which supports a NFC interface for key exchange. So the typical use cases of this reference design board is that we can convert GPS data into CAN bus, or make a servo or motor controller using this platform, or having other SPI or I2C peripherals we can convert. And this is based on our automotive S30K platform. So this is the block diagram of our board. So we have our MCU, we have two CAN PHYs, which can be used for a redundant connection. Then we have a UART port people can use to set up UART peripherals or SPI or I2C. Our SA050 is our secure element. On that we can connect a NFC call and use NFC products with that. And our board can be powered using the CAN connector, or we can connect it directly through 5-volt. So this is just another picture. So we have all the pinouts available. So it's very versatile to start prototyping to make a UAVCAN solution. So the software support for the UAVCAN S30K board is we support NUTX RTOS, and on top of that we can run PX4 autopilot firmware. So that's the main talk we're going to have here today. We also support the UAVCAN directly through a bare metal, if people are interested in that. And with the board, we have our S30K Design Studio. And with that, also we have an SDK if people want to play around with drivers, or there is a possibility for a free RTOS solution. As last, we also have a SL CAN interface for PC debugging. So we can also hook up our reference design board to a PC, so we can debug the CAN data. So this is the kit we sell. So we have a reference kit with two S32K boards, so you can communicate with each other. We have a terminator board, and we have a DCD-LG debug adapter, which can be used to program, and also has a serial console for the shell debugging or J-Link debugging for GDB debugging. So first, let's start, because we have a kit, we have two boards. So the second board we can use as a SL CAN node, And this allows us to observe and debug the CAN bus in Linux. And we can use the typical CAN-utils CAN-dump utilities to see the raw data. But this also opens up the possibility to use Pi UAVCAN, which is the UAVCAN implementation in Python. So you can already test some interactions through that. And in the future, you can also use the UCAN UAVCAN V1 tooling. Fortunately, it's still work in progress, so please check out their GitHub for the latest status of that. And using SLCAN is pretty simple. So on your Linux machine, you install the CAN-utils package, you set up a daemon, and you have a SLCAN interface, and you can easily just dump the data so you can see what's happening on the CAN bus. But now let's start with the UAVCAN 1 basics. We want to plot out it into an OC model. So on the bottom layer, we have our physical CAN bus, which has just CAN frames. We have a CAN ID and we have CAN data. And UAVCAN takes care of the network and transport. So it takes care on how addressing is done. It takes care of the transport of multiple packages and on how to combine them together. And it has a presentation layer through their DSTL layer. I don't want to go super into deep to this, and this afternoon Pavel is also having a presentation about the inner workings of UAVCAN, so I would glad you remind to check that out. So to implement UAVCAN V1 on our reference design board, we use the reference UAVCAN V1 transport implementation in C, created by the UAVCAN development team. So this is implemented on top of CAN bus and takes care of the UAVCAN V1 protocol. So we have support for both classical CAN and CAN FD. We have redundant transport, and it's extremely resource constrained when it comes to coding. It's very small. It's not a very complex protocol, so you can also check it out here. And on top of that, because UAVCAN is just a transport layer, we've been working together with Pixhawk on the DS15 standard, which is the open standard for drones we're working on, to think about the messaging on top of it. Where UAVCAN V1 is just a transport layer, not all the mechanisms are precisely described. So on how addressing is done, how communication is done, how setup is done, security we also want to handle, and we want to have a general system for health and introspection. So a defined way to do that, and also on how to deal with bootloading. So the goal is here to create a plug and play experience for UAVCAN V1. So we're working on specific avionics profiles for UAVCAN V1. So how does the PX4 setup works with this reference design? So on the left, we have our Pixhawk FMU running PX4 autopilot. We have our MUORP middleware to do inter-process communication. We have the full stack running. So this is being integrated into the Pixhawk FMU. But what we do with our reference platform is that we also run PX4, leveraging all the existing software there. So what we do is we run the same UAVCAN V1 stack, the same DS15 message stack, and we convert that to MUORP. And then the user can just make a very simple custom application just utilizing the MUORP protocol middleware as documented on the PX4 dev page. And this takes care of all the UAVCAN stuff that's running beneath. So here we're going to show an example on how to do that. So we just start with our debug interface. So this is our DC-DLC interface. We can plug it into our debug board, and to our machine we have a USB serial console and a G-Link JTAG debugger. So first we have to clone, to flash this board, we have to clone the PX4 firmware. And then we have to set up our toolchain. This is just easily done by setting up, executing this setup script, or otherwise the Git book goes further if you are stuck in that. Sometimes this can be a bit hard. Then we check out our work in progress branch for our UAVCAN stack software, and we can just easily build this project. When it's has been successfully compiled, we can just easily flash it to the UAVCAN board using these commands. And when it's flashed, we can just easily connect to our UAVCAN board. When we connect to it, we get our NuttX shell, and in this example, we're just gonna utilize existing software. So what we do here is we use the GPS daemon, which is already available in PX4. And for now, we run it in fake mode, so we create fake data, and we're gonna start the UAVCAN V1 converter software. Some remarks. So right now we run it in fake mode, but you're free to connect a real GPS to the UART pins, and this daemon takes care of the location. And PX4 parses this data, and we convert that. And for the sake of this demo, the DS15 is still a work in progress, and in the future we're going to support, of course, the GPS messages. But for now, we're using a non-defined set for that. So this is the demo for the GPS. So on the left, we have a Q ground control session running on an FMU. And on the right, we have the UAVCAN reference design board. Okay. Video is not working, but I'm just going to talk you through this. So what pretty much is happening if we start the UAVCAN software on our FMU, and if we start it on our UAVCAN reference design board, as shown in the previous slide, UAVCAN takes care of it. So right now we don't see that there is a lock, and if this video was working, then there was a showcase that we get valid GPS data to our FMU through UAVCAN. So that's the power there. It's easy to set up, and we have all the tools from the PX4 ecosystem. And wow, okay, I did something wrong. So this is the video. So on the left side, we setting up UAVCAN. On the right side, we start a GPS daemon, and we start the CAN node. And now we're converting it to MURP, and here receiving the data. And we see here on the left is showcasing that we now have a GPS fix. And this is an example on how a GPS fix, for instance, can be communicated over UAVCAN. But thanks to the DS15 set, we can extend it to multiple different applications. So that was the talk about UAVCAN on PX4, but we also have implemented UAVCAN directly on a other project we've been working on. So this is a reference design for a battery management system. And we initially prototyped the UAVCAN on our UAVCAN S32K 146. And we could easily port this to the NuttX running on this battery management system. And we have implemented the base set of DS15 with the BMS message profile. And what you see on the right is a simple example of that. So what we see here in comparison to PX4 is that we already had an application, and it's very easy to integrate libcanard and DS15 on top of that. And so we implement the BMS message profile there. So an example on how we have implemented is available on this GitHub page, but we're working on to be able to release the source code of this BMS completely, so people can use this reference platform and learn on how to implement UAVCAN. So some conclusions. PX4 with UAVCAN is a very easy solution to get started with UAVCAN, and we can reuse a lot of things from the PX4 ecosystems. For instance, the GPS parser, or for instance, gyro drivers, because it's already in there. People can also look if they want to go to resource constraint or make a very competitive solution to Nodex or even FreeRTOS and bare metal. They are very low print alternatives. So especially the footprint becomes small, but then it's a trade-off when it comes to driver support, especially in bare metal. A user has to work everything out by itself, whereas if someone decides to use PX4, there's a huge ecosystem and huge community behind it to make it easier. But that's the scalability what a user could choose for. So, for instance, the STRK platform itself, it's very scalable. So we have a Cortex M0, which is only 128 kilobytes, which can be a very small, cheap package where you can enable UAVCAN on a small product. But we also have a very complex and fast MCU with M4 F-core, where you can include a lot of smart functionality into your product. Something I also want to point out, so in our mobile robotics teams, we were working on multiple solutions. We have been working on our NXP FMU reference platform, and we're also working on a NavCube companion system software. And this afternoon, my colleague Ian Galloway is going to give a presentation about that. And we want to showcase what different ecosystems is. And for the people indicating that they attended the PX4 Developer Summit, there is a chance to win a free drone kit and NavCube companion computer. So check that out. Yes, thank you for listening to my presentation. Are there any questions?
Peter.
Yes.
Hi, can you hear me?
Yep.
Thank you for your presentation. That was really interesting. We have questions on Slack for you. Can you please join us in there? And our community volunteers will direct all of the questions to you.
Okay.
Thanks a lot for your time.
Okay.
Thank you so much, Peter. That was tremendous. Thanks for all your contributions to the community, and thanks to Dronecode Gold member NXP. I have a few announcements to make. If you're a company using any of the open source projects in our community and you're interested in supporting, please reach out to me. You can find me on Slack. You can find me on social media. You can go to the Dronecode website. We have lots of information regarding membership. The Dronecode membership is the second most direct way you can help the open source projects. Please reach out if you are interested and you have any questions. Feel free to bump into me on Slack. Thanks to the more than 30 Dronecode members that we have. Thanks for your tremendous support throughout the years, and thanks to your support, we're driving this community forward. So I look forward to hearing from more companies. Next up, we got another Dronecode Gold member, Microsoft. They're going to be talking about autonomous drone inspections using AirSim and PX4. Wara Kasuso and Paul Stubbs, they're both calling in from Seattle, USA. And let's see what Microsoft has plans for the PX4 open source community. I can't wait to hear. Please give me a moment while I connect you. on. Community, welcome back to the PX4 Developer Summit. I'm really excited to introduce our next speakers. We got Wala Casuso, Principal Product Manager from Microsoft, and Paul Stubbs, Director of Product Marketing for Microsoft AI. They're going to be talking about autonomous drone inspections using AirSim and PX4. Really excited to see what Microsoft team has today for us. So guys, take it away. Mike's all yours.
Awesome. Thank you, Ramon, and hello, everyone. My name is Wala Casuso. As Ramon mentioned, I work in Microsoft Autonomous Systems. I'm the PM lead for AirSim, our simulation. And here with me, I have Paul Stubbs, too. He is the marketing director for AI and is supporting our organization. Paul and I, we are super happy of being here with you guys today. And hopefully, we will be sharing things that are going to be useful for the community and trying to walk you through the progress that we have been made on the integration between PX4, AirSim, and also including some other Microsoft technologies as well. So that's us. And I think that before we jump to the key pieces of our presentation, I really want to mention this. For me, it's a milestone. It has been a year that, in fact, we decided to become partners and with Dronecode and to be around this amazing ecosystem. So I want to take a time to say thanks for this opportunity. For us, it's super important, and we see an incredible potential on the partnership itself. And I also brought two things here. One is big kudos to Chris Lovett. In fact, he has been a big contributor from Microsoft Research to all the efforts around the integration, as well as Radnesh Madam. If you have a chance to go through Radnesh's presentation, but he presented yesterday, and I think that the recording is available as well. He is one of our key researchers and leading the efforts around the V1 community. So with that, just before we jump to the core content, I would love to very quickly say what is Autonomous Systems. That is our organization, or the organization that hosts AirSim. So our main mission in the Autonomous Systems within Microsoft is to bring intelligence to machines. We believe that through the capabilities of sensing a dynamic world, we can provide safety and support many scenarios that goes from research to industrial applications. So with that, we will have some links at the end of the presentation in case you want to go and take a look at what the team is doing in addition to simulations. But you can do that probably through the links. Now I'm going to hand off to Paul, that he has the cool stuff here.
Thanks, Guada. So I just want to show you a quick demo of an inspection drone scenario. And we're really thinking about two main areas of drones for our autonomous systems and AirSim work that we're doing. The first is really inspections, right? The idea of an inspection scenario is that you're trying to get some sensor, a camera or something over some spot on the earth to gather information and take pictures or detect gas leakage at an oil refinery or something like that, right? And the second scenario is around delivery, where the goal is to take some payload to a certain spot on the earth and drop it off in the case of, package delivery or maybe precision farming, right, with fertilizer or things like that. So this demo is really inspections, which is how do we move a camera around in space and detect objects. So when you go to think about building a demo for drones, it's not just about how do you fly the drone. That's one part of it, and that's a big part. And that's really the part that we'll talk about today, which is around autonomous flight. And then also vision and object detection. So in case we're doing inspections, how do we detect objects that we want to inspect, and how do we detect objects we want to avoid for autonomous flight? But through all of these missions, there'll be other elements, such as a mission builder. How do we know what waypoints to fly? How do we know the weather? How do we know, can we fly? Like all of that is in mission builder. And then we have the other aspects of any solution, which is managing and monitoring, reporting and telemetry and alerts, right? And that's another big aspect of building a drone solution. And then finally, mobile monitoring for keeping up to what's going on with the mission from a mobile device, or other stakeholders can monitor the missions or understand or view the telemetry or manage multiple drones or redirect them or retask them. And so mobile is a big part of that. So for this demo, we really want to talk about kind of the autonomous flight and the object detection sensor part of this. But with any drone demo and drones built with Dronecode and PX4, we have this sort of generalized architecture here, which is in the top left, we have our flight controller that's running on PX4 or something like a Pixhawk. And then we have a companion computer running, for example, here, an NVIDIA TX2 or an NVIDIA Xavier board. And we run ROS2 on top of that. And we also can run our inferencing and reinforcement learning models on that. And those computers talk to each other through DDS, because ROS2 is DDS compliant. So they talk, the flight controller and the companion computer talk on the drone through DDS. And then we have at the bottom left, ground controller. In this case, it's our Q ground control, and that's talking to the flight controller using MAVLink. And then both of those systems, but more so the ground controller, can communicate with other edge services in the cloud, in the Azure cloud, things like the simulation and sensor information and storing of telemetry and alerting and security for deploying and the other existing machine learning APIs that we have in cognitive services. So all of these elements come together to build an inspection drone scenario. And so for this demo, I put together some hardware and sort of what the canonical example would look like. Starting on the right, I built a mini ATX computer that has, it's an Intel chip in there. It's running 32 gigs of RAM. It's running an M2 SSD, and I have a NVIDIA RTX 2080 as the main processor. And then I have a monitor that I can display, and you can see we're running AirSim, and this is the demo I'm going to show you in a minute. And if my hardware, I'm running a UAVCAN Draco research drone, a Draco R. And so on this research drone, it has a Pixhawk built in, and it has a TX2 board built in as well. And so the demo scenario is that I start with software in the loop, right? I want to do software in the loop to do everything I can in a Docker container on the machine, test all the components. And then at some point, what I want to do is switch over to hardware in the loop. And in this case, I have the drone plugged into the computer. I can deploy the flight controller, the PX4, directly to the Pixhawk hardware, where in the software in the loop, it runs in a Docker container. And then I can deploy the companion computer code, the ROS2 code, directly to the TX2. And that gives me a much greater surface area of testing my solution before I actually spin any propellers or fly anywhere. And so this is a really great kind of dev flow to get back and forth between the demos. And so let's go ahead and take a look at what this looks like. First thing, I start everything up with a simple PowerShell command. So we can go to my source folder and then launch this PowerShell command that will kind of kick off all the elements. And in this demo, you'll see all the elements in that architecture slide kind of come together on one box that makes it super easy for a developer to kind of iterate quickly on what's happening. So the first thing we're going to launch is the PX4 running in a Docker container. So this is a PX4 running in a Docker container that's going to be my flight controller. So once I have my flight controller set up, I'm able to start up Q ground control. Q ground control will then connect to that UDP port to communicate with the flight controller here. And then AirSim spins up as my vehicle simulation. And that connects also to Q ground control and then to the PX4 as well in the Docker container. So also what I have on my companion computer here, once I fire this up, it's actually reading the image messages coming out of PX4, which those images are generated using the sensors in AirSim. So we're getting synthetic image data from AirSim through PX4 that I'm reading in my ROS nodes. And then once I have those nodes coming, what we've also done is I've created a web page for us to have a 2D projection of the world that we're going to see. Let's just rearrange the windows a little bit to give us some space. So this 2D projection comes from the neighborhood scenario that's built into AirSim, and then we can read the messages coming out of ROS and visualize them on this simple web application. So next thing, all we need to do is load our mission so that we can fly around the neighborhood. Now the mission is a simple square that we're going to fly down the streets, and we're going to look for cars parked in the street. So we've uploaded the mission through PX4. Now we're able to start the mission, which then you'll see as we start in Q ground control. AirSim on the left takes off because we're controlling AirSim as our vehicle through PX4. And we start to see the visualization of that telemetry data on our 2D projection in the middle. And then we can start detecting cars. And you can see the sensors that AirSim has out of the box that we can see visualized at the bottom, the different types of sensors that we're looking at. And we can read and infer those sensors. In this case, we're using just a simple YOLO algorithm to look for cars that are parked. So we come up with some cars here, but they're in shadows, so we don't really see them. So this would be an area that we'd go back and test and try to find an algorithm that can detect those cars even in different lighting conditions. So here we see a car that's in pretty good lighting conditions, and we should be able to detect this one easily. And in fact, once we detect it, we just simply put a pin on the map, and we can actually see those cars and log those and save that for later analysis by somebody or another system. So from here, the mission continues. We continue looking for cars, and we continue to fly back towards our waypoints in the center. So I just want to dive in a little bit about the simulation used in here in AirSim and how that really enabled this scenario to really come alive. Now, as I said before, there's lots of lighting conditions that are difficult for computer vision to detect today. And it's not reasonable to ask somebody to fly in these conditions without having a good model yet to train. And so we do that training and simulation. Here we sponsored a team from Carnegie Mellon for the DARPA Subterranean Challenge. And we were able to produce a number of environmental conditions such as fog or smoke in the tunnel that they could train on before they actually even enter the tunnel. And in fact, we created a 3D representation of the entire tunnel system for the challenge. And they were able to fly this mission thousands of times before they even got on site for the actual contest. And so once they're in the tunnel, they can now train it to detect things that were part of the challenge, which are things like backpacks or toolboxes or fire extinguishers or things like that. And so this really becomes a very rich visual environment that you can train your vehicle in either both cases, either ground vehicles or air vehicles inside of AirSim. And in fact, the vehicle that they used for the challenge was actually very innovative. So the challenge required them to fly underground for 90 minutes. But most drones don't have that battery life. And so what they did was they have an AGV that they created, a ground vehicle, and the drone rides on top of the ground vehicle sort of as a mobile battery charger. And so the two work together. So we have a good solution for robot-to-robot communications and swarming, right, and squad type of environments and coordination where they can go together. And when they get to a point where they need to inspect a tunnel, the drone can take off and go inspect that area of the tunnel, come back and charge, and they can continue their mission. So it's a really good leveraging the capabilities for each platform the best, right? And it was very useful to have AirSim to be able to handle both ground vehicles and air vehicles. So with AirSim, you know, it's based on Unreal, and we can then get very rich visual environments. And the environments can be as rich as you want to or need them to be at any point in time. We can simulate city environments or urban environments. We can simulate warehousing and how do we do logistics. We can simulate rich vegetation, and we can do lighting conditions and weather. And in fact, this is the way that many of our customers start, because you want to test all of these scenarios before you take your multi-$1,000 drone out into the field. And in fact, we have a number of enterprise customers doing this today.
Yeah, and let me talk about that. In fact, Paul, thank you. I think this is great. I really like that inspection demo because it really shows how an industrial scenario or can leverage the integration of both PX4 and AirSim, and also the cloud, right? That we will talk later about that. But I think that going to the industrial applications, something that I would like to share with the community is two cases mainly that we just delivered last year. One is the CES 2020 demo where we, in partnership with Bell Flight, we in fact implemented a scenario where we provided simulations for training UAVs and being able to operate in a GPS denied environment. So basically, we train swarms of drones to go from one location to that it can be or can be delivery itself, where you have to go from one location and land and use visual objects identifications for that. And AirSim was a key piece because mainly what we did is train the AI models that were running on the drones to be able to perform the task, as well as we also use AirSim for runtime and visualization. That is something that we are seeing as a big use case now for a lot of customers when they want to ingest real data, telemetry, and use AirSim and simulations in general itself to visualize the current operation and make decisions as they run. And then the other case that I think is it really touches me, this one, because it has to be with wildlife preservation as well as clean energy, is what Air Autonomy is doing now. That is working on turbines inspection. In fact, one of their main customers is Excel Energy, and they are using AirSim for training the drones to perform the missions, be able to monitor and supervise the different turbines, help with any defects that you can have in the operation, as well as also the identification of hazards and the recognition of wildlife around the turbines in order to avoid any accidents. So I think as we move forward, we have many conversations with customers today that are willing to bring their own environments and make sure that they can run simulations to, I think, three different use cases. One is the development, the design of scenarios where they want to try and they want to make sure that everything is safe. And we see individual agents, UAVs or ground robots or the mix of them or swarms. Then we see testing and validation, where in fact regulations are part of that as well. And then the last one is, how do we use AirSim today for the visualization of the operations? So really a lot of potential on this area, and I think that we are all learning too on what are the main uses of this technology. So with this, Paul, I think, yeah, let's talk about deployment. And in fact, we included this last minute in the presentation because this is a new feature that we just added to AirSim open source, and is how to deploy AirSim in the cloud, mainly Azure, that is Microsoft Cloud itself. And based on the use cases, we identified two main needs. One is to use the cloud for development. You can think of this as I really need to have an environment. Today for AirSim is Unreal plus the binaries and other dependencies running in a machine where I need GPU and I need another requirements, and I don't have it in my own capacity now. So I scale that through the cloud. So basically I can deploy a VM, and through different command lines and scripts that we provided as part of this deployment package, you can have the development machine. We are also seeing uses of this as I want to share a demo, and I would love to have multiple developers or sometimes teams around the same simulation environment, so I can share this without the need of really making any infrastructure investment. And the second piece is, how can I test this at the scale, right? And I think that as we move forward with simulations, you really have the need of start testing different configurations, different variables. If you think about the environments, how do I test different weather conditions considering the same scenario itself? So I make sure that the data that I generate to train my autonomous agents is really substantial to get a level of accuracy where I can gain a right fidelity for that. So we made the efforts around this, and we can go to the next part here, Paul. So this is a recording of how the flow works today. If you go to the documentation of AirSim, we added a new section that is AirSim running on Azure. You can go there, you can have the different options, as I mentioned before, where you can deploy your own VM for development purposes, or you can also deploy a container. And I think the documentation is enough to really help you with the testing of this. So I encourage to go through that, but mainly is having the knowledge on how to package binaries and use what we provide currently on AirSim, as well as probably experience with Docker will be super helpful if you want to go this way. And again, I think there are two main scenarios. We differentiated that way based on what we are learning that are the requirements, but as you start using it, we would like to hear more about what is useful for the community. And we included in the site, in fact, a button that says deploy to Azure. In order to simplify the experience, if you just go there and click, you will be taken to the Azure portal itself. For this, you will need an account. The requirements for VMs are GPU, so you will have to probably scale a little bit on what it is a test account, but you can definitely provision a subscription. You see all the experience as we walk through this. You just create a resource group that mainly is a group of resources, that's to say relevant there, that goes from the VM and all the networking that is needed. You have to give it a name, give it a password to your VM. You can configure the size of your VM. In this case, we provide the baseline is the NV6, and you can check more around VM capacities on the Azure documentation. And then we provide finally scripting to simplify all the experience. And after that, you can review that everything is fine, and then just start the provisioning on Azure. That should be super simple. And as I said, we prepare everything in this template and experience to really facilitate the things for you and make sure that you have all dependencies and everything is ready to go once you continue the path. And we also added support for Visual Studio Code. In fact, we find a way in which you could connect through SSH to the VM that you just spin up and just establish the connection. And once you are there, you are able to clone the repository and just start using and running your simulations. Of course, as this is the case of the development sandbox, you can modify the code and rebuild the binaries and have it that running. And the experience, I think, in general, or our goal with all these efforts is to provide you with starting points where, again, you can use the binaries that we have today, or you can create your own binaries. And in fact, the customers that we have, they brought their own environments, and you have to rebuild the binaries as well as probably add some code configuration. But I think that that's the first step that we want to provide to facilitate the adoption of AirSim. And well, as Paul mentioned, I think it's also worth to talk about other components in addition to simulation as well. When he presented the demo of inspection, and when we designed that flow itself, we talk about many potentials there. And one is to really leverage another components of Microsoft as part of that as well. One big is Microsoft Cloud, Azure IoT, and everything that has to be with Intelligence Edge. That brings also capabilities for deployments on the edge, in this case, the drones, as well as to really bring another AI services that could help on that. If you go to our autonomous systems organization, you will also find Bonsai, that is the way in which we provide teaching learning capabilities and other advanced reinforcement learning that can be transferred and run in the drone itself to be able to perform different autonomous operations. But this is just a glance of what we are doing today. I think that there is a tremendous potential ahead to really continue integrating the different scenarios. There you have all the links from the resources. And of course, you have the GitHub repo of AirSim, as well as communities around that. We will be happy to chat and learn more about how you are using AirSim today. And again, how do we take this integration to the next level?
Great. Thank you, everyone.
Yeah, thank you.
Thank you, Paul. Thank you, Wada. That was awesome. There's a few questions from the community for you. Would it be okay if I share those with you? We still have time for 1 or 2 questions.
I think we're back to Ramon for some Q&A.
Yeah, I think so.
Yep, you're still on stream. Can I ask you 1 or 2 questions? Okay, so let's do this. I'm going to share the questions with you, and you can help me on Slack answering those. Community, hey guys, welcome. So we're going to have Paul and Wada on the PX4 Slack. Feel free to ask questions there. Our amazing community volunteers have collected all your questions, and we'll share them with them. And join us on Slack for them to get your answers to your questions. Wow, I'm running out of energy, surprisingly, but I still have a lot of coffee, so let's run strong. We have 2 more hours to go. Thank you, Wada. Thank you, Paul. Thank you again. Thanks, Microsoft, for your gracious sponsorship of Dronecode and the open source communities through your gold membership. Let's see what we got next. All right, so next up, community. So I'm back, your host, Ramon Roche, program manager from Dronecode. How are you doing? I hope you're not as tired as I am. Let us know in the chat. I want to see your pictures on the PX4 Dev Summit hashtag. Help me feel better. Help me recover my energy by looking at those awesome pictures of your dogs, of yourself taking a selfie in front of your screen, watching us. Thank you again for being here. You guys are really awesome. Let's see what we have next. Next here on our agenda, we have Hamish Willie on a pre-recorded talk. He's going to be giving a deep dive into the PX4 documentation. He's the PX4 lead behind our docs, and he's responsible for all the amazing content on docs.px4.io, dev.px4.io, documentation for QA control, for Maplink, for MAVSDK. So all around the go-to guy for documentation. So don't miss his presentation premiering soon on YouTube channel. And then on this channel, sticking with me, next up we got Dronecode founding member and one of the pillars for this community, Chris Anderson from 3DR, joining from beautiful Berkeley, California. And Chris is going to be talking about FAA type certification using open source PX4. This is the last session of the regulation track. We're almost over with day 2. Don't move. We'll be back with Chris Anderson. on. Community, welcome back to the PX4 Developer Summit Day 2. I have Chris Anderson on the line. He's going to be speaking about PX4 and FAA type certification. Chris Anderson is the CEO of 3D Robotics and a member of the FAA's Drone Advisory Committee, lead the ASTM, behind the ASTM drone type certification workgroup. 3DR is one of the first companies to go all the way through with the FAA new durability and reliability type certification process for low-risk drones, and works closely with Microsoft AirSim team, laying the groundwork for simulated PX4 data to be accepted in lieu of real-world data for some of the required DNR demonstrations. Chris is one of the founding members for Dronecode, overall pillar of the community, and I'm really excited to have him at the Dev Summit. Please, community, let's welcome Chris Anderson.
Thanks, Ramon. I assume we are actually live. Is it showing up on the stream? Okay, very, very good. Hi, everybody. This has been really impressive. I'm so proud to see this community growing. As Ramon said, I've been here from the beginning. Really the beginning, like 2007 beginning. These days, most of what I do is on the regulatory side. One of the curses of being successful in building up a bottoms-up organization and then bottoms-up community and helping create what we have here today is that at a certain point you go from the hey, we're just kind of working in the gray zone, we're kind of under the radar, we're just researchers and DIYers, and at a certain point you win and you're just like, okay, this is real, we're really out there, we're doing important work, and then you have to comply with the regulatory process. And in this case, the regulatory process was really not designed for what we do. And so we had to help create the regulatory process. And so what I'm going to be talking to you today is about where we stand on that, an exciting new development. So let me just switch now to my presentation. I hope you can see that. I'm going to be talking to you sort of with two of my hats on, the FAA drone advisory hat and the ASTM hat, which is the standards body, which we'll talk about in a second. A lot of the things we're talking about have been echoed in some of the previous talks that have been going on, so I'll cite those where relevant. But basically, the big news here is that the big news here is this notion of type certification. And you may ask, why do I need type certification? What's this all about? We're flying fine right now, but the reality is that we are not flying fine. As the IRIS presentation pointed out yesterday, we're supposed to be flying autonomously beyond visual line of sight, doing all those things that drones can do, and yet, today almost all operations are limited to beyond, to within visual line of sight. Under 400 feet, one pilot, one vehicle. Basically, the drone industry has not yet begun. The drones are supposed to be autonomous vehicles flying, anywhere, anytime, under their own steam. And we're still at a one person, one drone world. And the reason being is regulation. Technically, as you've seen over the last 2 days, technically these drones can fly autonomously anywhere. But we're not allowed to in the United States. And by the way, this presentation is going to be focused on the United States and FAA. I'll touch a little bit on parallels elsewhere. So what's stopping it? And if you look at this slide that Iris showed yesterday, the stats, yes, the beyond visual line of sight, waivers have been issued, and yes, there's more of them, but there should be thousands, there should be hundreds of thousands, there should be millions. You shouldn't need waivers at all. It should just be a normal thing. And so we're really waiting for something, and that something is a foundation of safety, which is called type certification or airworthiness of the vehicles. Right now, the FAA, all the things you've been hearing about, whether it's drone delivery or the IPPs or any particular operations beyond Part 107, have all required a special waiver or an exemption, and the FAA is just overwhelmed by these. Now, that's because they're all different. It's kind of an ad hoc, one-off sort of regulatory process. And what they need drones to start to look like the things they're used to certifying or used to regulating, and that means type certification. But type certification is the kind of thing you heard about with the 737 MAX. It's extremely expensive. It takes a long time. It's designed for vehicles that can be, jetliners. And the question is there a form of type certification that was appropriate for this new class of small unmanned vehicles? And the answer is yes. And not only is the answer yes, but I'll be talking to you about that. And the deadline is actually this year. So many of these exemptions and waivers, and especially the IPPs, which are these pilot projects, are expiring in October, just a few months. And so we need a new form of certification to be able to allow these kind of operations to not only continue, but expand under a process that doesn't overwhelm the FAA. And so the answer is a new form of type certification. I want to call out two more quotes from the IRIS presentation, which I thought really made a good point, which is that although it is a pain to have to go through the certification process, and we've been lucky to date that in the early days of the drone industry, because of things like Part 107, because of exemptions like developer exemptions or recreational use exemptions, we've been sort of spared all this. And it does seem like it's like I thought this is what we're trying to avoid, but in fact, it's actually a good thing to get certified, because it's going to allow us to accelerate, from here. It's a little bit of pain right now for a lot of gain later, and this is going to allow this autonomous era of the drone industry that we've wanted all along. The new form of certification is called durability and reliability, and it's basically streamlined. It is supposed to be, compared to traditional type certification, which I'll get into in a second, this is supposed to be fast and cheap, and it allows you to continue innovating, and more importantly, it reflects this new class of FAA regulation called performance-based. So in the traditional form of certification, they actually certify the individual components. So engines have to have, maintenance standards and mean time between failures, and just gets down into every little element, including the software. And so, one of the reasons that the 737 MAX was such a crisis is that the software really had not been, the software is dating back, 30 years, and that it's because it was so expensive to recertify the software. Anytime they wanted to make a change, it was a patch on top of the old software. And so at a certain point, after 30 years of this stuff, the patches outweigh the core code, and it becomes a maintenance nightmare. And that's really where they were. And so the notion is, what if we treat the vehicle as kind of a black box? And you say, look, we don't really need to know, we, the FAA, don't really need to know what's inside it. We don't need to know what the individual, reliability of the components are. If the entire system proves that it does what you say it's going to do, and it's durable and reliable, then that's good enough. And then you can do minor changes, within the vehicle itself, including software updates, as long as it doesn't change these overall performance parameters. And that's exactly what we want. I think that reflects what's appropriate for this class of low-risk vehicles and this pace of innovation. We don't want to have to lock down PX4 on a vehicle and not be able to update it for the life of that vehicle without having to go through certification again. And so, the ability to do these kind of minor incremental maintenance and improvement changes is really going to help us innovate. So who can apply for type certification? This is again a U.S. effort, so you have to be a U.S. company. You have to have what's called design authority. So whether you design and make it yourself, or just design it and have someone else make it, or even work with somebody else who's like an ODM who has components that you can use, somebody needs to be responsible for the design. And that's called having design authority. And by the way, a part of this I know is because 3DRs is going through this process as well. And we're one of the first in, we'll probably be one of the first out this year. So we've been through the entire process. So we really know it well. And so in the questions, I can talk a little bit about what design authority entails. You have to have a U.S. production facility. And the reason is because they're going to do a production inspection. You need a production certificate on your facility, and that needs to be here as well. And the vehicles need to be in this sort of low risk category, which you probably think of as 55 pounds, but is now expressed in newtons and energy based on the kinetic energy of the vehicle. So it's a combination of weight and speed. TC by itself will not let you do all those wonderful things, but it does make it much easier to get to those other places. So once you have the TC, your aircraft is considered airworthy, and that's great. Then once it's an airworthy, then you have to work with an operator, or if you're like a Google Wing or an Amazon Prime, and you are yourself an operator, you just go to the FAA and say, well, this is how we're going to operate. This is called our ConOps, our concept of operations. Here's the safety protocols we're going to do. Here's where we're going to fly, and what times and things like that. Now, it doesn't have to be specifically one geography, and that's the difference between this new form and the old exemptions and waivers. But it has to be a certain class of airspace, a certain class of geography. So if you say, we're going to fly over unpopulated areas, that's great. If you say, well, we're going to fly over populated areas of a certain population density, well, then there's a way to address that as well. But once you get that permission to fly under those ConOps, you can basically take it anywhere and any time where those environmental parameters hold. And then once you have that, you have permission to fly under that type certification. There's certain requirements about tracking your flights. If there's a crash, that needs to be reported. And if you want to extend your operations, you just go back and you say, we'd like to extend our ConOps to maybe a higher population density, and maybe some additional tests you do for that. The way this contrasts to the traditional type of certification that Boeing or Lockheed Martin would do is that as opposed to like a decade or longer, it's supposed to take 3 to 6 months. Now, this first one has been we've been working on it for a couple of years now, but this is, once we get this dialed in, it's going to be 3 to 6 months. As opposed to millions of dollars to go through the testing process, this could cost less than $100,000, depending on how much of the testing you've already done. It's only for the small and the low risk unmanned vehicles. So you're not going to be able to make an air taxi this way, but it's a great way for the FAA to start getting some experience with this new performance-based type certification, building up data so that they can extend it to higher risk categories going forward on a data-driven perspective. To get this, you've got to do the demonstrations. They're not tests in the sense, because you've already done your testing as part of R&D. This is demonstrating to the FAA that your vehicle is durable and reliable. There's two classes of these demonstrations. The first one is just a lot of hours. You basically take a representative operation. So maybe you take off, it flies autonomously, for some lawnmower pattern, lands. If that's representative, that's fine. And you just do tons of them. You can see at least 400 hours, and it can go up to thousands depending on your ConOps. And then that you do those lots of times. And then there's a bunch of other demonstrations that you do just a few times, sometimes only once. And this basically demonstrates things like your failure modes, environmental range, etc. Now, there's 32 kinds of those, and we're going to be publishing the FAA will publish those as part of its so-called means of compliance, and we're going to be publishing as well in October as part of our ASTM regs. But when you take these 32 different kinds of specific demonstrations about different kinds of flights, different kinds of failures, and then you combine them with all the variations of environment and center of gravity and temperature and air pressure, et cetera, it gets kind of overwhelming. And so we're going to get into a little bit of how to make that less overwhelming with possibly with simulation. The FAA nominated me to lead the ASTM counterpart to this, and this is the way it always works at the FAA. So the U.S. regulators, and this is true for regulators around the world, they typically try to use industry standards whenever possible. So in this case, the FAA says this is what we want to see in terms of the means of compliance, but they don't tell you how to achieve it. And then they turn to ASTM and they ask ASTM, the standards body, to put together a working group, and the working group then comes up with a very long, basically, a tutorial on how to deliver the data that the FAA needs. And that's the working group that I lead. We are in balloting right now, so we've essentially finished most of our work. This is just one example of what it looks like. You can see that I've just taken one of the 32, and this is about geofencing. And the first column on the left is what the FAA says they want. They say if geofencing is used to maintain safe operations, demonstrate that the logic works, and that contains the vehicle. Now, then the second column says, okay, here's how you actually do that. Here's the demonstration you do. And then the over on the right, that's just an extension of that first column. And it introduces some of the things you should think about. And so like this is a particular case where you have two things going on. On one hand, you've got a failure. So it should, under this particular failure, the vehicle should be flying back home. On the other hand, you've got geofences. And one should not preempt the other. So for example, if you were to fly straight back home, you would actually be breaching a geofence, and there might be a school there or a building or something like that. So in this case, you need to demonstrate that your return to home also respects the geofence. And so this is this combinatorial logic that you need to demonstrate so the FAA knows it's going to work. Now, as I mentioned, there is a overwhelming, if you look at all the permutations of the tests you need to do and the environmental conditions, et cetera. And let me go back here, just one slide. If you look here, I mean, just look at the slide on the right. When you look at all that variations, just look at one, this is one test, which says, just fly a distribution of, just fly a mission. But then it says, oh, okay, well, you also need to do it with your center of gravity, full forward, full left, full right. You have to move your center of gravity around. So that means your payload, et cetera. And then you also have to do it under, for your high and your low temperature, high and low pressure, humidity, whatever else you specified. And if you look at all the edges and all the corners of this test matrix, you can get tens of thousands of tests, which you normally would have to do. Now, obviously, that's not reasonable. And sometimes you can say, well, look, on this particular vehicle, maybe center of gravity is super important. Fix doing this particular vehicle, it's not as important. So you just negotiate this with the FAA. But another way to do it is to bring in simulation. This is a big part of what I'm doing right now, and this falls on very neatly from Paul and Guada's AirSim presentation. So we're working very closely with the industry as a whole, but especially Microsoft, on coming up with a way to construct simulation processes that can be acceptable to the FAA for certification. So this is diagram sort of shows you how it would work. So the tests are kind of right down the center of your operations, the kind of things you actually encounter all the time. You should definitely do that in the real world, and you should probably do it enough times that you can prove you're durable and reliable. So that's where the 400 hours come from. Then you start to move to some things you encounter more rarely. These would be maybe temperature or pressure, situations, altitude situations, battery situations, power situations that are kind of very unusual. And if it's really risky, and you probably are going to encounter it at some point in your operations, and you should probably do a couple tests to show that works. But then there's a bunch of others where you're probably never going to encounter it, or it's very rare, or you don't think that it's high risk, or it's just that you just want to touch all the edges of the test environment, but you've already done the same sort of environmental testing and a bunch of other tests, and it feels a little redundant. And there's a case for just doing that in simulation, in automated simulation. Essentially filling out your sparse matrix and turning into a dense matrix where you really can hit all the test points, some of them simulated, some of them real. And our objective here with our simulation project is to figure out, how to choose which tests to do in simulation, how to run those simulations so that they're persuasive, and then how to statistically demonstrate that this is high fidelity, in other words, predictable or has predictive power to the FAA. So this is really exciting. Now there are other non-real world flight options that will also be considered. There's going to be wind tunnel. That's one way to do it. There's benchtop testing. There's environmental chamber testing. All of those can be and historically have been introduced as a kind of an alternative means of compliance. However, I think that given the volume of testing we're doing, and given how well this community has aligned around simulation, computer simulation seems to be the one that's new, and we should emphasize the most. So this gives you the obvious pros and cons. The cons are that the FAA really has very little precedent of accepting simulation in lieu of real-world testing. In addition, the FAA is pretty comfortable with deterministic simulation. They don't necessarily love simulation instead of real-world testing, but they get it if it's like if you're doing a binary, like the logic worked or it didn't work. But once you get into probabilistic simulations, it's we need to help us with a statistical model they can understand. And so what we've done is we've basically divided the world of simulation into two groups. There's the system logic, And that's kind of binary. It works or it doesn't work. And you saw that, I'm going to cite a little later in the talk, Julian No's presentation, which is excellent. And so what he showed you with the hardware in the loop and software in the loop was largely system logic. And he gave you a perfect example of some kind of combination of GPS loss and battery life and things like that. You just want to make sure that the failure cascades, just kind of all percolate through the matrix of combinations of actions correctly as expected. So that's pretty easy to do in software in the loop and hardware in the loop. And again, it produces kind of pass-fail results. The other ones are all probabilistic, and this is like, this has to do with simulating environments, simulating sensors, simulating wind and things like that. And there you're going to get, it will never be perfect, just because we can't simulate the real world with infinite fidelity. And so it's going to be some approximation of the real world. And the question is it good enough? So this is the way we're going to propose it. That you're going to end up with this. Here's the matrix of all the various combinations. This goes back to kind of Julian's work on the system logic. Here's all the combinations that you might see. I just kind of put numbers up there, but you can imagine what they are. And some of them it was easy to test in the real world. We do have what we call fail boxes that we put on top of a drone. It's really just a box with a separate radio connection, and that box will like cut out the GPS, or it'll cut out a motor, and it'll or it'll disable the RC. And those ones we can test in the real world. And there's a bunch of others that we can't test in the real world, or it's not practical to test in the real world, and those we'll do in hardware in the loop or software in the loop. This is a slide from Julian's presentation. This is one of the pre-recorded ones, and I really would encourage you to go back and look at it. It was fantastic. But just two screenshots from this. On the top right, you can see his hardware in the loop box, and that's great. You can see it's got some motors, it's got some servos, and in that way we can sort of test some basic logic stuff, and then you can automate those tests, especially in both in hardware in the loop and software in the loop. And he talked a lot about how you would do that. So that's a way to really do the logic testing at scale and to help populate the matrix. So I'll leave that to his talk and encourage you to do that. But there's a lot more simulations that need to be done. So those are just the deterministic ones. On the probabilistic ones, there's 6 more simulations that need to be done to essentially fully simulate a vehicle. There's the stuff that's kind of basic aircraft operations. This is what's going to be required by the DNR. There's the physics and dynamics, and then the environment. You have to simulate. You can't just simulate the vehicle. You also have to simulate the air and the wind and the temperature. So you have 2 simulations there: aircraft physics and then environmental physics. The GE presentation yesterday was also really good on this, and I encourage you to go, if you haven't seen that, go back and see that. They really focus on the sort of the best practice in physics and dynamics, how they found the right ones for them, the pros and cons of the various options. And so I hope to work further with them on that. I was really impressed by that. Then we need to simulate the environment. And the problem with many of the simulators we use today, like Unity or Unreal, et cetera, is that they're really good at simulating kind of video game environments. But what we need to simulate something that's appropriate to FAA, and a lot of this has to do with gusts and turbulence around structures, like in buildings in an urban environment. And this is a very unusual sort of it's fluid dynamics simulation. I'll talk to you a little bit later about the test environment. We're doing some of that right now, but those are kind of that's where we're going to be focusing. And just to give you one example of how difficult it is sometimes to assess the fidelity of a simulator, let's just say that we simulate wind gusts pretty well, we think. Well, how do we compare that to the real world? Well, how do we measure wind gusts across an entire area? In other words, all the wind vectors at all the altitudes and geographies in that entire area. Well, so the weather map won't tell you. That'll just tell you the overall weather. You can put up 1 weather station or 2 weather stations, that'll tell you what the weather's like there. You can fly the drone around and know what the weather's like around the drone itself. But how do you do the entire wind vector field for the entire area at a resolution that's sort of drone sized? that's really an unsolved problem. There's some efforts in doing that with Doppler radar. You can certainly do try to measure wind and gusts on the vehicle itself, and then to kind of project that into a vector field. But it's an interesting problem. We're going to be resolving that later. You saw that AirSim is highly focused on perception. And there it's not just cameras, but it's LiDAR, depth sensors, radar, sonar, and things like that. We have to simulate all those sensors. And then you have to, when let's say you're looking at a surface and you want to see, how can I see that? Well, which sensor? Can you see it with your cameras? I don't know. Is it nighttime? Can you see it with LiDAR? Possibly. Is it large enough to hit your resolution? What about radar? Well, what about the absorption of the surface to a radar? Does it bounce radar or does it not? And so we have to now model the material properties of the environment to get that right. And then we get into the stuff that was covered in the IRIS talk about detect and avoid and traffic management. There's quite a lot of good work, especially done by NASA and the FAA in the past. But detect and avoid in particular is a little difficult. Now, we don't have a lot of real world data of collisions, thank God, because those would be bad. And we don't want to go up and fly airplanes at each other all the time, because that would also be dangerous. And so now we need to kind of procedurally generate realistic collision scenarios, approach scenarios, combinations of vehicles, and that not only you are likely to see, but also the ones you're unlikely to see, but not impossible. And so that's going to be we're probably going to use things like generative adversarial networks. And there's been a lot of work on self-driving cars to model pedestrian car road combinations, including really unusual ones. And so we're probably going to build on some of that work in that domain. Then we get to the question of how do we prove the fidelity, and I'm actually doing a lot of work on this right now. There's something called a teal coefficient, which is basically actually comes out of Shannon information theory. It's information entropy, but it's basically you take two data sets and just sort of figures out how correlated they are. And so we've created a little bit of a tool here that you can see on the left, where you upload two data logs, one real, one sim. You can then, let's say that their coordinate systems are reversed. You can, quickly align their coordinate systems. You can sort of move them around so you align their timestamps, and then you can drag over the area you want to see the correlation, and it'll generate a teal coefficient. And we're doing this with some of the same teams that are working with Microsoft and the AirSim. This is autonomy and the University of North Dakota. And as you probably saw in the earlier demonstration, they're using a wind turbine field to do their research. That's actually really useful, because wind is the #1 thing that we need to simulate. And so not only do the wind turbines have, they have turbines, so they have, they know what the wind is at the turbine level, but also it's a wind farm, and so there's a really well characterized, wind environments and structures and turbulence around the structures, et cetera. So watch that space, but we're going to be, delivering some initial takes on the fidelity of AirSim against the real world, and also PX4, because that's what it's based on. And we're going to find out it's not going to be perfect. No, it's not going to be perfect. The question is, where does it matter? How predictive is it, and how do we make it better? So I just want to finish with this last slide before I take some questions. This is an ongoing research project that we're doing with an industry working group. You can see the list of the people we're working with right now. Obviously, I fully intend to add the GE folks and the IRIS folks, to say nothing of the Alterian folks to this going forward. We're really just getting started on this. It's an ad hoc group. It's not official yet, but we do, as part of the Drone Advisory Committee, I have been asked to interject it as a possible policy topic for the FAA and DNR in the future. And so what we really want to do is we want to kind of all get together, figure out what makes sense, prove it, with a couple pilot projects, and then deliver it to the FAA in the form of white papers, so they can then formally find a way to accept simulation data in lieu of real world data, to help us do the DNR type certification more quickly, more cheaply, more reliably, so that more people can do it. So that is the end of my formal presentation. I think that is also the end of my window. So Ramon, what do you think? Should I take questions here, or do you want me to just take them on Slack?
You can take a few questions here.
Okay, good. Let me go to Slack here, and the questions popping up. I will. I think they're also probably on the YouTube channel, right?
Yeah, they're in YouTube channel too.
Okay.
Don't worry. Let's do this. Why don't we send the questions on the public PX4 Dev Summit channel, and you can join us there in the community.
Yeah. There are two. There's one question I can take right now, if you don't mind, off the
Go ahead, please.
Okay. This question was, how do the updated FAA requirements affect waivers flights of experimental drones during the initial R&D effort? And the answer to that is that many of these are intended to expire in October and be replaced by type certification. I think, and this will not surprise you, we're running a little late on this. It's a bunch of things, but it's a new process for the FAA. It's quite radical, and I suspect there probably will be some extensions. That it's not like everyone's going to be grounded in October. But what you are going to hear, if you already have an FAA waiver or exemption, you are going to hear from the FAA that they're going to want you to pretty much start entering the type certification process now. They're not going to want to continue extending the waivers if they don't have to. So get on a type certified platform. There will be several. Some of them are coming out of the PX4 community. There's at least 4 that I know of that are going through the process right now, including the 3DR H520G, which is our collaboration with Unique. So there will be choices, but in addition, there'll be a lot. The work we're doing right now is going to make it a lot easier for anybody on PX4 to get into this process if you can partner with or are a US company. So I will take the rest of the questions on Slack. Thanks so much.
Awesome. Thank you, Chris. Community, welcome. Thank you, Chris. That was super insightful and clear. I want to thank you in the name of the whole community for all the years of incredible service to our open source community. Thank you so much for the leadership, and talk to you soon. See you in Slack. All right, so let's see what we got. Hey, Ramon here, your host, Dronecode Program Manager. How are you doing? Are you still up? I don't see a lot of pictures on Slack yet. Thanks everyone for watching. Especially our friends in China. Did you know we have a mirror in China? Our beautiful partner Dimian Sang has hosted a mirror, and we have a lot of community members from China right now. It's like 5 a.m. in there. Thank you guys. Thank you. We are going to be hosting an after party. I think we've been leaking this on purpose. But we're only sharing that through Slack, so make sure you join us on Slack. Our community volunteers are going to be posting a few links in there so you can get an invite. The after party is not going to be streamed through YouTube or any of our social media channels. It's going to be an invite-only party, so make sure you get your invite before the next session ends, because there's going to be a short window where you can get invited. So make sure you stick with us till the end. All right, so keep sending your selfies. There's going to be a few surprises coming up next. All right, so next on our agenda, let's see. The last session from the pre-recorded talks is from Paul Weisbrot. He will be giving us an update on the PX4 state estimation. He gave a talk on the 2019 PX4 Dev Summit, which was super insightful. Fun fact for Paul, he is the only repeating speaker on the PX4 Dev Summit that joined both conferences remotely. Time zones are hard, people. Scheduling is hard. And I want to thank everyone here, all of the speakers, for doing the extra effort to be here. Paul, thanks for all your contributions to open source. And I want to take you, community, to our very last session of the live stream. This is a bittersweet moment for me. I'm going to introduce our next speaker, and then afterwards I'm going to be doing our final closing announcements and thanking the community, of course. But next up we got Ian Galloway. He's a drone program lead at NXP, and he's going to be calling in from Prince Edward Island, Canada, very far east Canada, and he will be talking about Hover Games Challenge 2. NXP Hover Games is a virtual coding and hardware challenge that takes place over several months. Using the NXP Hover Games Drone Development Kit, you'll address some of the biggest challenges facing society: disaster management, health crisis, environmental protection, wildlife conservation, and more. Horror Games Challenge 1 was about firefighting with flyers. That was a really cool competition. Dronecode has a prize for one of the winners for the previous competition. We're also going to be judges of the second competition. We're really excited to have NXP here. NXP's Gold Dronecode member. They're big supporters of the open source community. And give me a moment, like, while I connect you to Canada, back to Ian. All right, be right back. Go. Community, welcome back to the PX4 Dev Summit. Our very last speaker of the day, Ian Galloway. He's going to be joining us from Prince Edward Island, Canada. He's a drone program lead at NXP. NXP is a Dronecode Gold member. The NXP mobile robotics team looks across the breadth of semiconductor products from all the NXP business lines. This includes automotive, industrial, medical, RF sensors, and wireless semiconductors. The team prepares the reference designs for FMU, CAN, two-wire, Ethernet, security, and companion computers. Horror Games is our flagship program, which provides a complete open source hardware and software design and interesting virtual challenges to get people started in development in drones and rovers. Community, please welcome Ian Galloway.
Hi, everyone. I'm here from Prince Edward Island, as you can see my background. Let me just share my screen. And is that sharing well, Ramon? All right. There we go. All right. So for those of you who haven't seen, there's been a few of my colleagues earlier that mentioned about NXP Semiconductors. We're a global semiconductor company, and one of our focus areas is in automotive. We're a leader in the automotive industry, but of course, industrial, mobile, smart home, smart city, our parts tend to get used in high reliability or long life parts, medical equipment, those sorts of things. The mobile robotics team is a small team. It started as a small drone team, and we were lucky enough to be able to focus on that. And I identified PX4 early on as the software we wanted to focus on because of its applicability and ability to be commercialized as well. We've since expanded a little bit to become a mobile robotics team. We've adapted some things like our NXP Cup car. To be able to use our flight controllers and things like that, PX4-based components on vehicles. We've also done experimental VTOL aircraft and delivery vehicles. But really what as Ramon said in the introduction, we really look across the entire spectrum of components from NXP and to see what is applicable in the drone space. And in particular, what we know is the area of most interest or most concern that where we can help is with automotive functional safety parts. And that means ISO 26262 and ASIL, which is an automotive safety level part that include things like onboard diagnostics and error correcting memory, and really taking these, what is a mature, let's say, came up from the hobby drone industry and making it more mature and suitable for things like BVLOS, like Chris was just talking about. One of the important things to note is we don't build drones. We only build reference designs. Now, we do sell a drone kit, but I'll talk about that later. But we're not in the business of making these kits. We're in the business of selling semiconductors, and everything we're doing here is to help others work with our components and get a jump start in solutions for this space. To give you an idea of automotive grade components, just to give you sort of a block diagram feel for the types of things we're talking about. This is an S32S. It's a safety-based component that's meant for things like automotive drivetrain, and you can see right off it's quite a complex part. It's got 8 cores. There's 4 lockstep cores, so each of those has a backup. Over on the system block, you can see things like built-in self-test, and these are the sorts of things that make automotive parts automotive. They're built very carefully. The construction of the semiconductor is quite a bit different than, say, a cell phone type of part. This particular part has lots and lots of memory. And I'm not going to go over the part. I'm just saying in general, this is what you can expect from an automotive grade component. And we're working to enable those. And particularly the drone team or the mobile robotics team is able to be the bridge and help manage the challenges of using a part like this in a non-automotive industry. Normally these are millions and millions of pieces that get used, and they're made by they're being worked on by automotive vendors, and we were able to make the bridge to much smaller, of course, drone solutions. One of the first things we did as a mobile robotics team was build a flight controller, and this is a pretty generic looking flight controller. It's got our PX4 connectors, and it's not a particularly small form factor. It's sort of same as a regular Pixhawk. It's based on an FMU V4 design, but we did add our own twist on a few components, particularly, of course, CAN, and future parts we have CAN FD included. But the first one that's quite a bit different is the TJA 1100. It's a 2R automotive Ethernet. And that allows you to have an Ethernet connection with just 2 unshielded twisted pair wires. Very well suited for drones and rovers and mobile robotics applications. Another part we included that was a secure element, and this was our first part to start introducing this. And it allows you to start experimenting and developing on it. So we had a flight controller, and now we said, well, what if we're going to have a flight controller? We might as well have a drone. So we built to put a drone kit together. And it's a very complete and quite a decent size. It's a 500 millimeter frame. It's got nice space for additional components, and made a complete development kit. And when we had a development kit, we said, well, we should maybe have a competition. So that's when Hover Games was born, and it uses the drone development kit. And we put forward a challenge, but it's a coding competition. It's not a flying challenge or anything like that. We're trying to encourage developers to get involved in PX4 and grow the community and get people trying new things in the context of a drone. So it is open to basically everyone anywhere. And that means engineers, coders, developers. We have students. We have just hobbyists that are interested in learning a bit more. And we've seen quite a lot of activity as a result. We give out prizes. Our first competition was called Fight Fires with Flyers. And the results were quite surprising. We had over 1,000 people following, ended up with about 50 submissions in the end. And then we ended up also internally inside of NXP getting quite a bit of interest. And I'll talk about some of those results as well. So Hover Games is meant to be an ongoing competition as well. So in the 2019 contest, it was called Fight Fires with Flyers. The idea was to help basically in any way a first responder in solving or helping in fighting fires or managing fires. So you don't want to take that literally. We're not talking about dropping water, but how can a drone help in this situation? And so our first winner was got involved in machine learning, and it was looking for identifying people that might be stuck in a catastrophic condition, lost in the woods, etc. And so they implemented machine learning and cooperated with the drone over MAVLink communication, and implemented machine learning with an additional companion computer. Our second place winner was interesting as well. They equipped the drone with very sort of off-the-shelf fume or chemical sensors, and they used that to determine what type of fire it was, so it would help in the response. We had a number of special awards. One of them was a Dronecode award, and that's where they literally created heat maps. And I particularly like this because it showed the idea of a drone, a few $100 drone, and a very inexpensive heat sensor, ending up generating pretty good results in terms of resolution and sensing capability. You can see the heat maps. There's actually two different teams that did something similar, but by flying a grid pattern, you were able to easily detect small coals or embers or hot spots in the ground. And so it's actually very practical that instead of having quite an expensive drone, a first responder, a fire department anywhere could have one or more of these going out and searching for hotspots. The second place, I won't go into all the detail here, but we were impressed with the quick jump to machine learning that people did. And so this had several different sensors, also very low cost devices, and built a machine learning model to detect what type of fire it was. Another unusual one and quite interesting was a lightning detection system. So by adding a lightning detector, specialized IC, with some microcontrollers, another LPC micro from NXP and other components, it would detect lightning strikes, and then as you get a frequency of lightning strikes over a certain amount, the drone would be able to go out and inspect to see if there's a fire that needs attention or if something had happened as a result. So it was quite inspiring that there's lots of different unusual examples here. And then one of our internal participants did work with our ultra-wideband parts. We have some new ultra-wideband parts that aren't quite out to the market, but they were able to use it for the beginnings of precision landing by having anchors and doing sort of millimeter or centimeter level precision for locating drones in space. Now for the next Hover Games, I said these are ongoing challenges, it's not one-off. We were going to do a search and rescue type of fair, and of course the pandemic hit, so we thought it only appropriate, it would be a little insensitive to not to do something completely obtuse to that. So we pivoted and said let's do called Help Drones Help Others During Pandemics. And so we're looking at what interesting ways can we use drones to help other people during pandemics, and that could be like what can we learn? There's people get isolated. There's medicines that people need. There's moving blood samples from a hospital to a test lab. There's a lot of really innovative ways, and it does build upon the first Fight Fires with Flyers, where there was a lot of technology, extending radio coverage networks, and anytime there's a pandemic or a disaster situation, sometimes there's a need for a lot of infrastructure or support for first responders and that sort of thing. And so, we're thinking, how can we help people in any way? We're quite flexible on that. It doesn't, it can be quite a narrow focus, and it can be quite deep in terms of focusing on a particular software enablement as well. So we operate the contest through Hackster.io, and so applications are running until the end of July, and the contest runs all the way up until November. In promotion for this video, we did a flight YouTube video with flight test, and that was a lot of fun. One of the things we did was we actually built a tail sitter VTOL aircraft with the normal flight test build foam board build methods. And it's completely experimental. It was a lot of fun, and we do want to work on it some more to develop it further. But the thought here was, we had an opportunity to do something interesting. Maybe there's people in the PX4 community that would appreciate a low-cost VTOL tail sitter. So that actually is now, they're making it available for sale. And, the important thing is also that it attracts a large audience to PX4 development as well. This has already been seen. It's only been out for a few days, and we're up to over 120,000 people have viewed this video, which means they've all been introduced in some way to PX4. And so in Hover Games 2, we are now introducing a companion computer. It's based on an i.MX processor, an i.MX 8M Mini, and we're calling this board a NavQ. It's a little stack up of boards. It is experimental. It is new, but we're enabling things like the Vision, OpenCV. There's a camera on board, GStreamer, ROS, and this will grow over time. We'll do some rapid iterations on code as we determine what people want to see on a companion computer. It is actually for people that have already been in the first Hover Games. Again, it's only a $50 adder. It's quite an amazing discount that we were able to provide on a processor board of this caliber. It's basically a stack up of 3 boards. This SOM on the far left is a system on module, a SOM that is a more or less a duplicate of our normal EVK SOMs, the evaluation kits that we make for this processor. It includes eMMC memory. It has Wi-Fi and Bluetooth. The center board breaks out the camera interface, a display interface, and an SD card for your code. And then on the far right is a really what makes it a Hover Games board is all the PX4 connectors and UARTs, SPI ports, etc. So we can communicate with as a companion computer. Has a USB-C based power input, so you get 6 to 20 volt input, and we leverage that. Also can be connected directly to the battery of the drone. We also include an HDMI adapter, so if you wanted to use it as a little mini desktop, you could, and a Google Coral camera. And I'll mention over here on this slide, we're introducing a new form factor called an IX Industrial Ethernet, and you can see the reason is it's quite nice and small. These are made by Hirozi, and this makes it possible to have an RJ40, a small enough connector for on a drone, which is a replacement for an RJ45. So to join or find out more, these are basically the links you might want to follow. You can get to it anytime through hovergames.com. We do like to partner with other companies as well, so you can look at that and contact us there. But hovergames.com will get you to the right place, and then we do have a specific registration page. There's a user guide on GitBooks that shows you all about how to build. It's got step-by-step guides and videos. And then we have a list of different compatible PX4 drone hardware on this page, Hover Games Drone. And we can discuss things also on the PX4 #HoverGames Slack channel. Now I just want to talk about some of the new developments from the NXP Mobile Robotics team, because these developments move into the next Hover Games, and what what's coming up. Let's just jump in. So NavQ and NavQ Flow. Okay, so for the first Hover Games, we did introduce some new things. We had the opportunity to build some new hardware, and we had this little product called a Rapid IoT module. That's the blue part. And so we were able to make a adapter board for that would allow the Rapid IoT module to take these click modules. Whoops, click modules that can add lots of sensors. There's over 400 of them. And I'm sorry about that. And then we ported MAVLink to it. And so it allowed new experimentation with this. The IMX8M Mini that we're introducing has a lot of interesting features. It has the ones I've highlighted here. It's a quad core A53, so it's a Linux computer, companion computer, running at a 1.2 gigahertz. It has hardware encoders for video. It has one MIPI CSI camera lane, and then introduces gigabit Ethernet on board, as well as other things that are available on the chip, so USB 2.0 and PCIe, etc. This is already used in a number of other commercial drone applications. Later this year, we'll introduce an 8M Plus, and I'm quite excited about this one. The biggest claim to fame here is that we introduce a machine learning accelerator. So this is designed to accelerate neural nets and operating about 2.3 TOPS. It has, again, the quad A53 processor core. It does have a secondary M7 core that could be used. We have hardware encoders for video again. This time it does H.265 and wide dynamic range encoding. And then has a dual camera interface, which allows for, with an ISP. So it allows for things like dewarping and de-Bayer patterning and hardware. And with dual cameras, we can add things like both a front and rear camera, or a time of flight camera and a regular camera. The other thing that's quite exciting here is the connectivity. So we've now got CAN FD on board, which of course will support UAVCAN V1 quite nicely. 2 gigabit Ethernet ports, and that's also being seen as terms of connection to payload buses and things like that. And then 2 USB 3.0, which means if you were to use this as a camera head, you've got a nice high-speed USB interface that you could use, or of course you can pipe it out over Ethernet. And lots of other features here I won't go into. The important thing to remember or look at here is these are embedded, these are edge compute devices. And the idea is, unlike some of the other processors, we have optimized this so it's typically running at 2 or 3 watts. And when our current measurements today is when it's running flat out, it's only a 5-watt device. So it means that you can have multiple of these on board, and you're not going to require large heat sinks to weigh down a drone. Another new focus for the mobile robotics team is to use S32K. These are some automotive microcontrollers. In some ways, I kind of think of them as pickup trucks. They're not all that sexy, but they are rugged, and they're automotive grade microcontrollers. So these are M4 cores running at 100 odd megahertz. And this is what we've been using in some of our new products to give you this sort of entry automotive reliability in sensors and peripherals. And to that end, okay, so another part we've also been adding is our latest sort of flagship secure element called SE050. And we're a large supplier to many passports and credit cards and bus tokens and things like that worldwide. So these are the same sorts of components that are in those parts. It's got a huge number of different key and cryptographic tools that are associated with it. And by adding these to a drone, it allows us to include authentication of modules, of submodules, and then also be used for cryptographic key storage. So if you're trying to, let's say, give authorization to fly a drone only to the firefighter that is supposed to operate the drone, or that someone has to have a certain level of authorization before they're allowed to fly a drone in a certain way, and that could be managed through keys that are stored in a secure element. And these are used all over the place in terms of industrial authentication and commissioning of IoT devices and connecting them to different networks. One of the first products to include this is we had a presentation earlier here on the summit for UAVCAN, and we have this board, a little node, a generic UCAN board, which lets you break out the UAVCAN and go to traditional interfaces like UART, I2C, SPI, an RC PWM, so you could have build yourself a UAVCAN connected motor controller and prototype and experiment very quickly with a small, simple, low-cost board. And these designs that we do are completely open source. Like the software is open source based on PX4, and of course the hardware designs are completely open source and available for download from us. Block diagram here, we include the secure element, which has a optional NFC interface on the right, where you could maybe tap a card or tap it to another part of the drone to allow it to join the same network. Dual CAN FD. So now we can start looking at a UAV CAN application, and then yeah, fairly straightforward. There's not a lot of interesting, complex things here, so it's very flexible. Another board that we've also included these microcontrollers and secure element on, well, actually a different secure element, is our battery management reference design. This is enabled in PX4 as well. And we also included a slightly different authentication component, so even less expensive one, often used in consumable components, but it has the ability to do things like flag. If you had an abusive condition like a severe undervoltage or severe over temperature, you might burn or set a flag in the authentication component that is permanent. You can also permanently count cycles, and with that sort of thing, you know, under certain flight requirements, you might need to do that, and you might need to be able to prove that this particular battery pack only has so many cycles on it. And again, this completely open source reference design, and it's able to scale up to quite a high battery power current. I think over 90 amps capable. Another one is a media converter. So we said we had these 2-wire automotive Ethernet on our flight controller. In order to connect to that, you need a 2-wire automotive Ethernet converter. So we built one. This is meant to be like a little dongle, and it would allow you to connect, say, over to that companion computer, the NavQ companion computer. And again, this is applicable in all sorts of other areas as well. If you just want to try a 2-wire Ethernet, you can get 2 of them and plug 2 computers together and see how it performs. We decided to also build an automotive grade Ethernet switch. So we have a 10-port Ethernet switch automotive component. So put this down on a board, a small 50 millimeter by 70 millimeter, 75 millimeter, and with 6 of these 2-wire automotive Ethernet ports, a Hunter base TX port, and an IX industrial at a gigabit port. So this will be used for, this will be available for anyone to use, but also, you know, we may incorporate some of these things into future hover games. And then finally, I mentioned the precision landing. We've continued to do development on that, and we're working towards being able to land a drone to centimeter accuracy on a moving platform with our ultra wideband board. Some of these things are internal at the moment, but once we get a code developed to a certain amount, at a certain level, we'll be able to make this publicly available for the general PX4 community. And that's our sort of ecosystem. It looks a bit messy, but it's growing very quickly. There's lots of different components, both we're developing as reference designs, and that third parties have used our components in, things like even ADSB RF transponders for vehicles. So they use our LDMOS RF power amplifiers. We've got third-party companies building motor control, high reliability motor control, ESCs with IMX, RT, and S32K parts. And we'll be continuing to fill this out with other solutions that people can use as reference points. So back to hover games, which is what I'm talking about here. Why should I join hover games if I'm already working on PX4? Well, first of all, there's prizes, so that's a good thing. You can get paid, or if you win, you can make a little bit of money to support your investment in time. But it might just be the incentive you need to test or implement a new application idea. It also gets you FCC CE approved hardware. This is all approved hardware, past all the regulatory requirements, unlike some hobby level grade stuff. It is a complete kit. It includes everything but the lithium polymer battery. Radio controllers included, telemetry is included, those sorts of things. You get access to some of these new hardware features to try. You might be interested in encryption or 2R Ethernet or UAVCAN, and this hardware has it active and is able to test and use it right away. And then the other reason maybe you don't want to join yourself, but you might want to promote it to others in order to help grow the PX4 community. And the bigger the community is and the more people developing in the space, the better it is for everyone. So the final slide, and my colleague Peter also mentioned in his UCAN board discussion, this is how to get started. You join at Hackster.io or go to hovergames.com. It'll get you over to Hackster.io. But you fill out an application with an idea, and winning applications get a coupon to get the entire drone kit and the companion computer that includes the Coral camera, adapters, power cables, mounting brackets, USB hub, all this stuff for $300. If you happen to already have a Hover Games drone, you can get the NavQ for only $50. And if when you fill out an application, you mark PX4 Developer Summit on your application, one of you will get a chance to win a free drone kit and NavQ computer. Thank you very much.
Awesome job, Ian. Thank you. There's a few questions around how to join Hover Games.
Yeah. Am I on the right
you're
slide?
Still,
I'm still
yeah,
not. Okay. Yeah, how to join. Go to either www.hovergames.com or you go to this Hackster link, the direct Hackster link, which is Hackster.io contests Hover Games 2. And what you do is you basically write a little profile of what your idea is and share it, and that's the application in order to be judged if you sort of win the application round.
Awesome. And can anyone join?
Yes, anyone can join. I mean, I think there are a couple of restrictions in terms of certain countries we're not allowed to ship to. But yes, anyone can join, students, engineers, professionals. If you're employees of NXP aren't eligible for the prizes, but we do have an internal contest that follows the same track.
Awesome. And lastly, what OS are you running on the IMX8 Plus?
So we're going to be making a couple of options available. Normally, our customers are deeply embedded, right? So they actually want to build a stripped down, basically, usually an open embedded kernel or something like that. So it's very focused. And so what we've been trying to put together for this is a friendly Linux of sorts. It's sort of a Debian-based Linux, and we'll have a couple of flavors of that. We do expect some challenges there, but we're making great progress.
Awesome. Thank you for your time, Ian.
All right. Thank you.
Community, welcome back. Thank you, Ian Galloway. Since day one, NXP has been doing amazing work for the PX4 community. We're really excited to have you here. Next up is our next speaker, which is me. So give me one moment while I queue up my slides, and I'll be right back. Thank you. Ta-ta-ta. Community, we're back. Thank you for sticking with us throughout the whole day. It's been an amazing 2 days. Thank you for joining us. We're really excited to have everyone. We've seen people joining us from all across the globe. How did we do? Did you like the pre-recorded sessions? Did you like the live sessions? Which was your favorite? Let us know in Slack. We're still here. We're going to be here after the stream ends. And we're still going to be at the after party. So make sure you join Slack, slack.px4.io. Go to the PX4 Dev Summit channel, and there's going to be a special invite link in there. You have to look for it. It's not easy. So it's not, you have to earn it. Thank you again to the beautiful community for being here. I want to thank the Dronecode board for their trust and this event staff. They trusted us in delivering a great event. I want to thank all the Dronecode members for all the tremendous support throughout the year. I want to have a special thank you to all of our sponsors, Autharian, Microsoft, NXP, 96 Sports, CUAV, Holipro, UVFi, to our partners, Open Robotics, Hackster, and Innerdrone, and Demian Chan. Great work, guys. Thanks for all the support. Thanks for helping us spread the word. I want to thank our speakers, all 56 of them. You guys did amazing. Thanks for being so comprehensive and for being available for us and for the community. I know it's not easy to coordinate. I know it's a pain with time zones. We tried our best. We did great. Thank you again. I want to thank the community quickly. Thank you for being here for us. You've always been here. This event wouldn't be possible without you. This is great. I want to also thank our awesome staff. This is not the slide. So you see, this is why life is fun. Hey, here we go. Thanks, staff. I want to thank Ginger, Lawrence, Asian, Stone, Farhan, Bivu, Natalia, Javier, Gong, Guada, Hamish, Nuno, Julian, Arnaud, Ian. All of you have helped us get here. Thank you for your tremendous support. It's been really hard, but we did it. We managed. Lastly, we're going to send a post-event survey. Please help fill that out. There's going to be special prizes for those of you that help us complete it. There's going to be hardware prizes. Please check your emails. Stay tuned to that. If you're new to the PX4 community, this is the first time you have experienced open source drones, welcome. We're really excited to have you here. Please let us know how we're doing. Please let us know if there's anything else we need to do to make sure we're inclusive, we're open to everyone in this community. If you're a long-term contributor to PX4 or any of the ecosystem projects, thank you. Thank you again for all the work. All the people that are live here, they're here for you. So thanks again. Thanks for making this project so good. And without anything else, I want to say bye, I guess. I don't want to say bye. Oh my God. Thank you guys. Until next time, see you in Zurich next year. All right, here we go. Bye.